All right, good morning, everyone. I think that's time to start with the first session for this morning. So thank you very much for showing up. So my name's Adam Michaelchuk, and my co-chair this morning is Yuki Hajiwara. And we'll be giving a brief introduction to this morning's session on crystals under light and force. Now, just before doing that, we have a brief announcement from the organizing committee that the group photos that we took a couple days ago are now available to collect just in front of the lecture theater here, so you can do so at the coffee break or later on today. Right, so thinking about crystals under light and force, it is quite a broad topic, and there's a lot of ways we can interpret how crystals might behave under these types of stimulation. So we thought we'd try to give a brief overview to quite a diverse range of speakers this morning, focusing on their sort of subcategories under this broader topic. So I hope we can do that a bit of justice in the next few minutes. So the first area where mechanical force is really coming into play in the world of organic materials is this area now of mechanochemistry. The idea that we can actually drive chemical and physical transformations using mechanical force. So in most of these mechanochemical transformations, if you're not familiar, we tend to take a powder or two powders dry. We mix them together in one of these ball milling devices. We can add a steel ball, and we simply shake it up and down really fast. And we hope that that mechanical force of the impact between the ball and the powder is enough to drive some transformation either within or between powders. And it turns out there's actually a lot of different devices we can use for this type of transformation. Some of them are things such as a twin screw extrusion, and as some of us will talk about over the next couple of days, this resonant acoustic mixing device. And so different types of mechanochemical reactors to try to drive the mechanical force in different ways. But mechanochemistry, particularly in the organic solid-state community, has really skyrocketed in the last couple of decades. And you can see that from just a quick overview, slightly out-of-date overview of the number of citations that are coming in for this world of mechanochemistry. And actually, a lot of that has to do with the fact that mechanochemistry is really a new dimension in this world of green and sustainable material synthesis and chemical synthesis. That is, when we're mixing our dry powders together in a mechanochemical reactor, we don't need to add solvent. And what that means is, of course, then our processes become much more environmentally friendly. But what's more than that, there's been a number of studies, this one's a little bit older now in 2014, done at trying to identify the energy consumption that's required to conduct a mechanochemical transformation. And so you can see quite clearly if we're doing this simple organic oxidation process by a number of conventional methods, and we actually require a lot more energy to drive the transformation than we would need by using a ball milling device or some other mechanochemical reactor. So not only are we looking at these processes in terms of less consumption of solvent, but we're also looking at them in terms of much reduced energy consumption. And now those two parameters, amongst others, have actually led the IUPAC to name mechanochemistry amongst the 10 chemical innovations that are going to change our world, really driving this new paradigm in green and sustainable synthesis. But you might be thinking that this sounds like a lot of hooey, that actually how are we going to actually drive chemistry? How are we going to be able to make materials and make molecules? And it turns out there's an enormous range of things that we can do using this mechanical force, an enormous range of materials and molecules that we can make. Now, it might seem somewhat counterintuitive, but actually one of the most, I think, shocking results is that we can make these massive porous solids, these extended solids like metal organic frameworks and others using mechanical force. There's a lot of work being done in organic synthesis, and we'll hear some of that, I think, this morning, looking at peptide synthesis using ball milling devices. But now what people are starting to think is we don't want to just do conventional chemistry in a ball mill or conventional material synthesis, but can we really push the boundaries of what we can do with mechanical force? And there's been some really interesting recent work done where we're actually able to make metastable or unstable intermediates in a ball milling device, such as a Grignard reagent, and use that in situ to drive chemistry forward. So now we're able to do a lot of chemistry in a ball milling device in a much easier way than we would have to do it in conventional solution chemistry. And others, including our speaker this morning, have also looked at trying to identify whether we can use the ball milling apparatus or other mechanochemical apparatus actually in the chemistry itself. And this has led to this development of this area very recently, the so-called mechanocatalysis. Can we use the balls, the metal of the milling balls, can we use the metal of the jar itself, and can we use that now to actually drive the chemistry forward? So really an exciting direction in mechanochemistry. So people are often asked, can mechanochemistry replace all of chemistry and all of material synthesis? And I think we're starting to push in the direction that probably we can, and if we haven't yet found a solution for it, it's probably just a matter of time before someone comes up with an innovation to do the chemistry and material synthesis in mechanical force. That said, mechanochemistry is very exciting for sure, but there's really a lot that we still need to learn about it. For example, we don't actually understand how it works. We don't really know when two particles come colliding together how the chemistry is happening. There's a lot of theories, including some very old theories, the so-called magma plasma model, where you have a meteor striking the surface of your Earth, and it's creating a high-energy plasma, and there's some chemistry happening. And a lot more benign mechanisms that have been proposed, particularly in organic solids. For example, looking at eutectics at the interface of our powders, so actually this so-called mechanochemical reaction might be happening in a melt. Or as we saw also with Helena's example the other day, the deliquescence at the interface between particles and actually the precipitation of your product from a solution phase. And there's also been a lot of work done recently in simulation, looking at trying to identify how the atoms are arranging at the interface of a collision between particles and looking at the formation of this amorphous intermediates. But sort of on top of trying to understand how these processes work, what we're also trying to do is understand a lot how can we begin to design these transformations. So there's a lot of interest now in what happens if we start to change the surrounding of our mechanochemical reactors, the material of the reactors, how does that affect our transformation? How do we control the kinetics and the outcome of our reactions, for example, by changing the milling ball, by changing the frequencies of our transformations, of the energy we're putting into our ball mill. And a lot of interest also in trying to understand how can we control the outcome of mechanochemical reactions by using additives. If we're going to add a small amount of liquid or a solid or a polymer, how can we use that really to direct the outcome of our transformation? And finally, one of the other big questions is how do we actually take this technology from the laboratory at some milligram scale into an industrial setting at a larger scale? How do we really use this to revolutionize technological processes? So there's been a lot of work recently also done in looking at how do we develop strategies to analyze and to monitor processes at scale, using different types of mechanochemical reactors to scale up to produce large amounts of material, and indeed looking towards using things like twin screw extrusion actually to drive mechanochemistry into a continuous processing platform. So with that, yes, mechanochemistry is really an exciting direction in the organic solid state community, but there's a lot of work that needs to be done in terms of trying to understand how these processes work and how we can control them. And I'm absolutely delighted to welcome Professor James Mack this morning, who I think will be a fantastic introduction to many of these challenges. And Professor Mack has done a lot of fundamental work in mechanochemistry, really trying to dig down into the details of how mechanochemical reactions are happening and trying to link some of the chemistry side, the thermodynamics of the chemistry, with the processing conditions in a ball mill, and really trying to push the boundaries of how we can understand how to control these transformations. So a really lovely lecture coming up, I'm sure. But the side of the mechanical control of crystals isn't just limited to our ability to drive synthesis, but also towards controlling the macroscopic properties of these materials. Now, we've seen a lot over the last couple of days in terms of the mechanically flexible crystals, so I won't dwell too much on that. But this morning in particular, focusing on the idea that the mechanical properties are also very important for the macroscopic bulk properties, for example, of the powder in generating the tablet formation. And this is really an important direction in understanding how our organic solids can be compacted, for example, in technological applications in the pharmaceutical industry. So again, I won't dwell too much on the flexible side of things. We've heard a lot about this, but again, these flexible crystals at the mechanical perturbation at the macroscopic scale is really very fascinating, both in terms of the geometries we can create out of these materials, but also the applications of these materials, for example, in directional polarization of light and in producing flexible nanowires and flexible electronic materials. But I think what's really important, particularly in this morning's session and in this community, is learning the fact that actually all of these mechanical properties, the mechanical behavior, all of this has a crystallographic origin. Perhaps not surprising, but we are still, I think, in the early stages of trying to figure out what that crystallographic origin is. And it goes beyond just the fact that our different crystallographic packings can give rise to different bulk single crystal properties, but actually that the crystallographic packing can have a significant influence on the bulk powder properties of our materials. So really there's a length of scale where we're needing to now understand where the design of our structures has to come into play in order to manipulate and design the mechanical properties across lengths of scale. And it's with that I can highlight two, I think, in my opinion, two big questions still in the field, and perhaps it's more than just two questions. But one of them really still is, how do we design at the atomic scale or at the molecular scale, how do we design this mechanical properties into our single crystals? And again, we've seen a lot of this work over the last couple of days. And I think in particular, looking towards this morning's lecture, how do we actually translate that understanding of the molecular design features and crystallographic design features through to the bulk single crystal properties, and finally into the bulk powder properties? Can we really use this now to guide the design of functional systems? And with that, I'm really delighted this morning to also introduce Professor Calvin Sun from the University of Minnesota, who's really been a pioneer at understanding how we can control particular tabletability in powders from a crystallographic origin, and has really done some fascinating, groundbreaking work now in trying to link the flexibility properties of our crystals towards their compaction. So looking forward to that this morning. And with that, I turn it over to my co-chair for the next.
So I'm Yuki Hagiwara in Japan at Waseda University. Thank you for giving opportunity of co-chairing Professor Namov. And let me introduce about photochemical solid-state reactions. Same as a mechanical-chemical reaction, the photochemical solid-state reaction is important for in terms of green chemistry and functional applications. The first example of the photochemical solid-state reaction is a transdynamic acid of the polymorph dependence 2+2 photoreactions. This transdynamic acid form the three polymorphs, alpha, beta, gamma form. All of this form, the molecules arranged in parallel. However, the distance was different, 3.5 angstrom and 3.9 angstrom and 4.7 angstrom. Interestingly, upon UV radiation to this polymorphs, in alpha form, these molecules underwent photodimerization and forming this dimer. In beta form, this molecules was also photodimerization and forming the different dimers as shown here. And in contrast, upon photoirradiation to this gamma form crystals, the molecules did not underwent photodimerization, and no photoproducts was generated. So the reason why is explained by the Professor Schmidt, as a reaction in the solid state occurs with a minimum amount of atomic and molecular movement. Therefore, after this finding, many photochemical solid-state reactions have been reported, and the empirical Schmidt rule have been decided for the activity of the 2+2 photodimerization. The two double bonds distance is closer to 4.2 angstrom, and the parallel packing of molecule in crystals exhibit photodimerization. As shown here, this molecule exhibits polymorph dependence 2+2 photodimerization in the solid state. In contrast, in solution, this molecule exhibits only photoisomerization tolerance to cis form, and therefore, compared to photoreaction in the solution, in the solid state, the photochemical solid state reaction have some advantage, as shown here. No requirements of solvent, high stereoselectivity and site selectivity, and controllable reactivity by crystal structure design. And then other photomechanical solid-state reactions have been developed in 50 or 60 years. For example, this Norris type 2 hydrogen abstraction is occurred with maintaining absolute asymmetry in the crystal. And this benzophenone molecules exhibit photocyclization with maintaining absolute asymmetry and maintain a crystalline state during the photocyclization. And then this molecule exhibits enantiomeric fragmentation and done as a solution. And then this molecule exhibits the oxygen transportation, oxygen transport to the specific site, as shown here. And then this molecule shows the rearrangement of chloride molecules, as shown here. Then recently, the photochemical solid-state reaction with functions have been developed, mainly focusing on two strategies. The first strategy is the crystal engineering approach. Professor Gabriel, today's presenter group, reported that by crystal engineering approach, that this crystal structure was controlled, and then the reactivity was changed. And then upon photoirradiation to this crystal, the molecules in the crystal underwent photodimerization, and then this crystal can exhibit selective uptake of host due to the generating cavity. The second approach is a molecular design change. These thymine derivatives arranged parallel in the crystal, and upon photoirradiation, these molecules underwent photopolymerization and generating the photopolymer. In contrast, these branched molecules underwent photodimerization in crystals. However, this molecule did not exhibit photopolymerization but formed tetramer. Therefore, by changing the crystal structure and the molecular structure, and then the reactivity and the function can be tuned. Other functions by photoirradiation of this 9-methyl anthracene crystals, this molecule underwent photodimerization in crystals homogeneously, and then the interference color in the crystal was changed under cross-Nichols. And very recently, this DVP crystal molecules underwent photopolymerization in this crystal heterogeneously heterogeneously. As shown in this movie, upon photoirradiation, the polymerization was occurred from the edge of the crystal, and then the molecule exhibited photopolymerization completely. Interestingly, this mechanism of the homogeneously photochemical reaction could be simulated based on the photosynergetic reactions. And then let me introduce today's presenter, Professor Gabriel. He's a professor of the Iowa University, and he's known to well known to the solid-state chemistry, and he published many interesting research, and this slide shows the recent publications as shown here. And then, same as the function of the as for the same function of the photochemical reaction in solid state, the photomechanical bending of crystals was also important because the microscale photoreaction induces a macroscopic deformation in the crystals. The first finding of the photomechanical bending of crystal is Professor this group in 1980s. After this finding, in 2009, Professor Ilia group and Professor Badin group simultaneously at the same time investigated the detail of the photomechanical bending of crystals, the terrace and anthracene crystals, respectively. So after this finding in 2007, the many typical photochromic crystals have been focused on the mechanical crystal development, and many photomechanical bending have been developed of the typical photochromic crystals, such as diaracene, azobenzene, salicylene aniline, anthracene, fulgide, rhodium dionite, ethionite, dibenzoyl nitroamine copper that's benzoxazole. And then, as a practical applications, the Professor Kobataki group have reported the electric circuit switch as using photomechanical bending of the photochromic crystals. Then, as same as the bending behavior, the jumping behavior is important and have been investigated all over the world, many. So this jumping behavior is divided into two phenomena: the thermosalient effect, jumping by heating, and photosalient, jumping by photoirradiation. The thermosalient effect is a well-known phenomenon that the first finding is that 1983, this pH crystal, and Professor Panda and Professor Naumov group investigated in detail of the mechanism. After the report, the many thermosalient crystals have been developed. And for practical applications, the fuses using salient crystals have been proposed as shown in this movie. And then, same as the thermosalient, the photosalient crystal have recently developed. So for this crystal exhibited both thermosalient and photosalient effect due to the upon heating and photoisomerization, respectively. And then this crystal exhibit photosalient effect by the photo-induced phase transition, and this crystal exhibit the same due to the photoisomerization. So today's presentation, let me explain. Professor Panda is an assistant professor of the University, and he was known for the mechanically responsive crystals by heat and light. And the final presenter is Dr. Manuel Fernandez. He's an associate professor in Witwatersrand University in Johannesburg. He will be talk about the hopping of transdynamic acid crystal by heat and light. So finally, let me introduce today's session contents. The first, Professor Meck and McGilvray will conduct this lecture, and then the coffee break. And after coffee break, Professor San, Panda, and Fernandez will provide a lecture. So this is the end of the session overview. Thank you for kind attention.
All right, so very happy to welcome Professor Mack to the stage for our first talk.
Okay. Thank you. This is different. So, good morning, and Panche, thank you for the invitation to come. When I came to visit you in NYU, Abu Dhabi, you said you must come to Macedonia, and you were exactly right. Just a wonderful time, wonderful trip. It was worth the 3-hour drive to come over. Thank you, Adam, for a wonderful introduction and really setting the stage for the mechanochemistry. And what I'm going to try to convince you today is that mechanochemistry is not different than anything you already know, a little bit different, but a lot of it is the same. And so when I started in this area, everyone thought about mechanochemistry as this magical, different thing, and people would say, well, it's not even real chemistry. You don't do real chemistry. I didn't even know what that meant because I could have swore we were making and breaking bonds. And I think a lot of times they were looking at, well, you don't put it in a flask, and that's what chemistry is. That's how we do chemistry. And I started reading Adam Grant, who's an organizational psychologist, in terms of how to get people to change their minds about different things. And one of the things that he talks about in his book, Thinks Again, is focus on what's similar to people, and then they can easily move over. If it's too wildly different, then it's like, nope, doesn't work, I don't believe it, and so on and so forth. And so what I'm going to focus on is what's the same about mechanochemical reactions versus what we would typically do in solution. So a brief overview is what I'll try to convince you of is many of the rules that govern a mechanochemical process is the same as the things that we already know. Kinetics work. So all the rules of kinetic pretty much work the same way that they do here. Thermodynamics also work. However, I'm going to show you a little bit about entropy. That's a little bit different possibly in these systems. And then I'm going to focus on some biomolecules, or one biomolecule in particular that we started getting interested in to see how that might work under mechanochemical conditions. So Adam said a little bit about mechanochemistry, so I'm going to go a little bit more. So typically, when most people run a chemical reaction, this is what you see. So you'll take reagents, you'll put them inside of a round bottom flask. You add solvent to break up the intermolecular reactions between the solvent to get the mixing to occur. You might heat, you might stir, or both. That causes the chemical reaction to occur. You remove the liquid, and then you get your product out. And as Adam articulated earlier, from a green chemistry perspective, a lot of people looked at this as a novel way to do chemistry from a mechanochemical condition, because then you don't have the solvent that you have to then get rid of. So you start with solids, you wind up with solids, and you skip the auxiliary in the middle. And that auxiliary represents a significant amount of the total amount of mass that one would use in a chemical reaction. Roughly around 80 to 85% of the mass that you would use for an active pharmaceutical is solvent, is pretty much used as an auxiliary. So the idea is if you can replace that auxiliary with something else that doesn't have such a detrimental effect to the environment, that might be a good thing. And so what we do instead is we take these reagents, we put it inside of a vial, inside of a milling machine, and there's various milling machines, and I'll talk about the one we specifically use. Shake it up, and then get the solids out. So pretty much the same process. The only thing is the solvent is being used to mix things together, and in this case, a ball is being used to mix things together. So very similar to what we already know and do. The equipment we specifically use is from the Specs company. It's a Specs mixer mill. The vials, we typically homegrown these vials, although there's other vials from Formtech that we use oftentimes. And we can make vials out of various materials. And as Adam talked about, sometimes, depending upon the type of chemical reaction we want to use, we'll choose a vial based on that. Most of the reactions you'll see with stainless steel, but we do some reactions with nickel and copper and some other materials as well. So let's see if I can play this video. Maybe. Okay, so that's about how fast it goes. If you look at real time, I would advise never to do this. This was done with the lid off, so the student risked life trying to get this video for you. So that's how fast it goes. If we slow it down a bit, then you should be able to see pretty much how the ball moves around in our system. So basically, if you can imagine, there's materials inside, the ball is crushing those materials all the way through. And so that's what that process looks like. So basically, everything we do is we take our material, open up a valve, put material in, put a ball in, put it in a machine, mill it for a set amount of time, and then that's pretty much it. So I said this chemistry is about the same as chemistry that we know already. So you have reagents, typically have to overcome some activation barrier. So there's an activation barrier in mechanochemical conditions, and you get to a product. If the difference in the reactants and the products if the product is lower than the reactant, then the reaction will proceed. If you can overcome the activation barrier, the reaction will proceed. very, very similar to what we already know. So now let's take a deeper dive into what we already know and let's look at some of the possibilities and some differences that are here. So if we want to look at from a kinetic standpoint, molecules must meet. They have to overcome an activation barrier. The temperature gives you the right amount of energy to overcome that activation barrier. And if you could do all of this, then the reaction proceeds pretty quickly. From a thermodynamic standpoint, a carbon-carbon bond is the same amount of energy in solution as it is in the solid state. So there's no magical difference about that. I'm going to talk about a little bit what the temperature differences may or may not be, but it's about the same as you would find in solution. And later on, I'm going to talk about this entropy term, where entropy might be a little bit different in this system. Here is where we find a major difference from a mechanochemical reaction in solution. I'm going to talk about that in a minute. And here is where we find that difference from a thermodynamic standpoint. I'm going to talk about that a little bit too. This is where the differences come. So the equation still works, but how we manipulate these two terms is what's going to be a little bit different for us. So there are also some other unique aspects that one can use. And so this is just an example of from Hugh Davies' work using carbenoids, using this silver triflate. If you have DCM, the carbenoid is so active it reacts with the DCM. If you remove the DCM, then you get the product that you desired. So then the solvent's not in the way. This was another example that was done where you typically get dimerizations in solution, but when we do this process without DCM, we get the desired product. So there's some differences that we do see in some of these reactions where the solvent actually plays a role. So then the question is can this work for anything? I do think we'll figure out conditions to make things work, but here's an example where dilution is actually pretty good. So if you wanted to do an enolate reaction, so you go through and you say, okay, here's an aldol condensation, we react together, or I want to do an enolate and I want to add an electrophile and I want to get this product, and so we can choose differences between those two products, and that's typically what happens. However, when you do it in a mechanochemical sense, if you do it in a stepwise process like this one is, the molecule doesn't know you're supposed to do aldol, you're supposed to do electrophilic substitution, and so it's going to prefer the aldol because it's going to do the aldol before you're able to add the second compound in. Or if you add everything in together, then the base becomes a nucleophile and you start getting these kind of reactions. However, if you have something that's sterically hindered, you can start making sterically hindered compounds in this way because the ball can just crush things together in a way that solution you can't get that kind of force behind it. So you can start making molecules that you typically can't make in solution. Today I'm going to focus on three areas. One is on energetics, second is on catalysis, and the last is this area of biomolecules, which we found pretty interesting and started looking at. So first I'm going to talk about energetics. So we wanted to look at where's the energy coming from in these reactions? How does this pretty much work? And what we decided to do was we needed a reporter inside of the vial to be able to really let us know what's going on. And we chose the Diels-Alder reaction for a number of reasons. The Diels-Alder reaction, pretty much if you have enough energy to do the reaction occurs. If you don't have enough energy, it doesn't. So now you can look at the energetics. The second thing is the transition state can be calculated pretty accurately by a number of different conditions. And so these were the different Diels-Alder reactions that we looked at and pursued with the idea that if we milled for a period of time at a certain speed, either we came over these barriers or we didn't. So we can actually say check or no. And we wanted a reaction that went to about 50% yield in about 3 hours, and this was the reaction that we selected. So that way we can go up and down depending upon the conditions that we change. So what you're seeing on this slide is all of those reactions, but now they're just points on a graph. And so these are all the different conditions we tried. So this is the number here is how fast we went, 15 hertz, 18 hertz, or 21 hertz. And then here is the material that was used, Teflon, steel, hardened steel, to see how hard the vial was and how much energy that would provide. And so what you're seeing on this dot right here is that all the conditions that we used went quantitative at 3 hours. And that was the one at roughly 9 kilocalories per mole. And so you see this one roughly around 12 kilocalories per mole. And now you're starting to see some differences, roughly around 13 kilocalories per mole, where depending upon how fast you go and where the vial hardness is, you can go from being quantitative to nothing at all. And so now you have some energetic differences that you're starting to see, and it starts going down as we get to higher activation barriers. And so no matter how fast we went, there were certain reactions that we couldn't overcome. And so we were puzzled by that, because if a lot of the energy was coming from the ball impacting, then we should start to see at least some of these things as we move to faster and faster speeds. And so we started looking at this a little bit more. And then we started to say, what happens if you change the temperature? So if you started changing the temperature, we started looking at reactions that didn't go before and started to go down. So then we started looking at maybe there's a thermal component as well as a milling component to these systems. And that's what we looked at. And so one of the things that we were able to do is say, well, how can we use this information that we could separate out the milling aspect from the temperature aspect, meaning that we can heat it up to a high temperature and then not move it at all, so then a reaction doesn't occur because nothing meets. Or we can cool it down to a low temperature and speed up the interaction, and so now the temperature is not controlling how fast things go. So normally in solution, if you cool things down, molecules move slower. If you heat things up, molecules move faster. But now we have independent control over how high we heat and how fast we move, and that allows us to do some interesting things. So in this case, we looked at a very simple reaction, diastereoselectivity of T-butyl cyclohexanone with sodium borohydride. And basically what it allows us to do is change the stereochemistry because it gives us another dial to turn. So normally when we look at stereochemical reactions or enantioselectivity or diastereoselectivity, we look at temperature. And so this is the temperature dial here. And so you can go down through temperature. And as you go down through temperature, things increase. But now we have a speed dial. So now if we slow things down a little bit, we don't give as much energy. And so now we can get higher diastereoselectivities because we have a new knob to control that you typically don't have in solution. We could cool it down, and the rate of the reaction is dependent upon how fast we want to go. So we can make molecules go faster, 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 and that controls the rate of the reaction. So that's that A term that we typically use. In solution, you don't have a whole lot of control over the A term. What we typically do is if we cut the amount of solvent in half, then we'll say the molecules will meet twice as often. If we increase the amount of solvent, then they meet twice as less. And that's going to depend on solubility. If we cool things down, then molecules are typically less soluble, which means you have to add more solvent, which means rate typically goes down. But now if we don't have a solvent and we can control the rate, we could do very fast things. And we have total control over that. So we looked at a lot of different reactions. So this is an SNAR reaction. We wanted to see how this plays out in terms of these rates. And so here you have a situation where we're looking at mechanochemical conditions versus the same reaction in DMF at various temperatures. And you can see the mechanochemical reaction is typically faster, and on average is about 9 times faster, what you see in solution. And so here again, basically the rate enhancement is coming from manipulation of that A term. So that's a term that we're able to control. So Adam also talked about scale up. This is something that's been in the community for a long period of time. How would you scale these reactions up? And so one process that we think is pretty good is a twin screw extruder. And this is an example of a twin screw extruder. Basically, there's 2 barrels with a bunch of different screws, and so the material can be fed on the inside and then go down the barrel, and you can see it coming out there in a solid form. So solids in, solids out in that case. Let's see if this video will play for me. So this is our extruder. So basically we're just showing we had 2 white solids coming in, and so here's the product coming out, and so that's scale up. And it's a flow reaction and process, so you could use kilograms per hour moving out of this type of system. So then the question became is, can you take the R&D aspect of the mill on small scale and then scale up in some way? Is there a translation that occurs? And the answer is there is a translation that occurs. And so we took this reaction that we've looked at before, and we did it on pretty much R&D scale. This is different temperatures we looked at, and this is the rate of the reaction at those temperatures. And then we want to translate it to an extruder. So these are different conditions that we use to translate it to see how things work through. And basically, our conditions worked out. So whatever we saw in small scale on the mill, we can use those conditions to go to larger scale. So what you're looking at here is 3 runs on the extruder going through. So you could see that the time and the amount of yield depending upon the temperature is pretty consistent all the way through. And this is the average of them all. So this is what we found in the extruder, and then this is what we found in the mill. And you can see at some point, they work out to be the same, but also at some point, the extruder actually works a little bit better. And that's the different kinds of shearing and compression forces that happens in the mill versus the twin screw extruder. And so we looked at a different reaction to make sure that this was applicable into more than just one reaction, and we see the same type of trend here. So a lot of times what we can do is take a small scale and use a ball mill, and then scale up those conditions to an extruder. And they make extruders of various different sizes. So that's a little bit about the energetics of the process. So now I'm going to switch to catalysis. So we've been looking at what's called direct mechanical catalysis for a period of time. And so this is a report from the Borchardt group. We looked at nickel, we looked at copper, we looked at a lot of different things, but they started looking at palladium. And started making polymers with palladium, using palladium powder, and then they had palladium-coated balls. And they were able to do these catalysts, and more recently, they published on a Suzuki reaction, which is something we were working on as well, and I'll show you in a minute, where they take these palladium balls in a plastic jar to do these catalytic reactions that are pretty unique. So we started looking at the Shonagashira reaction instead of Suzuki reaction. We looked at this reaction in the past. And so if you take palladium tetrachlorophosphine in these conditions, and we use a copper vial instead of copper iodide, we were able to do this reaction pretty easily. So we wanted to just use palladium powder, looking at what the Borchardt group did, and so we didn't see any reaction. And so we thought, well, maybe it only works for the Suzuki reaction. But maybe it gives us an opportunity to do something. And so one of the things that we wanted to look at is, what if we can organize material in the ball? And so if we added a system, how would this be? And the question really came down to, what does entropy look like in this system? And so we had 2 thoughts of what this might be. It could be a situation like this one, where a ball comes through and smashes everything, and everything falls into pieces and breaks apart. So that's, you would say, it's not entropically favored in that case. So that's one way to look at it. The other way was, what if it's more like a hammer and a nail? What if the ball organizes everything? So you have a nail and you have the hammer, and now you're forcing the nail into the piece of wood. So now entropy is on your side in that case. So what does this look like, and can we manipulate this system in our favor? And so if you look at catalysis, really what you want is the active catalyst, but what typically people buy is the pre-catalyst. So people will purchase the pre-catalyst so it can fall apart in solution to make the active catalyst, and then that's how you get your catalytic reaction to occur. So it's a lot of difficulty with catalysis because you want something that is reactive enough to do the chemistry, but you don't want something too reactive that you can't isolate it. So our thought was, maybe we don't need to isolate it. Maybe the ball can organize all of the pieces together in situ, and then we don't have to worry about ordering a catalyst, has stability, or anything else. And so that was the idea. So typically you would take a pre-catalyst, you make the active catalyst, it would react with your reagents, and you go through, and that's how you get this catalytic cycle. And if you look at the price, so if you look at palladium tetrachlorophosphine, you look at the price per gram, If you just add the palladium and triphenylphosphine, it's a little bit cheaper, so you pay a lot of money to organize things together. So if the ball can organize things together, it'd be easier, cheaper for you to do that type of chemistry. So that was the idea. So we started looking at, what if we take palladium, triphenylphosphine, our reagents, our copper vial, put everything together in a system? Can we get the Sonneger-Shearer reaction to go that way? And so that's what we did. And so we started looking at this reaction. So we used cesium carbonate, palladium, triphenylphosphine, our copper ball, 3 hours. And we looked at different temperatures. And if you get to 90 degrees, that's when the reaction pretty much goes quantitatively. And we could do it for a lot of different substrates. So it worked out really well. We also started looking at, can you recycle the palladium? So since you have this catalyst and it doesn't go anywhere, can you recycle it? And the answer is you can. So we started with a lot of palladium early on, and then we started cutting the palladium down until we got to the point where we didn't add any more palladium. We still started a reaction going through. And that's because after a period of time, the palladium kind of got wedged into the copper vial. And so now you got a pretty much ready-made catalyst over a period of time that you didn't have to add any more material into. However, it does diminish over a period of time. So you can get about 2 or 3 runs out of it. So we started just saying, well, let's just add 5 mole percent to the mixture, and that'll be what we do. The other thing we can do is, instead of buying multiple palladium catalysts, we could just do ligand screening. So we don't have to use triphenylphosphine as a ligand. We can use whatever ligand we want. So we do the same screening an organometallic chemist would use. And so we didn't have a whole lot of success with bromide, but when we switched to a different ligand, then the bromide went through no problem. And so now we started looking at, well, now we can have some selectivity. So if you take iodo-bromo benzene and we do Sonneger-Shearer with triphenylphosphine, then the iodide can go. And then if we switch to this tri-T-butyl phosphine, then the bromide could go. And so now we could get mixed Sonneger-Shearer kind of coupling. So as I said, we started looking at Suzuki reaction in this pathway. If we use just palladium Chesterkiss triphenylphosphine, it takes a long period of time, but we can get there. If we just had palladium the way that the Borchardt group did it, we didn't see a whole lot. But if we heated the reaction up to 90 degrees, then we started to see more. So we had to get over that activation barrier to do the chemistry. And Adam had a slide on there that talked about different types of mills. So different types of mills has different energetics associated with it. And so there's a mill called a planetary mill, and a planetary mill has a bunch of balls in it and use friction grinding, and temperatures can be really, really hot. And so this was an example of a Suzuki reaction using a planetary mill. And notice that the yields didn't start to really come in until they went to about 300 revolutions per minute, which is pretty fast. So if you go slower than that, then the reaction doesn't work very well. There's a different article that kind of measured what the temperature of these different mills were. And if you go through these conditions, they went for roughly around 30 minutes. You can see that mill gets to roughly around 150 degrees in that time period. So we use that, and instead of going 17 hours, we just heat it up to 150 degrees in a half an hour, and then we start to see these reactions go. So we can start taking conditions from different mills and use and kind of tune things and take what someone else did and look at what we did. So here we looked at heat is pretty important. Ligands is dependent on the reaction, but we can switch ligands out. I didn't talk much about bases, but there's some base choices that one has to make, and then we could do some chemoselective reactions. So the last thing I'm going to talk about is the mechanochemistry of biomolecules, was something we just started. Had a student who was interested in joining my lab, but was like, but I'm really interested in biochemistry. I was like, I don't do biochemistry, but I really want to work with you. So we collaborated. We made that work. So we learned a whole lot about the mechanochemistry of biomolecules. And the idea here is really going back to energetics. So if you go back to this, what we learned from these organic reactions, or the Diels-Alder reaction, it was the thermal component that took over. So then the question became is there no energy coming from the ball itself? And it was like, well, there has to be some energy coming from the ball. Maybe not enough to do a Diels-Alder reaction or some other reactions, but how can we determine how much energy is coming from the ball specifically, and when does that matter? And so we started thinking about molecules, and so, low amount of energy is conformations. But who cares about conformations of organic molecules? So if cyclohexane's in a boat or a chair, if I can make the ball move it from a boat to a chair, I don't think anybody would care. But biomolecules, the conformation does matter. So people do get excited about those conformations. And so we started looking at that because that should be less than 9 kilocalories per mole. Remember, the lowest reaction we looked at was about 9 kcal per mole. And so we need to go lower than that. So stress on proteins are important, and there's a lot of things that come through. So there's chemical modifications that one can do, but there's also physical modifications that you can do as well, whether through thermally or through force that people have looked at. And so people do want to understand what the mechanical stimuli are in proteins, and typically what people do, and I've actually seen this device once, is they put a subject into pretty much what looks like a guillotine, and then they take a ball and they drop it at different heights, and then they extract out the cells and then see if there was anything happening to the protein. The mouse does not make it through that process. And so we thought, well, if you really just want to look at the proteins, why can't we just mill the protein and then save the mouse? And so that's what we typically do. The protein that we used in this situation was a T1 RNase. It pretty much cleaves RNA at the G and the C areas. And so it's a well-known protein with one alpha helix and a beta sheet on it. And so the experimental design here was we wanted to look at primary structure through MALDI, see if we were making and breaking bonds by this milling process. And we wanted to go through a secondary process to look at the secondary structure to see, and we did that by CD. So let's look at the primary structure first. In the primary structure, what we noticed is there's no change in the primary structure. So whether you had the standard, which was the no milling, all the way down to 23 hertz, we never broke any bonds, or we didn't see any evidence of breaking bonds in that case. So we were all good there. So then we started looking at the secondary structure. So on the right side is what's looking at is the thermal denaturation, and that's been done in the literature many, many years before. This is our recreation of that by CD. And so here is just ambient temperatures, physiological temperatures, and below. And so this is typically what that CD should look like. And at roughly around 55 degrees, you start seeing a breakdown of the alpha helix region as well as the beta sheet region. So the alpha helix region is roughly between 190 and 200, and this beta sheet region is between 205 and 215. This was done with the sample directly in the CD, and you're heating it while it's in the CD so you can look at it in real time. So this is our mechanochemical approach to it. So this is not milled at all. So that's this blue trace right here. So that mimics what's going on there. And what you start to see is there's some differences here. So in this region, the alpha helix doesn't seem to be as responsive to the milling as the beta sheet version is. And so here is where you start to see some nuanced differences. So again, this is 0, and then you're going to 8 hertz, 11 hertz, 12 hertz, and then right around here, things pretty much don't change as you mill continuously at that point. So again, 8 hertz is roughly around the same as 0, but then you start to see some changes right here, and this is where things don't change. So then we started to look at what happens to the function of it. Does it still do the same thing it was programmed to do by Mother Nature? And so here we had this 31-mer RNA sequence, and it should clip at every GC unit or every gene unit. And if it does what it's supposed to do, these are the masses you should see by GC and by MALDI, and this is the sequence that you'll get out. And so if you take the same RNA 31-mer And so here's the unmilled protein, and so you see exactly what you're supposed to see. When you get to 8 hertz, still see exactly what you're supposed to see, so the molecule is still doing what it is. But when you get to that 11 hertz, and that's what you saw on the previous slide, that's when things start to change a little bit. Now you're starting to see some cleavages that don't occur. So now we're not able to observe these cleavages anymore, but we are able to observe some cleavages on the end, and that's consistent all the way through. So if I go back a little bit, just to remind you that at some point in time, nothing changes about the protein, and we see that in the function as well. So then we started to look at miscleavages. Okay, so now it's not functioning the way it normally did, but does it do something different than it did before? And so if you look at the unmilled protein, nope, cleaves exactly where it's supposed to. If you look at the 8 hertz, that cleaves exactly where it's supposed to. But now 11 and beyond starts miscleaving at the same spots. And so these become the sequences that you typically don't see in the unmilled version. So then we started to look at, well, what's going on in this system? And what we started to realize is that maybe these beta sheets, which typically is the less robust of the two, the alpha helix is typically more robust than the beta sheet, takes less energy to break this up. Maybe we're destroying the pocket a bit, and so now the molecule can't fit in the way it's designed to. The other thing that we think is going on, and I'll go back just one to look at the sequence to point something out. Let me go back another one. This sequence, it's the parts of the middle that are not being cleaved anymore. And so what we think is we're crushing that pocket a little bit. And so now at the middle part of the RNA, it can't fit. The end part can still wedge itself in there. And so that's why we see consistency on the ends. But in the middle, that's where we think things are not functioning the way it is. It's not docking appropriately because we don't think the pocket is where it needs to be. So you start looking at the active site and where things should be kind of crushed, if you will. And so these are what the active site looks like, and these are the proteins that would be manipulated in that active site. And so we think there's the P site region is the one that's being manipulated, but there's some more work to do on that. So conclusions on this one, there's no disruption to the primary structure. There is disruption to the secondary structure. One of the things that I want to mention that I didn't mention before, when I talked about the thermal denaturation, I said it was inside the CD, and that's what you're looking at. If you remove it from the CD, the protein actually goes back to its native state. That's what it tries to get back to where it was. When we do our milling system, we took it out of the mill and then took it to the CD. It was enough time for the protein to go back to its native state, but we put it in some situation that it can't get back there. If we heat the protein up, it can get back there, but just by milling alone, we put it in some new conformation that it just can't get itself out of without an additional energy. So that was another interesting aspect. If you mill at 12 or higher, it causes some very specific changes to the protein, and then it starts miscleaving at certain spots. And so with that, I'll acknowledge all the people that worked on this project and my collaborators in funding, and thank you for your attention. I'd be happy to take any questions.
Yep, great. Thank you very much, James, for a very stimulating lecture this morning. We've still got time for some questions.
Kevin Roberts, University of Leeds. Lovely talk. I enjoyed that. I was kind of two related questions about interfaces, really. So in a mill, you bring the surfaces of materials closely together. And it seems to be that there's a kind of pre-design you could do in terms of looking at the crystal chemistry of the reacting species. And you can see from just examining them how they will fracture. You can easily locate slip planes from molecular modeling, and that might get, and then when you look at that, you see the functional groups that are exposed. And so I wonder whether that's something, I mean, the first thing is to go back and maybe commend the work, because moving to solvent-free chemical reactions is obviously fabulous for sustainability. Why would you not want to do it? And I totally agree with the vision of what you're doing. But I wondered if you could take it a bit further and start to know your reactants better. And the other thing that came back, it reminds me of work that Bill Jones's team did on making co-crystals with grinding. And this observation that a small dab of solvent, usually something with no solubility, greatly improve the efficacy of the reaction. Just thoughts.
Yep, absolutely. I think, so I'll take the second one first. Liquid assistant grinding is something that a lot of people in the community use, and it's not something that it's a solubility. So we're still trying to figure out, how does that work? Does the solvent or liquid help bring things together through intermolecular forces in a different way than we typically see in solution? Because depending upon the liquid you use, you can see different reactivities, and there are things that's not soluble in the liquid that you're using that causes it. So that's a phenomenal approach, and one that we're still trying to learn about. On the crystalline side, to really understand what's going on. So a lot of the materials we use, some of them are amorphous. We get them out of the jar, right? So sometimes they come amorphous, sometimes they come crystalline, so on and so forth. So we do have a colleague, and they work on crystals, and we did have this idea about how we can work together. The challenge with that is they work so hard to make the crystal, and then we destroy the crystal. And that relationship is not one that works a lot, because the other person has to be equally committed to the idea as we are. And typically that hasn't happened yet, because it's easy for us to destroy what you all make. It's really hard for you to make good quality X-ray crystals and then go, okay, I'm going to take it and destroy it, and then we're going to figure out what this chemistry. And it's going to be multiple times, because we're going to have to do this a lot for us to get the details. So I'm looking for a collaborator who's willing, but haven't found that person yet.
Thank you, James, for a wonderful talk. Shamarki Mohammed, Khalifa University. I'm just wondering about the role of abrasion in ball milling, and also when you showed some slides on twin screw extrusion, you mentioned that there was some white powder that went in, but clearly white powder did not come out. To what extent is, in twin screw extrusion, you probably have some leftover powder from previous reactions. So how do you even go about cleaning that? And then in ball milling, what role do abrasion of the surface, either the ball or the jar, play in creating pathways which perhaps we're not aware of?
So that's a great question. There are two types of forces, and those forces are different. And so compression forces is what we typically use in our ball mill. So that's basically forcing things together, pressing them together. And then the extrusion is typically shear forces. So you would go through and you're shearing things together. And so I didn't spend a whole lot of time on this slide with the extruder, but all of these screw elements is a rotation. And you could design the screw elements so that you can choose the type of abrasion you want in a certain area. So some of them are 90 degrees, some of them 45 degrees, some of them 60 degrees, some of them reverse, some have kneadings, all different types. And so, and conveying, and so here is all the different mixing sections in the screw elements and how many of these screw elements. So this R60 is a 60 degree, and there's 4 of them. And then you would say there's a 30 degree element, and there's 4 of those, and then another 60 degree element. And so these are the mixing sections going through, and then you would convey material or change it through, and then the torque changes are occurring due to the fact of how much torque is going through. So you're exactly right. We can design that piece of it to say, okay, I need a little bit more here, a little less there, and it's material dependent. So some material is affected by shearing, some of them are not, and so you can make these adjustments. So we had to kind of optimize this aspect. The second part is in terms of how do you get the stuff out of the extruder. There's 2 ways to do it. There's the hard way and the hard way. So the first hard way is you take all the screws apart and you scrub it down, and you get all the material off it, and that's what you do. The second hard way, which actually is not that hard, but harder than just cleaning a round bottom flask, there's something called isomelt. It's a pretty easy thing. You get it from Amazon. It's sort of like a sugar, but it goes in solid. You could heat it up, and then it liquefies. So you can liquefy things all the way through, and it just pushes everything out. So now you got the isomalt stuck in the extruder, but that's water soluble. So now you can flush that out, and so now you have pretty much a clean slate, but you still got to go back in and do some other cleaning to it. So I would say the students hate it because that's the hard part. It's cool coming out. Oh my God, you can look at it, whatever. The cleaning part is, it's like cooking, I guess. You make the big meal, but then you got to clean the kitchen at some point. So that's the hard part.
Do you know how much pressure you're generating?
So there are a lot of people looking at that aspect as well, and it's hard to know. So there's been calculations on the amount of pressure that's generated. We don't actually know because the key for us is how much of that pressure is actually being translated to the molecule versus dissipated to the wall and other places. And so it's hard for us, but we're working with a group at Texas A&M where they're looking at pressure in contacts, and so we're working with engineers to say, okay, if I hit it for this amount of time, how much is transferred, how much is not transferred? And for us, we really don't know. So it's because of the transfer, I would hate to guess. People have done calculations, and we've done some calculations too, but it's really how much energy is transferred to the material. So that's why we did the Diels-Alder reaction, because we needed a reporter inside that was responsive to everything that we're doing. And same thing with the protein. The protein is the closest thing, but then my biochemical partners are saying, well, now the size of the protein matters. So then you don't know how big this protein is versus another one. So we're looking at BSA as another protein. And so there's a lot of changes for me to say a guess.
So I think we'll just
hello.
take this one last question, and then I will ask for everyone else to pass to the coffee break.
Hi, Tomislav Stolar from Ruđer Bošković Institute. Thank you, Professor Mack, for a wonderful lecture. I didn't fully get what your conclusion was when you explored the entropy effect. Was it the smashing or nail and hammer? So would you please comment on that?
So we think it's the nail and hammer. So we think that we can take metal, a ligand, substrates, and if the ball is the hammer, force the nail all together in the wood so you could get that chemical reaction to occur. So it's not smashing things into a million different pieces all over the place. It's actually organizing compounds. And the ultimate goal for us is we think we could take reactions that are typically endergonic in solution because of the change in the entropy term, make them exergonic in the mill.
Excellent. Thank you again, James, for a stimulating start to the morning. If you'll join me in giving a round of applause once more. And then I think we invite our next speaker, Professor McGillivray, for the next lecture.
Okay, so good morning, everybody. I think we're good. All right, so again, I'd like to thank the Panche and his team for providing the opportunity for all of us to be here. Can everybody hear me pretty well? Okay, and what I should also say is that the social program is quite outstanding, and I thank you for that as well. So I'll still try to do my best to convey the work that we're doing in my group. So what I would like to talk about today is the work that we've been doing in my group to develop work to allow organic solid-state chemists to basically try to build molecules and crystals. And we think that there's an outstanding opportunity for organic solid-state chemists, maybe more specifically crystal engineers, to make an impact on the field of organic chemistry. One of the exciting things about how we do things as crystal engineers is that we really think differently about molecules. And we can also think differently about how they can react to create new structures. And so hopefully I'll be able to convey to you that we can do that in exciting ways to create actual products that organic synthetic chemists can't even imagine, okay? And I really think that we're sort of at the very beginning in terms of going forward with these ideas. So to start, I wanted to start where Craig Eckhart kind of left off in terms of looking at historical aspects of organic solid-state chemistry. And I wanted to start with a quote, which is also sort of tucked into the history of organic solid-state chemistry. That's by Gerhard Schmidt. And so if you go to the literature, Schmidt published a paper in Pure and Applied Chemistry, 1971. And there's a comment in there. I strongly recommend to all crystal engineers to go back and read some of the later papers by Schmidt in terms of topochemistry. And what he said, so this is the classic illustration of the reactivity of cinnamic acid. And the exciting thing, if you're an organic synthetic chemist, is that this reaction occurs in a crystal, of course, to create covalent bonds. And covalent bonds are the glue, as we just saw by the talk by James of organic synthetic chemists. So in this reaction, of course, we use light. There'll be other talks that'll describe how you can do reactions in crystals thermally, and we've seen a lot of that as well. But what Schmidt said is that given the observation that if you have alkenes and they're separated by the order of 4 angstroms, and given that they'll undergo this cycloaddition reaction, one might want to construct crystals in which that distance is predictably achieved. Okay, so this is basically the concept of crystal engineering. But you'd want to do that for as large a class of unsaturated compounds as possible. Okay? So we're going to make covalent bonds in crystals, and how can we go about this in a very general way? That's the general idea here. And doing so by means of a simple chemical modification. So here's the concept of efficiency related to sustainability, green chemistry, and so on, without affecting that reaction would be a desirable goal. Okay? So as crystal engineers, over the decades, there has been tremendous effort to do this. And there are many examples in which you can achieve this reaction by modifying reactants. But I would also ask the question, is if you're going to do this, for what purpose? Okay? So, you want to create crystals that are reactive, but what is the next step? Okay, why would you want to do this in achieving these reactions? And as we've seen from this conference, in the field of crystal engineering, there are many, many different things that we like to do in terms of engineering solids. So there are applications such as energy capture and storage, pharmaceutics, we'll see some more of that a little bit later, catalysis and separations, electronic media for flexible displays, and all of these areas generally have a goal, okay? So we want to make an organic crystal that exhibits minimal resistivity for electronics. We want to make an organic crystal that exhibits interesting solubility for bioavailability purposes, and so on and so forth. But when it comes to controlling reactions in crystals, what is the purpose, okay, to be able to make covalent bonds? We know that we can achieve reactions in crystals, and those reactions give rise to very interesting properties. We saw a lot related to here and here over the last few days. But how does that apply to a field such as organic chemistry? And so this is a slide which kind of philosophically represents how we, in my group, kind of feel from time to time. Okay, so on the left is our organic solid-state chemistry. So we're used to concepts such as single crystal reactions, flexible materials, pharmaceutics, electronics, all kinds of properties you could design to make crystals. And on the other side, there's the field of organic synthetic chemistry. And in organic synthetic chemistry, there are many different concepts that are utilized in the liquid phase, such as homology, stereochemistry. But organic synthetic chemists do a lot of other very different things, right? They actually make molecules by design. So they sit down, plan out a synthesis, and create a particular target that'll be of use for a downstream application. So I would argue that what Schmidt was indicating in his paper is that one would want to apply this reaction to a large, broad molecules for the purpose of doing the kinds of things that organic synthetic chemists like to do. And that is make natural products, make targets. What do targets look like that crystal engineers can create? This is what I mean by tremendous opportunity. We think very differently compared to liquid phase organic chemists. We use crystallography to study how molecules are associated in crystals in very unique geometries, and we have an opportunity to capture those geometries to actually create some useful products. So oftentimes, one might feel there's this huge area of organic synthetic chemistry that's sitting alongside of crystal engineers, and we still have to work on recognizing these opportunities, but we still have to try to bridge to a different kind of language that organic synthetic chemists use in the liquid phase. And so if you step back and think about the concept of using crystals, crystal engineers, as organic laboratories, okay, then again, we know we can do stereo-controlled reactions. That's pretty straightforward. Crystals are homogeneous, so I argue we can expect quantitative yields routinely when we make our products. We saw green chemistry. There's novel chemical space that we can explore, and there's certainly a need for novel chemical space to be explored by synthetic chemists. Arguably, the liquid phase, despite being so vast in opportunity, still can be limited in terms of the products that you can create. The products that we make can have unique applications, and as we saw yesterday, there's the issue of planetary science. So through discoveries that are going to take place for decades, there may be forms of organic chemistry that we're not even aware of yet, which could be directly connected to the kinds of things that we're doing as solid-state chemists. So there is a need to map reactivity in chemical space in terms of crystal engineering. And then, as we've seen, there are various properties that you can develop, such as displays, high-density storage. The area of molecular machines is also related to reactions in crystals and so on. So this is very exciting, and what has been the fundamental problem, and this goes back to what Schmidt has also mentioned in his work. And so what Schmidt has mentioned is that the rule of homology, okay, and we're all aware of this, but the rule of homology, which is essential to development of a liquid phase chemistry, so you make very subtle changes to molecular structure, is not necessarily applicable to crystals, of course, because small changes to molecular structure can lead to vast changes in crystal structure, and then generalizations of one or two examples can be very highly misleading, as we all know. So that's the problem, of course, is crystal packing. We've seen this comment a number of times. We're used to this one. A crystal is a chemical cemetery. Molecules go to crystals not to live, right? But actually they can live. They can undergo dynamics. And as we've seen, we know crystals are flexible and they're soft. So there's enough motion in a crystal for us to take advantage of to have molecules to react. So what we've been doing in my group is trying to address crystal packing problems, the psychological problem, and embrace the flexibility to think about what kinds of products that we can make in crystals that would excite solution phase organic chemists. And what we've been doing is we're basically using molecules to build molecules in crystals through applications of co-crystals. So in our original work, what we showed is that you can take a molecule, such as resorcinol, and then co-crystallize it with a reactant that interacts with the reactant by hydrogen bonding here. And the key here is to get this discrete structure whereby the reactivity is programmed independent, largely, of packing. And I think Craig mentioned this or referred to this a little bit in your talk. And by doing so, we isolate the reactivity. In this case, we shine light and we get the corresponding tetrapyridyl cyclobutane in quantitative yield. So we get the single product, that's good. Quantitative yield, that's good. We can do this on the gram scale. And we've also used mechanochemistry to form these co-crystals. And there are many examples now in which you can do, make binary co-crystals to control reactions. But the key here is that, in a sense, this is our little laboratory, our little discrete unit that we can manipulate to potentially make things that excite organic synthetic chemists. So what we've been doing in my group is when we start to build molecules, we begin to ask questions such as, what is the tolerance of the self-assembly process to various non-covalent bonding? So we've been looking at halogen bonding, metal coordination, the example that we saw earlier, boron-nitrogen bonding to achieve the reactions. Once we're here, we begin to ask, what kinds of targets can we make? So this is our laboratory. How do we expand this laboratory to make molecules that, what organic chemists do all the time? They make these targets. And there are a number of elements of green chemistry that are related to this co-crystallization, which I won't get into, but I'll address as we go along. And then finally, we kind of embrace what Schmidt had mentioned by thinking about how can we use these products for various applications. So we want to create some distance between just the reactive crystal and make use of these products for a particular purpose. I cannot claim that we're there yet. There's I still think personally it's very early for us in that regard. So what we've been doing in terms of the targets is we've been trying to modify the laboratory to make some interesting molecules. And here is some examples of the first targets that we made. So we put it on our crystal engineering hat and then our organic synthetic chemistry hat, which arguably didn't even exist because our training was mostly as crystal engineers versus organic synthetic chemists. So we wanted to try to make something that would be of interest to the liquid phase community. And so the first target that we made was this molecule here. So we said, how do we modify the self-assembly process in a way that creates something that resembles something you get in the liquid phase? And that something that we made is a paracyclophane, in which we programmed the self-assembly to involve 2 double bonds. Now, I'm sure we're aware that it's extremely difficult to expect 4 molecules to self-assemble by weak OHN hydrogen bonds in the liquid phase, okay? Solvent effects are very, very detrimental to hydrogen bonding in solution. Co-crystal provides this quantitatively. We have 100% of molecules stacked and ready to react through co-crystallization. That's powerful versus the liquid phase. And so when we shine light on this crystal, this is work by Tomislav Friščić, who's currently at McGill. I believe he's moving to Birmingham soon. And he showed that we can make the paracyclophane quantitatively with no side products. And then later, we show that you can make molecules known as lateranes, in which you have a string of double and single bonds lined up at a row to form polycyclobutane structures. And I'll get into that in a minute in terms of their potential applications. So I wanted to focus just somewhat briefly on the nuts and bolts of making paracyclophanes in related structures. And so Craig and I have been talking the last few days about organic solid-state chemistry, the history, and it was a discussion that Craig and I had, I'm not exactly sure of the year, I think it was 2006 in Iowa City. And I told Craig that we were able to make the paracyclophane at 100% yield. And what you would think, rightly so, is that we used resorcinol to do that. Okay, that's what I show here. But in fact, we did not just use resorcinol. What we do in our lab is we screen, as James was mentioning, various template molecules. Resorcinols are commercially available in gram quantities. And what we discovered is that it was benzyl resorcinol that functions as a template for us to create the paracyclophane in 100% yield. I said, Craig, you know, we just have to change the R group, and eventually we're going to get to 100%. I'm convinced. And Craig said, well, you know what? That group is acting like a molecular cushion in the solid state. So here's the benzyl group. What it's doing structurally is it's preventing any side reactions between the dienes, plus it's allowing us to program some mechanochemical molecular type response, in my opinion, that modifies the bulk properties of this co-crystal to allow these double bonds to react quantitatively. Okay? And so this is a very different rule versus solution phase organic chemistry, changing R groups to achieve 100% yield. So this is what crystal engineers have to offer to liquid phase chemists. And we were also interested in making the other isomers of and we call this process template switching. It's probably not the best concept, but it's sort of a term we use in my lab. Let's just change the template to get to our product in 100% yield. And so we were also interested in making the corresponding ortho and metacyclophanes as well. This had never been done. creating a series, a homologous series of target molecules, such as these kinds of architectures. And what we discovered is that the chlororesorcinol allows you to make the orthocyclophane at 100% yield. But we can also make use of the chlororesorcinol to form what we call the XOXO orthocyclophane. I'm sorry, it's the XOXO is the conformation of that product, in which the cyclobutanes here are pointing into the board. So that's one stereoisomer. What we didn't expect is that we could make the other stereoisomer, which is the endoxo, in which now this cyclobutane is pointing out of the board towards us, also in 100% yield. And there we discovered that cyclohexylresorcinol allows us to create the other isomer. And why is that the case? Well, that template is somehow allowing us to control the conformation of the diene in the crystal. So this gets back to Aurora's talk about the importance of conformation in solid-state chemistry. By changing the resorcinol, we can change the actual stereochemistry of that product and provide an entry into the other isomer. And if you look at the crystal structure, this is familiar to this area. You have the olefins in a crisscross and a parallel orientation, and we don't know the reasoning why we eventually get these two isomers. Okay, there's a lot going on here, and this demands treatment through computational chemistry, but there's something going on in terms of the conformation and the packing that allows us to create those two products, which is good. I also mentioned the lateranes. So we made the 5-laterane using methoxyresorcinol, and at the time that we published the 5-laterane, there was actually a discovery in biochemistry on lateranes being present as natural products, which was nice for us. And so there's an anaerobic bacteria in the Pacific Ocean that is actually churning out these lipid laterane products. And so we're actually able to use a crystal to make a fragment that's present in this unusual natural product. And so I'll get, near the end of the talk, I'll address some of the work that we're doing to try to get to the naturally occurring laterane through the solid state. More recently, so to make the 5-laterane, we use a triene as a reactant. And dienes, trienes, tetraenes, they all come in different geometries and flavors as potential reactants. And very recently, we've shown that you can actually make cubane-like cages in the solid state as well. Okay? This is work by Peter Yates, around the same time as the work of Schmidt. And what was described here is that this molecule, it's a diene, so it's a cyclic diene, and Jorgensen, it undergoes a intermolecular photodimerization reaction to form a cubane-like structure. If you go back to the chemistry of cubanes, there's a history there in the liquid phase, but they're difficult to make. They're also controversial, but they're difficult to make. And in this paper, it was reported that the cubane forms in 30% yield, and that was it. There was nothing else published on this work since that time. Even the structure itself had not been authenticated using crystallography, which is an enormous surprise to us. So we went back to this system, and then we grew the crystals. The structure had been reported. It's right here. You can see that the dimethylpyrones adopt a head-to-tail geometry. We grew the crystals, beautiful octahedral type single crystals. And then we solved the structure of the cubane. It's right here. So it makes sense in terms of what was reported. And then the student, and this is not using hydrogen bond-directed co-crystallization, I realize that, but it's a representation of what else you can make in a crystal. But the student working on this project came up with the idea to make a binary co-crystal. And what he did is he co-crystallized dimethylpyrrone with this perone diacid. And he said he got a co-crystal. So we solved the structure, and it turns out the diacids themselves are stacked in this co-crystal. So this was trial and error. This was not designed, I must admit, but in this structure, the diacid's reactive, and the dimethyl perone sits in the crystal lattice to kind of support the binary co-crystal. And then we shine light, and now we got the corresponding multi-carboxylic acid as our product, also in 100% yield. So now we get the second cubane very quickly using a co-crystallization strategy. And so now if you look at the targets that we have been making in the solid state, now this is kind of a controversial slide, but like I said, the social program is outstanding, so you might as well put some interesting concepts on the board. Here is a demonstration of the products that we've made in a crystal to date, okay? And we've made 5-laterane, paracyclophanes, the various ortho and the metacyclophane, and the cubane. And so when you think about the work of Schmidt and sort of the call to do what organic synthetic chemists make, there of course is the book of Alice in Wonderland, Through the Looking Glass. And that is a situation in which you look through a mirror and you see an entry into sort of a strange, unusual world that's living in parallel. And so I think that these products that we've been able to fish out of the solid state and make is kind of like a glimpse into the kinds of things that, as crystal engineers, we can actually make in the solid state. And they're unusual. The rules are very different. We use cushions. We get unique products. We control conformation in unusual ways. We can expect quantitative yields. And I think there are many more products available that we can try to design as crystal engineers. And so we were fortunate to be able to have the work over the last few years also illustrated on the cover of the journals in which we published the work. So very recently, looking back to the work of Schmidt, what also became apparent is something so enormously simple. And that is a cyclobutane with 4 different groups, 4 different aryl groups, had not been made deliberately in a crystal. And so we created a challenge for ourselves to try to make a cyclobutane that has 4 different groups. And this would be the equivalent, in a sense, of a stereogenic carbon atom. Okay, a chiral molecule created with 4 different substituents. And given what we had learned, we thought we might be able to do this. Again, this is not the Resorcinol-based chemistry. But what we came up with is that we could make use of perfluorophenyl-phenyl interactions as well as unsymmetrical reactants to undergo a cross reaction to generate our cyclobutane with 4 groups. And it works. And so we've just recently published this work in which we designed I'll call it a stereogenic/chiral cyclobutane product. 100% yield, 1 product. The only problem right now is that we get a racemic mixture of the cyclobutane. But what we did here is we co-crystallized stilbazole, which we have in the lab, of course, from our resorcinol-based chemistry. And then we co-crystallize it with this stilbene that has 4 fluorine atoms and 5. So it's a 9-fluorinated stilbene. We get the co-crystal, which I'm not showing. We shine light, 100% yield to the chiral cyclobutane. And then here's the crystal structure of the corresponding salt with paratoluene sulfonic acid to confirm that we got the 4 different groups. No disorder, nothing along those lines in the reactant co-crystal. So as I mentioned, there are a lot of opportunities in terms of materials properties that one can take advantage of in terms of reactions. We'll probably see more of that later this afternoon in Alexei Tivanski's talk. Alexei and I have a collaboration in which Alexei utilizes AFM to study mechanical properties of these crystals and conductivity as well. But we've shown over the years that you can control various properties, or shall I say the properties change upon photoreaction. And one thing I would like to highlight is catalysis. So we saw in the last talk mechanochemical catalysis. We have shown that you can use this resorcinol system as a catalyst through grinding to facilitate the photodimerization reaction. And the way in which we do that is we use a vortex grinder. So this is an enormously inexpensive apparatus. We all have vortex grinders in our labs. They're in the corner somewhere, $9.99 on eBay. And so what we decided to do is literally just place the vortex grinder in the photoreactor and then shine light as we have we put some balls and BBs that we purchase at a sports store inside the sample vial to cause the mechanical force. And it works very nicely. So we showed, in this case, dichlororesorcinol acts as a template and a catalyst to form the tetrapyryl cyclobutane in 100% yield. And then we also applied this approach to the synthesis of metal organic framework as well to show that it's a little bit more general. And then Tomislav Friščić now sells a photo jar for applications of mechanochemistry. So you can go with the $9.99 version or much more expensive version, of course, if you'd like to do so. So it works pretty well. And then we've just recently shown that you can actually design a chemical cascade or a supramolecular cascade process. So here we use the product of a Diels-Alder reaction, the diacid, as a template for this reaction. But to get here, we used mechanochemistry to cause the Diels-Alder reaction and then generate the diacid, which then undergoes hydrolysis and then captures the bispyridylethylene in a co-crystal all in one pot. Shine light, and you also get your product in quantitative yield. So where are we at right now? So this is a summary, literally, of what we've been doing for the last 20 years. It's hard to believe that it's been such a period of time. So on the left here are the templates that we've developed. We've used halogen bonding as well, and we've also used metal organic chemistry. These are the substrates that we've studied in terms of the photodimerization process. And then here are the representations of the products that we've created. And this is a lot like what biology does. So in biology uses the same building blocks over and over again to create chemical complexity, i.e. amino acids. Here, we're using that simple Schmidt reaction using alkenes and using the same kinds of building blocks to generate complexity in a way that's it's biochemistry inspired as well. So for the last part, I wanted to address two things, and that is applications. So as I said, we're making molecules. We've got to make them for a purpose. And what we've shown, I'm sure you can imagine, all of these molecules we've created here are multi-topic. And so they are really primed to be used as ligands to make metal organic frameworks. It's a green approach to metal organic ligands for metal organic frameworks. And so over the years, we've shown that you can take the multipyridyl cyclobutanes and use them as building blocks to make porous structures. And very recently, we've actually used this to enlarge the cavity of a metal organic structure. So here is an example of where we take the bis-2, bis-4 pyridyl cyclobutane and use it as a product of a metal organic rhomboid. And so the challenge in my group was, let's make this bigger. Okay, let's make this cavity larger. But the rule is we could only use solid-state chemistry to do it, okay? Well, we could use little liquid phase chemistry to make the building blocks. But the rule was we're not allowed to do any kinds of liquid phase chemistry to get to this product. And so, of course, what we did is we made the corresponding alkene, then we co-crystallized it with various resorcinols, and in this case, we got a 1 to 2 stoichiometry. It's dichlororesorcinol, which we have an edge-to-face interaction, and the alkene's photostable. If you change the stoichiometry of the co-crystallization process, what happens is we got a 10-component assembly. Again, virtually impossible, in my opinion, to achieve in the liquid phase. This is photoreactive, and now here's the structure of the larger metal organic rhomboid, okay? So we can use the chemistry of co-crystallization as a way to enhance the properties of this targeted structure that we're trying to create, make it bigger. And then we've also have interests in pharmaceutical co-crystals. And this is just an unusual case in which we were studying 5-fluorouracil. And we've also discovered that 5-fluorouracil will undergo a photoreaction to form this cross product. And we're looking at that as a potential small molecule drug. Again, only made possible by organic solid-state chemistry, at least efficiently. And then finally, I believe, and I'm sure the literature shows, that there's a need to be able to post-modify products. So yes, we can make these diverse structures, but if you look at the structures, they're all lined with pyridyl groups, and pyridyl groups are somewhat benign, they're difficult to modify, and so on and so forth. And so it would be useful to somehow have an entry to be able to install various functional groups on the products. And I flip back from this slide here, but this is an example of by E.J. Corey, in which he performed a total synthesis of the naturally occurring laterane structure. And you'll note here the laterane that was formed in the liquid phase at that time relied on a nitrogen extrusion reaction, which was 6% overall yield, okay? The overall yield is 0.24%, which is actually not that bad in terms of natural products. But the tough part here was to get to the laterane. And then you install carbonyl groups and do simple Wittig chemistry to form the lipid structure. Now, more recently, Noah Burns at Stanford has done a more efficient synthesis, I must admit. And then Miguel Garcia-Garibay has shown that reactions in crystals can contribute to natural product syntheses. But we wanted to maintain what we do, but to be able to place various functional groups in a post-modifiable direction. And so one type of group we wanted to install were carboxylic acid groups. Here we were interested in co-crystallizing the resorcinol with this pyridyl acid. Didn't work, because you can imagine the pyridyl acid is very insoluble, very difficult to compete for hydrogen bonding. And so what we did instead is that we converted the acid to an ester, performed the co-crystallization, and then restored the acid groups in the product. So here we are, in a sense, installing carboxylic acids on the products. More recently, we've shown that you can post-modify the cyclobutane ring directly. So here we have carbonyl groups directly attached, just like what Corey was interested in, to the cyclobutane product through imine chemistry. So what we did here is we take 4-aminopyridine, make the imine, reverse the bond, and eventually get to the oxidized carbon, which is good. And then finally, what we've done just recently is we published a paper which we think provides a more broader entry into functionalized cyclobutanes. So again, here are the kinds of products we've been making. Here's the co-crystallization process. And what we wanted to do here is to create a handle on the alkenes that serves two purposes. Acts as a hydrogen bond acceptor, of the resourcenols. The resourcenols work really well. At the same time, we wanted a functional group that can be modified generally. So we needed to program the self-assembly process with these two parameters: modifiable to a diverse range of functional groups and sustain the self-assembly process. And so what we identified would be useful here are aryl nitriles. So here is the nitrile group. It's known to act as a hydrogen bond acceptor, but it's not really used to a great deal in crystal engineering. There are not many papers published on nitriles as hydrogen bond acceptors. But if you look to the field of organic chemistry, so on the other side of the fence, cyano groups can be converted into tetrazoles, acids, amines, amidines. So there's all kinds of scope here. As I mentioned, they can act as hydrogen bond acceptors. And so we co-crystallize this dicyanostilbene with a methoxy resorcinol, in this case, through our screening process. And we got the corresponding aryl cyclobutane. And here is the example in which we converted the tetracyanocyclobutane to a tetrazole. So we did what is essentially a click reaction on our product to create some added functional usage. And then we just published this work. It was published in Chemistry, a European journal, in which we're in a sense able to remove the cyano group and replace it with a different kind of functionality. So we want to try to create some more exciting products in this process, but we're very excited about the cyano group. So hopefully I've convinced you that organic crystals can be used kind of like laboratories to make molecules. And this is my current group, and then here are the list of students that have worked over the years. And then we've been very fortunate to have funding by the National Science Foundation. So thank you for your time, and I know it's close to coffee, so we can discuss it coffee or as part of the social agenda. So thank you.
So thank you for excellent talk. We have time for one or two quick questions.
Okay.
Oh yeah, thank you for the talk. It was just wanted to go back to the template switching.
Yeah.
So I think the example you gave was when you had the cyclohexane coming off of the ring, you were able to get the endo form.
Right.
Are you able to more generally relate those sort of substituents to the stereochemistry you're then going to get? So for example, if you had the cyclohexane again for a similar product or for a similar analyte, would you expect the endo as well? Or is it more just try everything and see what you get?
I don't have an answer to that question. So intuitively, I think it would require a different substituent. But I don't think we have enough examples to say that. There's another possibility, and that is once we take a step back and look at all the co-crystals we've made, it might be that there's certain structures that are being created over and over again in which a substituent might fit a certain structure type, right? But we're not there yet in terms of that level of prediction. And this is why I really think there's an opportunity for computational chemistry to really get into the details of how that group is affecting packing and disorder in the crystal. And potentially predict along those lines.
Hi, it's a nice talk. So could you please comment on the reversibility of this 2+2 cycloaddition, because some cycloadditions are reversible like 4+4 or thymine dimerization. But what about this 2+2?
The 2+2 is most definitely reversible. There actually been, I think there are 4 or 5 papers been published since about 2018 on the reversibility using metal organic chemistry. Now, I don't know if the metal is necessary for the reversibility. It might weaken the cyclobutane enough because of the interaction between the metal and the pyridyl, or acid or whatever's bound to the metal, to weaken it. For our system so far, all I can say is that the the diene that forms the 3-laterane, that one does reverse. We haven't described that in the literature. But if you let the laterane sit as the co-crystal, it does go back, okay? Thermally, presumably. But if you take the 3-laterane, if I remember correctly, as a pure compound, it's not as easily reversed. So there might be something about the co-crystal or the resorcinol being present in that lattice that allows it to do so as well.
So if you have more question, please ask and discuss during the coffee break. Now we're coffee break until 11:10, and the next speaker's presentation starts at 11:10. Okay.
Thank you. Okay.
You don't need a lonely night. Baby, I can make it right. You just got to let me try to give you what you want. You've been scared of love and what it did to you. You don't have to run. I know what you've been through. Just a simple touch and it can set you free. We don't have to rush when you're alone with me. I feel it coming. I feel it coming, baby. I feel it coming. I feel it coming, baby. I feel it coming. I feel it coming, baby. I feel it coming. I feel it coming. Feel it coming. Oh, I feel it coming. I feel it coming. Oh, I feel it coming.
Got a condo in Manhattan. Baby girl, let's head. You and your ass invited, so gonna get to clapping. So pop it for a Pam, pop it for me. Turn around and drop it for a Pam, drop it for me. I went to beach house in Miami. Wake up with no jammies. Lounge outside for dinner. Treat yourself, that's scammy. You got it if you want it, got it if you want it. Say you got it if you want it. Take my wallet if you want it now. Jump in the Cadillac, girl, let's put some miles on it. Anything you want, just to put a smile on it. You deserve it, baby, you deserve it all. And I'm gonna give it to you. Gold jewelry shining so bright. Strawberry champagne on nice. Lucky for you, that's what I like. That's what I like. Lucky for you, that's what I like. That's what I like. Sex by the fire at night. Silk sheets and diamonds. Oh, what? Lucky for you, that's what I like. That's what I like. Lucky for you, that's what I like. That's what I like. I'm talking trip to Puerto Rico. Say the words Enrico. You can be my freaka. Girl, I'll be your freaka mama. I will never make a promise that I can't keep. I promise that you smile and you never leave. Shopping trees in Paris. Everything 24 carats. Take a look in that mirror. Now tell me who's the fairest. Is it you? Is it me? Say it's us and I'll agree, baby. Jump in the Cadillac, girl, let's put some miles on it. Anything you want, just to put a smile on it. You deserve it, baby, you deserve it all. And I'm gonna give it to you. Gold jewelry shining so bright. Strawberry champagne on nice. Lucky for you, that's what I like. That's what I like. Lucky for you, that's what I like. That's what I like. Sex by the fire at night. Silk sheets and diamonds on nice. Lucky for you, that's what I like. That's what I like. Lucky for you, that's what I like. That's what I like. If you
miss the sun when it starts to snow. Only know you love her when you let her go. Only know you've been high when you're feeling low. Only hate the road when you're missing home. Only know you love her when you let her go. And you let her go. Staring at the bottom of a glass, hoping one day you make a dream last. But dreams come slow and they go so fast. You see it when you close your eyes. Maybe one day you'll understand why everything you touch slowly dies. 'Cause you only need the light when it's burning low. Only need the sun when it starts to snow. Only know you love her when you let her go. Only know you've been high when you're feeling low. Only hate the road when you're missing home. Only know you love her when you let her go. Staring at the ceiling in the dark. Same old empty feelings in your heart. 'Cause love comes slow and it goes so fast. Well, you see it when you fall asleep. Never to touch and never to keep. 'Cause you love her so much and you dive too deep. Well, you only need the light when you're burning low. Only miss the sun when it starts to snow. Only know you love her when you let her go. Only know you've been high when you're feeling low. Only hate the road when you're missing home. Only know you love her when you let her go. And you let her go. Cause you only need the light when it's burning low. Only hate the road when you're missing home. Only know you love her when you let her go. Yeah, you only need the light when it's burning low. Only miss the sun when it starts to snow. Only know you love her when you let her go. And you let her go. Say hello to the girl that I am. You're gonna have to see through my perspective. I need to make mistakes just to learn who I am. And I don't wanna be so damn protected. There must be another way. 'Cause I believe you're sleeping away. Though I know I'll be hunting high and low. High. There's no end to the length I go to. Hunting high and low. High. There's no end to the length I go to find her again. Upon these my dreams are depending through the dark. I sense the pounding of her heart next to mine. She's the sweetest love I could find. So I guess I'll be hunting high.
Do the same as
Yes.
High. There's no end to the length I go to. Hunting high.
Excellent. Welcome back from the coffee break. Thank you for all being on time. So we're ready to start, I think, the second session of this morning. Just before we do so, just a quick reminder, if you're not staying at this hotel, please contact the organizers to arrange transport to the airport for the end of the conference. And indeed, if you haven't collected your group photo yet, they're just sitting outside the front door, so you can do so after the session. And with that, I'm absolutely delighted to welcome Professor Calvin Sun to the stage to discuss his work on mechanical properties of solids.
Thank you, Adam, for the nice introduction. Good job with the overview this morning. Before I start, I'd like to thank Panche and his team for putting together such a wonderful event. I've enjoyed it tremendously. Thank you so much. And also like to express my appreciation of many other colleagues who don't get to see each other very often, but I met some new friends and catch up with old friends. Yeah, it's been great. Yeah. So today, I just want to share with actually a simple message at the end. I hope it's clear. We've been studying compaction property of molecular crystals in the context of pharmaceutical tableting. Recently, we found something interesting that I want to share with you today. So one thing, since I came to Macedonia, I've been thinking about whether I should take this medicine, melatonin. If you have traveled internationally, I never tried this myself before, but when you have jet lag, you want to proactively deal with it. You want to, take this before getting on flight, so you can sleep on the flight and you become energetic after you arrive. Maybe try it next time. Yeah. But if you don't travel internationally, you don't have the jet lag issue, but you may have known this drug. Advil is an ibuprofen tablet. You have pain or fever, you want to take this. Or even you don't take it, you're healthy and young, maybe you have allergy, right? You have to take this Claritin or some other allergy medicines. Or we heard about this ritonavir story several times so far in the conference. So this is actually the ritonavir is now one of the active ingredient for use in anti-COVID-19 tablet developed by Pfizer. It's a combination tablet containing ritonavir and nirmatrelvir. So the common thing among the 4 examples I shown on the screen is they are all tablets. So why tablet is so popular? And because it delivers certain pharmaceutical advantages to serve the patients. One thing is the drug, when it's in solid state, it exhibits excellent stability. This stability means both physical stability and chemical stability. Because in solution, so in solid state, things tend to be much more stable compared to solution. So that's quite clear. Physical stability as well, unless you have a very sensitive solid form polymorph, normally it's very stable. But if you have a solid state stability issue, you would have overcome that during the course of development. So the The final tablet formulation you provide to patients should be stable both chemically and physically. And it's very convenient to carry and store. It's a tablet, you can take it in a bottle or in a blister package. You can carry it everywhere and take it when needed. It has a very high patient compliance. I guess maybe I can do a survey now. So if you have a choice for some medicine, you have a choice of taking oral tablets versus injection, please raise your hand if you prefer the needle. How about tablet? I think most of you, yeah, me too, including me, right? Because of that very reason you take tablet, so it's much preferred by patients. When you get a tablet prescription, you will normally follow the doctor's order. And also commercially, the tablet can be made in large quantity within a short period of time. You think about the COVID-19 tablet by Pfizer, right? The market need can be enormous, but you can do that, can compress out many tablets within a short period of time. So not only you can meet the market need easily, also you have the economy of scale. So the cost of manufacturing is lower. And also by the compaction, the tablets are normally made by compressing a powder. You mix your drug with inactive materials, you make them into tablet by compaction. By controlling the conditions under which you make a tablet, you can easily control the structure of tablet. I mentioned that a little bit more later in terms of the porosity. You can imagine when you apply higher pressure, the tablet tends to be more dense. That means it's stronger in terms of the mechanical strength. But if the porosity is too low, means let's say there's no pore in there, water will be more difficult to penetrate into the tablet. You may have a dissolution issue, but by controlling this porosity, you have the ability to balance how fast the drug will be dissolved, and also how strong the tablet is. By one step of comparison, by using suitable tooling, you can control the tablet size, shape. You can put a logo on the tablet. Everything is done in one single step. So to the company, it's very attractive. And also depends on the disease you're treating. You can have different release profile, can be more preferred one over the other. But by doing formulation, for example, you can by incorporating polymer in the tablet, you can achieve controlled dissolution profiles, either immediate release if you want the drug to work right away, or it can be sustained release. You want the tablet to work over a long period of time. The different release profiles can be achieved. For those reasons, if you look at the popularity of tablets on the market, and if you look at the approved products in 2019, out of all the FDA-approved products, 40% are tablets. Here, the 39% of the approved products are injectables. And these are mostly for the proteins and larger molecules. For small molecules, in terms of the dosage and approved drug products, is more than 75% of the approved drug products are tablets. This is only by the type of drug products. But if you count the dosage units, if we say one capsule versus one tablet, it's going to be more than 90% of this drug will be delivered in the form of tablet. So all of this just says tablets are very popular. It's a very important way of delivering drugs to patients. So when making tablets, we want to make high quality tablets. So we need to meet a certain criteria. So the first one is the tablet must exhibit adequate mechanical strength. If it's not strong enough, during storage, manufacturing, handling, you lose some of the materials, then you maybe lose this drug content. Also, the drug content must be uniform in the tablet. The tablet weight must be consistent. That's a stringent criteria for all of this. Tablet must disintegrate as appropriate. If it's immediate release, it must be very quick. If it's a sustained release, it must be very slow. Dissolution rate is important. I mentioned earlier, it can be quickly released or slowly released over a period of time. And drug must be very stable during storage, from the manufacturing to taken by the patients. And they must look attractive to patients. It cannot taste too bad. Also, it cannot contain many living organisms, virus, bacteria. And it must be scalable. You have to make these tablets at commercial scale. So, in terms of the mechanical strength, we want to avoid these problems, such as high friability. That means if you shake or apply some stress to tablet, material will be lost. You cannot have the defects like lamination and caping of your tablet. You don't want to have any sticking, filming, and chipping during the course of manufacturing. If, say, material gets stuck on the punch tip, you have to stop the manufacturing process. So all of these problems has to do with tabletability, how easy, how well the powder can be compressed into tablet. So in terms of tabletability, so we get a profile of the tensile strength on the y-axis as a function of compaction pressure. Normally, when you apply higher pressure, you get a stronger tablet. But the tabletability profiles comes in different shapes, depending on the material properties. For example, in some drugs, many drugs that don't have very good tabletability. That means within this typical pressure range for tablet compression, you don't get a very strong tablet. One example is phenacetin. But some materials can have much better tabletability profiles. This is one example, is from the dical. It's one of the excipients we use in the tablet. For other materials, it can exhibit various profiles. All this has to do with their mechanical properties. And so in practice, if you want to know, even the tablet can be made into very strong mechanically, but you don't, maybe not much more benefit anymore. Practically speaking, if you can have tablets reaching 2 megapascal tensile strength, typically you have sufficient strength. Even higher than that, may not have too much more benefit in terms of the mechanical strength. And for most drugs, it falls below this 2 megapascal in terms of their tabletability profiles. So you have to use some excipients when you do formulation to make sure this problem can be overcome. So common problems we encountered when making tablets having to do with tabletability, including fracture. Basically, after ejection of tablet, after compaction, you don't have an intact tablet falling into pieces. You have a caping. The caping is just a cap. The top of the tablet gets detached from the body of the tablet. You can have a lamination, actually several layers of the tablet. So all of these have to be avoided for a successful tablet product. So why this happens? Right? You want to understand the origin of the problem. Remember I mentioned about this material science tetrahedron. When you have performance problems, means you don't have adequate tabletability. We have to solve the problem, we have to go back to the fundamentals. What's the relationship between the structure, property, performance? Right? Only with that understanding, we can solve the problem effectively. So let's take a look at this compaction process. You start with the compaction with loose powder. You fill the powder into the dye. The particle has a very loose contact. Now you apply stress during the compression phase. So particles in response to the external stress will initially undergo slippage, rearrangement to fill the void. At some point, there's not enough pores or voids available for rearrangement. The particles are forced to deform against each other and against the dye wall. Then during the decompression process, the pressure is removed. Therefore, the particle can undergo a recovery. And if the material is very elastic, imagine you are compressing rubber spheres, and their deformation is fully elastically reversible. So after remove the pressure, the particles go back to the original shape and size. Really, you have a very porous tablet. There's very little contact between particles. But on the other hand, if the material is plastic, so these particles undergo plastic deformation during compression. And this plastic deformation is permanent, is not reversible. In that case, the particles remain deformed even after you remove the pressure. As a result of that, the tablets typically are dense and that normally have a higher strength. So after the decompression, you have to push the tablet out in order to fill powder to make the next tablet. So during the course of ejection, you can imagine the tablet is partly out of the die, but partly is constrained. So the top part of the tablet tend to expand laterally because now there's nothing confining the tablet. So but if this tablet is not strong enough, and this lateral expansion of tablet can lead to defects such as capping and lamination. So when we think about tablet, it consists of particles that stuck together and also voids, like air. So therefore, if you typically for same formulation, same material, if you have a tablet with a lower porosity, means less pore in there, there's a larger contact area between particles, then you have a stronger tablet. And this lower porosity of tablet can be achieved by either using a higher pressure, so you can have a higher extent of deformation during the compression process, or if the material has a higher plasticity, on the same pressure, there's a higher degree of permanent deformation of the material. So that's in terms of the bulk powder. Let's take a look at the same process at a more microscopic level, look at single particles. So imagine initially you have two particles have the point contact. They are spherical in shape. During compression, they both undergo deformation. And during decompression, if the material is elastic, the particles will recover to the original shape and size. You still have a very small contact area between them. And if the material is plastic, you have a large bonding area. And so the first case, elastic case, give you a weak tablet. And the plastic material give you a strong tablet. So from this discussion, I think I hope you can agree with me. Adequate plasticity, which is required for plastic deformation, is necessary for good tabletability. So if particles don't undergo plastic deformation, means like in the case of purely elastic material, you don't have a bonding area between particles. So therefore, there's no strength to the tablet. But even the bonding area between particles is large, the overall strength of tablet also is affected by the strength of the bonding over a unit area between particles. So even area is large, if the bonding strength itself is weak, overall strength is still not high enough. So in order to have this good tabletability, high mechanical strength, we need to have both large bonding area and large bonding strength. So it's the interplay between the two variables that is most critical. When you think about the bonding area, it has to do with molecular packing in the crystal, which affects the mechanical property. We saw some examples earlier with when you have slip lines, crystal tend to be more plastic, undergo more plastic deformation, leading to a larger bonding area. In terms of bonding strength, has to do with surface energy. So basically, compression process is a process of surface elimination. When surface is eliminated, the surface energy is eliminated, and that's how it holds the particles together. So in order to affect or control the bonding area bonding strength, actually one very useful tool maybe of interest to this community is the crystal engineering. You can change the pack, how the molecules are packed in crystal, therefore can control the mechanical property. Also can you can change the chemical composition, therefore the surface energy can be modified. Some examples. Metformin hydrochloride is an anti-diabetes drug. It's a very important drug on the market, but it has to be given at a high dose. And unfortunately, this hydrochloride salt of metformin exhibit a very poor tabletability. So that, in combination of high dose, make it very challenging. You normally have to develop a relatively large size of tablet, because you have to use some other excipients to overcome the tableting problems. Other things, metformin hydrochloride exhibit a poor taste, it's bitter. For oral tablets, you don't want to have any issue like that. So to overcome this problem, we consider crystal engineering. In this case, we consider to form a salt with artificial sweetener, because this molecule is organic base, which can react with organic acid. In this case, we use acesulfame, which is a relatively strong organic acid. Of course, they form organic salt. So when you study this tabletability of the new salt relative to the hydrochloride salt, you can see there's a significant improvement in terms of the tabletability. So hydrochloride salt is the black line. It doesn't form a strong tablet over the entire range of pressure, but for the new acesulfame salt, give you much higher tablet strength with at a pressure below 200 megapascal. So this improvement it has to do with the mechanical property of this acesulfame salt. When compared to the HCl salt, the acesulfame salt exhibit both a lower elastic modulus and also lower hardness. This means that this salt is more plastic, so different compaction. According to our early discussion, more plastic material will undergo more plastic deformation, giving you the large bonding area between particles. So this does help with the formulation of tablet of this drug. But another advantage, which is something we should consider, is when you do crystal engineering, you're not only overcoming one problem. If you choose the right approach, you can overcome several problems simultaneously. This case can be the taste. I mentioned earlier, this drug is bitter, but by forming the salt with artificial sweetener, actually you can significantly improve the taste profile. You can imagine, this is just says the test score, 1 being sweet, the 6 being extremely bitter, and everything in between. You can see this is the result from a test panel. For this, the metformin acesulfame salt, you can see the test profile is much improved. It shifts towards the sweet side, and hydrochloride salt is bitter. So this is by forming this salt, not only you improve the tabletability, you also get this much improved test profile. So that is good. So we can also look at another example of improving tabletability through crystal engineering by making the crystal more plastic. So this is one of the early work we did by using co-crystallization to improve the tabletability of metal gallet, which is the green line here, by forming co-crystal with caffeine. You can see this red line is the co-crystal, give you a beautiful tabletability profile. And we explain this based on the crystal structure. For this metal gallet, it forms a three-dimensional hydrogen bond network. This kind of structure is sturdy, right? It doesn't undergo plastic deformation easily. But for the co-crystal, you see the flat layered structures. You can imagine this kind of crystal will undergo easy deformation under stress, under shear stress. So that's at this point is expected. But when you look at this tabletability profile of the three materials, one thing catch your eye, which is the caffeine. So it increase and up to about 200 megapascal. But when you pressure go above that, actually, not only you don't have a higher strength, actually the tablet strength decreases sharply. Why is that? So we look at this elastic recovery. From this discussion earlier, we know that if the material is elastic, where the deformation is recovered, it's a reversible deformation, then we'll have a weak tablet. So therefore, we decided to look at this elastic recovery of the tablet during the course of compaction. This can be calculated by looking at this dimensional change, because during compaction, the diameter is fixed. So the tablet diameter won't change, but height will change. If the material is undergo more elastic recovery, the change of this thickness of tablet will be larger. So by taking the percentage change of the thickness of tablet, you can get an assessment on the extent of elastic recovery. So in this case, you can see that for this metal gallette, it gives you very high elastic recovery, corresponding to very poor tablability. So the more elastic recovery, less permanent bonding between particles, weak tablet. For the caffeine, you can see that up to 200 megapascal, you have a gradual increase in elastic recovery, but then once the pressure goes higher, you have a sudden jump. Suddenly the elastic recovery starts to increase much faster than at lower pressure. So here, this strange behavior, the sharp decrease in mechanical strength, is correlated to the higher elastic recovery, which is explained by the model we have. So this suggests that if the material is more elastic, then we tend to have poor tablability. So at that point, this is what I believe, what most people believe. So then that's some examples reported about elastic crystals. Right? This was reported by the Gauch and Reddy. This was first example reported with a highly elastic molecular crystal. I think that this as an example has been shown before several times, but for the sake of the completeness of this talk, I still want to show you. So if you bend the crystal like this, you can see the recovery is shape. So this crystal is highly elastic. This crystal is a co-crystal between caffeine and this the 4-chloro-3-nitrobenzoic acid methanol sorbate. So that was all from the model we just discussed. We say if the crystal undergo elastic deformation, the more elastic deformation than the poor tablability. We say, well, let's try that, try to test the model. We decided to use this crystal as a model compound to test the model. But of course, it came as a surprise. When you look at tablability profile, so this blue curve is the profile for this highly elastic crystal. And not only is not bad, it's actually among the best organic crystals we have ever studied. So these two are the top examples of relatively plastic crystals, which give us a very good tablability. But this elastic crystal gives you even better tablability. Why is that? Somehow the model seems not working. So we decided to look into that. So we look at this deformation of the crystal during die compaction, right? Because the high elasticity of this crystal was established based on 3-point bending, as I showed in the video. When we look at this die compression data, we assess the plasticity of the crystal. There's different ways you can do it. We use the two ways. By using the Heco analysis of the in-die compression data, you can extract a parameter, Py, mean yield pressure. The lower the pressure means the more plastic the material is. Another parameter is 1/C. Same thing, the lower the value, the more plastic the material is. You can see compared to common tablet excipients we use to develop formulations, this elastic co-crystal actually is on this plastic side. This inorganic material give you very high values, means very low plasticity, and this HPC hydropropyl cellulose is highly plastic. And MCC microcrystalline cellulose is a well-known plastic material. So actually, this elastic crystal exhibits plasticity comparable to known plastic materials. we look at this elastic recovery of this powder during compaction. So this one is range between 1.5 to 3, and this is very low. I forgot to mention earlier with the caffeine metal gallate co-crystal, the elastic recovery, which was calculated in the same way as this, range from 2 to 30%. And this is on the low end. So clearly, this material, although exhibiting elastic bending behavior during die compaction, it doesn't behave elastically. That means that this material, upon compaction, the large bonding area between particles will be developed because the materials undergo elastic, very little elastic deformation, but a lot of plastic deformation. So now we have to provide explanation. So we look at the crystal structure. So this is a model for the needle crystal of this co-crystal. So this crystal structure, this energy framework looked along the needle axis of the crystal. So this dominant phase of this needle crystal is 110 and 1 bar 0. When you look at this energy framework, you can clearly see a potential of slip lines, which is highlighted in red here, which is a 010 plane. So between these planes, the interaction energy is low. So if the layers can slip, they will most likely slip along these layers, and not on other planes. But one feature of these slip planes is not flat compared to the caffeine metal gallate co-crystal. It has a very flat slip planes, right? That means this slip can go around many directions. But this one the slip can only occur along one specific direction, which is the needle direction of this crystal. Okay, now let's look at this 3-point bending. So you have a needle-like crystal, like showing in the video. You hold on to the end, you put a stress from the middle, right? So if you apply either dominant phases, either 110 or 1 bar 0, you can see the stress applied to the crystal is not parallel to the slip plane at all. So it's at an angle to it. These slip planes are kind of compressed, and the shear stress is along direction, not where the slip can occur. So therefore, although we do have, so the slip mechanism is kind of deactivated. It's there, but in the stress condition of the 3-point bending, is not activated. So it doesn't cause a slip. So therefore, in absence of slip, the crystal appears elastic. So we call this a dormant slip system. So, but if you look at the powder compaction, the story is different. So initially you have the loose powder in there, but during compaction, particularly at high pressure, the powder is highly consolidated. The stress you apply from the actual direction actually is transmitted to the radial direction. And in this case, these crystals are subject to pseudo-hydrostatic pressure, the stress all along. As always, any direction you can find some stress applied to the crystal. This can be proven with some die wall stress measurement. So this is for the four materials, we measure the die wall stress as a function of axial stress. You can see that in this case, this is a very plastic HPC. I mentioned earlier, the stress basically between the axial and die wall stress is almost identical. It means it's like a liquid, right? Transmits stress perfectly. And the less the plasticity, the lower is the slope. And so that's a different story. But the key point here I want to mention is the particles do experience this pseudo-hydrostatic stress. Therefore, there's always, along any direction, the stress will be applied. In this case, you can imagine for this crystal, this slip system, which is dormant during 3-point bending, will have a chance to be activated. So that's our explanation. Of course, it's only one example. We also look at other examples. So here I want to mention the second example is silicoxib crystal. We studied this, we found this crystal exhibit 1D elastic deformation during 3-point bending. So early example was the 2D elastic bending. This one is when you bend on the 001 plane, it's elastic, highly elastic. But when you bend on the 01 bar 1 plane, it's brittle, it fractures. But when we look at this plasticity, in this case by PY, by the mean yield pressure, again, so it's among this more plastic category. It's less plastic than the earlier cork crystal, but it's still rather plastic. So this seems to be not unique to the caffeine cork crystal. The first example I mentioned. We also actually look at copper Akiko, which is another well-known elastic deforming crystal. We found the same thing. But in terms of the structural explanation, there's work ongoing. So I'm coming to the end of my report today. So when we consider the crystal mechanical property and how they deform, we must, not only the structure, we also need to consider the stress state the crystal is subject to. So during 3-point bending, it's relatively simple stress state, but during die compaction, it's different. We have the pseudostatic, hydrostatic stress. So therefore, the different behaviors may be expected in terms of whether it's elastic or not. So before I take questions, I'd like to thank my collaborator, Professor Mala Reddy, and my postdoc and lab members who did work I presented today. And of course, I'd like to thank the funding organizations. Without their generous support, it's not possible for me to be here to share our work with you. And thank you for your attention. I'm happy to answer any question you have.
Excellent. Thank you very much for that wonderful talk. And we do have a few minutes left for questions, so if there's anyone in the audience. No, maybe I'll kick this off then with a quick question. And so it strikes me interesting that you're looking at the compressibility of the void space within the powder, but actually, has there been any correlation, or do you think there is any correlation between the bulk modulus of the material itself and your ability to tablet the material?
What modulus you say?
The compressibility of the crystal structure itself, and the ability to actually formulate that into a tablet.
Of course, that's a clear connection between them, right? If the crystal is more compliant, it's more plastic, during compaction, the extent of the plastic deformation will be much greater, and they also stay there. So when you look at the bulk level, the tablet tend to be stronger.
Thank you.
Yep.
So may I ask you a question?
Yes.
Okay, so you mentioned that when a 3-point bending is occurred at a high elasticity, however, when a compression, that high tabletability. So the reason is that crystal deformation behavior depends on the state of stress.
Yes.
However, when 3-point bending conducted in the diagonal direction and same as a sweeping direction, what's happened difference between appeared phase?
Which phase?
So plasticity is observed by 3-point bending in the diagonal direction of crystals.
Can you rephrase your question?
Sorry.
So during 3-point bending,
yes,
and you are expecting plastic deformation also, is that right?
Yes, sweeping is occurred in a diagonal direction of the crystal.
So slip can occur, right?
Can occur.
But when you have this elastic crystal, I mean, what you observe is it doesn't occur. It has to do with the intermolecular interaction and not only strength, also the topology of the layers, right? So it's a very important question to ask. What kind of structural features we can use to predict the deformation behavior during three-point bending. Yeah. But here is, we are relying on the experimental observation. Yeah. So to explain that, people have been, Professor Reddy had already did some work to try to rationalize why this crystal is more elastic. Of course, if you have a slip line, some other crystals with, the clear slip lines, when also Dr. Mara Reddy have many examples, right? When you bend it, they do undergo quite easy plastic deformation, which can be explained from their structures. Yeah. But we have done, those plastic crystals, the two example reference material I mentioned in that plot, they are plastic crystals. When we bend them, they undergo very easy, very facial plastic deformation. Yeah. But in this case is, when you bend them, they are elastic, without breaking, without undergo plastic deformation. Yet they give you a very strong tablet. By the way, the model is still right. So when you have more plastic deformation during compaction, you get a strong tablet. So that model is, is still okay. But then predicting from structure and from the three-point bending behavior to the bulk compaction, we need to consider stress state. So that's the message. Yeah.
Thank you.
Any other questions?
Right. If there are no further questions, then I guess we thank
you.
Professor Sun again.
So the next presenter is Professor Panda, and he's conducted the lecture in online.
Hello, Mr. Manas, can you hear us? Да.
Yes, can you hear me?
Yes, we can hear you very well. Did you hear us very well? Or?
Yeah, sure.
Okay. Yes, you may start your presentation.
Okay, so can you see the slide? I have already shared the
Yes,
slide.
yes, we can see.
Okay, that's great. Okay, so good morning to all of you. First of all, I would like to say that I'm Manas Panda, an assistant professor of chemistry at Yadavpur University, Kolkata. Thank you, Chairman, for your kind introduction. And first of all, I would like to thank Professor Kanse Namo for giving me the opportunity to present my research work in this conference, a very reputed conference of ICOS 25, in front of all the esteemed scientists around the world in this community. And I would also like to say that I'm very disheartened that I could not attend physically over there because of my visa delay. But even though my physical body is here, my heart and soul are always with you over there. And as I am taking coffee and having beer with all of you. But nevertheless, I'm online all the time and getting all the flavors of the chemistry that is happening over there. So let us start. The title of my talk is Light-Fueled Macroscopic Motion by Organic Crystal. But before going to the main, slides are not moving. Okay, so before going to the main part of the talk, I would like to give you a brief overview about the research activities that is going on going at our laboratory. So it's basically on the line of stimuli responsive smart materials, mostly on the crystals, including light fuel actuating materials or the properties that can be tuned by different stimuli, external stimuli, light, heat, or any other stimuli that is available in the nature or available in the laboratory. And that includes polymorphism in the crystals, crystal-to-crystal phase transition in the solid state, and also slightly different topic is, which is also we are working with the fluorescence switching material in the solid state. So we are also working on the soft crystals which are fluorescent, and we try to see whether different environmental cues or kind of analyte which can change their fluorescence response or fluorescence color, so that we can utilize it for different application. And very recently, we have also started working in a nanocomposite films and their application as actuator or any other purposes. But these are very nascent stage, so I will not cover all these things over here. So I'll cover only in the light field actuating material. So since the talk is on light fueled motion, that means these are the soft actuator. So soft in the sense that these are organic material and that can actuate. That means mechanical response can be expressed in different types of bending, moving or rolling, or different types of response that you have seen plenty of example in the literature or even in the conference lectures in the last few days. And these are induced by different external stimuli, light, heat, thermal, or light, thermal, or pressure or humidity. Energy, input energy, and obviously these are called artificial soft actuators, and these are very important because this has potential to replace the conventional robotic or machinery systems, because the conventional systems are made of very hard material like metals, and their elastic modulus is not sometimes appropriate for certain application. And these soft actuators are much more friendly and benign to especially to the medical for the medical purposes or any other soft purposes. So these have tremendous potential to be utilized for miniature machinery, soft grippers, or even the medical tools, diagnostic tools, etc., etc. And whenever we are talking about artificial actuator, we must acknowledge the nature. And this is one of my favorite slide. Professor Pansino probably know that I am using this kind of slide since my postdoc days over there. Now, this is the collection of many different actuation that is happening in the plant kingdom, and I do not like to spend much time on over there. But what I would like to say that the scientists are always inspired by this kind of actuation and try to mimic this actuation artificially. And this community, solid state crystal community, are always working to develop such kind of material. As you can see in this slide, and you have already seen in the last several days, the different modes of actuation, like peeling, protruding crystal, peeling crystal, crawling crystal, thermally actuating crystal, photo actuating crystals, super elastic crystals, or self-peeling crystal recently developed. But I would like to also mention about something which is very much close to my heart, is thermosalient crystal that I have worked during my postdoc period at Professor Pansino lab. And especially this video is a kind of landmark video where it was a kind of challenging to make the crystal static under, make the jumping crystal static under the microscope and calculate the speed of phase progression, font progression. It was actually quite difficult to make the crystal static. And the day I could record this video and I started jumping and making the crystal static under the microscope. And that's really very enjoyable moment I can still cherish. And from this video, you can actually calculate the phase font progression. And all the debate about the thermosalient phase transition and non-thermosalient phase transition, their speed comparison actually triggered from these videos. So we can calculate now the speed of the thermosalient transition. So along this line, we are also working, for developing a photoactuating material, keeping certain rationale in mind that there must be a photoactive group and certain functional group that can engage in intermolecular interaction. So with that, we have designed and synthesized slightly different molecules which are commonly reported, but in general, most of the photoactuating molecules are vasobenzyne-based or the anthracene-based molecules. But here we have developed a cyanophenyl, a molecule that have cyanophenyl double bond that are expected to undergo trans to cis isomerization as well as the 2+2 cycloaddition reaction in solid state. And we have judiciously, selected this functional group like fluoride functional groups or different other functional group we have synthesized in a series, CF3 group, CF3 functional and other halogens. And we have also changed this functionality, but in this case we found that the best response, photo response can be found for this molecule when this R is NHCOCH3 and this fluorine functionality. The others are not really, so I will not discuss about those part. I will only focus on this molecule which is commonly known as ARF2 molecules in our laboratory. And this molecule undergo trans to cis isomerization and it shows different types of actuation. So when you see under microscope, it's actually green emissive, and at the same time it starts actuating under UV light. And as you can see from this video that the green fluorescent crystals are actually moving, and these slowly changing its fluorescent color from green to cyan. And this is because of the molecular change happening in the crystal from trans to cis isomerization. I will not talk about the fluorescent change over here, because the focus over here is the mechanical response over here. So in order to know how much it can bend with the light irradiation, we have done an experiment. I mean, we have recorded a video by selectively irradiating on a specific part of the crystal and then see how much or what is the maximum bend angle it can achieve by photo irradiation. Now 001 phase, which is the widest phase of this crystal, and which when irradiated with the UV light, and as you can see, the 390 nanometer light actually is not UV, it still falls in the visible region, and you can see the crystal slowly moving, and it can achieve the maximum bending angle up to 200 degrees, nearly to the sharp. So it's quite flexible and quite elastic, quite elastic in terms of considering that it's a crystal, which is generally considered as a brittle and non-elastic material, except this flexible crystal. So as you can see, and these are the snapshot, and from which we can calculate the bending angle. The maximum bending angle we can achieve is 200 degrees, and up to 3/4 cycle it can achieve 200 degree. After that, there are other photoreactions which starts occurring, and as a result, the crystal integrity starts deteriorating. But up to 3/4 cycles, the crystal integrity remains intact. That I will show in the later slide. Now, we want to mention that the crystal can be reversibly bent by reversing the direction of the illumination at the two different sides of the same phase. Let's say it's 001 phase. If you irradiate on the 001 phase, it bends away from the light to a particular direction. And if you again irradiate on the 00-1 phase, it will straighten back and it will bend on the opposite direction. So by reversing the light illumination, we can actually make the crystals in a different shape. Here you can see that we have made a S kind of shape, and then again we have specifically irradiating or illuminating on the specific part of the crystal. We have straightened the crystal. So this is completely based on the forward reaction. That means trans to cis isomerization reaction. But this reversibility, that means the bending to unbending, can also achieve. Sorry, these are the snapshot that I can show. You can follow the arrows where we have selectively irradiated on the crystal surface. But this bending, unbending can also be achieved based on the thermal back reaction. So if you take a photo bent crystals and start irradiating, start heating at 100 degrees centigrade for 5 to 6 hours, you can see the bent crystal can, slowly straighten up, and it closely comes to the initial shape. So it's almost straight like the initial shape over here. So this unbending follows different, different reaction or different process, because this is a back reaction which is happening by thermal energy. Whereas the previous slide, what we showed, is mostly based on the forward reaction, that is trans to cis isomerization. But there are other different modes also. In some cases, we have seen the twisting motion as well as the jumping motion. That means photosalient motions, but that depends on the crystal size. So we are not we are not going to show all the videos over here, just few videos we are showing over here. So in order to show that the surface morphology remains intact after 3-4 cycle, or the crystal integrity remains intact after 3-4 cycle, we have done the surface morphology test, that means with scanning electron microscopy. And as you can see, the before irradiation is very smooth, and after irradiation is also very smooth. By magnification also, we have seen that it doesn't really deteriorate the crystal surface. So that means the crystal is sufficiently elastic after 3-4 cycles. But after 3-4 cycles, there is additional reaction. That means prolonged irradiation leads to a 2+2 cycle addition reaction, and that time crystal integrity starts deteriorating. Crystal starts splitting or cracking or all these things happening. But initially, when trans to cis isomerization is happening, that time the crystal, crystal elasticity or crystal integrity remains intact. And in order to know the molecular process over there, what we have done that you have taken the crystal, irradiated with the UV light, and then dissolved in a solution, DMSO-B6 solution, and then recorded the NMR spectra. And after almost 15 minutes of irradiation, what we can see that there is a there is a existence of both photoisomerized jet isomer, trans cis isomer, as well as the 2+2 cycloaddition product. As you can see, the 2 cyclobutane proton over here and the NH proton over here, and the mass spectrometry also shows that P corresponds to the 2+2 cycloaddition product. So this means that, but initially these 2 peaks are not appearing. So that means that the initial stage or in the solution stage, we do not see these peaks over here. So that means the initial 2-3 cycles, the 2+2 cycloaddition is not happening. Only cis-trans isomerization is happening over there. Now, when there is a possibility of 2+2 cycloaddition, that means this must follow the Schmidt criteria in the solid state. So according to the Schmidt rule, this must the double bond should be in a proper distance in the solid state in the crystal structure. So we observe in our crystal structure that the cyanovinyl double bond resides around 3.87 angstrom apart from each other, and also the obtuse angle is within close to 90 degree, around 98 degree. So that satisfies the Schmidt rule, and it doesn't have any difficulty in undergoing photochemical, topochemical 2+2 cycloaddition reaction. Apart from that, we have also seen that the crystal is stitched by different hydrogen bonding interaction. And the phase indexing of the crystal shows that phase indexing in crystal packing analysis, we can reveal that the pi-pi stacking interactions are actually extended along the length of the crystal, the physical length of the crystal, which is actually parallel to the A-axis of the crystal. And that is important. This pi-pi stacking interactions are important because these are actually stitching crystals to maintain this crystal integrity during the bending. And as long as the 2+2 cycloaddition is not happening, the pi-pi stacking is keeping the crystal integrity intact. And once the 2+2 cycloaddition reaction is happening, this pi-pi stacking interaction is lost, and the crystal starts deteriorating. And in order to know more details about the underlying mechanism, what we have done that we have done the IR spectra, powder X-ray diffraction, etc. And what we have seen that actually amide stretching frequency, the carbon stretching frequency, there is a huge change in the amide stretching frequency and the NH stretching frequency, or even the CH bending frequency, the aromatic CH bending frequency, which suggests that the intermolecular rearrangement associated intermolecular interaction change or reconfiguration of the intermolecular arrangement associated to these bonds. And the powder X-ray also shows the distinct feature before and after UV radiation. So that means there is a packing change during the photoirradiation and trans to cis isomerization or 2+2 cycloaddition reaction. So with all this information in mind, we tried to understand the mechanism for our crystal, even though the mechanism is well established by Professor Pansalamov group, and different Timesonku model and bimorphic model has been established in different reviews and perspective, as well as by Professor Christopher Badin group. This mechanism is already well established, but we wanted to see what is happening in our crystal, why the crystal is bending away from the light, and what are the intermolecular interaction is responsible for this kind of observation. So as we have mentioned earlier, the widest phase is the 001 phase. That means it's perpendicular to the C-axis of the crystal. C-axis, crystallographic C-axis of the C-axis. And when you irradiate the UV light on the on this crystal surface, what happens is the molecules are aligned in this way. Actually, if you see along the c-axis view, the crystals are aligned in this way. That means the crystals are aligned almost parallel to the c-axis. Now, if it has its trans to cis isomerization on this irradiated illuminated surface, these undergo kind of trans to cis isomerization, and there occur a significant change of molecular length. So there is a decrease of molecular length over here upon irradiation. So along the thickness of the crystal, which is parallel to the C direction, there is a compression which is happening along the thickness of the crystal. Whereas, as we have seen, even though we do not have the crystal structure of the cis form, but with theoretical, with the colleague who did the theoretical calculation by geometry optimization on a crystal, what we have found that this molecular length, I mean effective molecular length along the A-axis actually slightly increase during the trans to cis isomerization. So if this slight increase of molecular length, effective molecular length along A direction, in which pi stacking interactions are also there, so that means this illuminated surface is actually elongated. Now, if this is elongated and the compression along the thickness, then obviously the crystal will bend away from the light. So this is how we established the mechanism for this particular crystal. We feel that this may also be common for some other system that we are studying. Now, apart from that, we are also working on many other projects. I would like to highlight those things, even though these are not published results. So the previous one is published in PSTENSCOM last year, but this one, these are not published. In the manuscript is under preparation. So, but since this is a solid state community, I do not have any, any constraint to present this work. So I will not disclose the structure of the molecule, but I can say that this is an anthracene-based molecule with the possibility of 4+4 cycloaddition reaction. And when we crystallize this compound from different solvent like DMF, it incorporates a DMF molecule in the crystal lattice. So it forms a different crystal habit. It's a different crystal structure. When it is crystallized from methanol, it incorporates a water molecule. So we call it as an H2O molecule, H2O form, and the crystal habit is quite different. And interestingly, these two solvates crystals shows very distinct mechanical response when UV light is irradiated or even under heating. So let me give you the glimpse of the activities that are observed for these crystals. So this is the yellow form, that means the DMF incorporated crystal. As you can see from this, from the first video over here, that the crystal elasticity is much less compared to the crystal we have studied earlier. So it immediately breaks after a certain degree of bending, maybe 30 degree of bending, it immediately breaks. And when you have a closer look on these crystals, these are recorded quite far away from the crystal. But if we have a closer look on these crystals, that means much magnified view, what we can see that UV or even the visible light can induce the cracking on the crystal surface, and that cracks are perpendicular to the length of the crystals. Okay, so this video actually shows that cracking is developed, is quite slow actually. It takes a little bit of time. Yeah, you can see the parallel cracks, which is perpendicular to the length of the crystal, physical length of the crystal, and so as a result, the crystal actually disintegrate very rapidly. Now, so we have tested many other crystals, and we are currently developing. Currently this work is under progress. So, and this cracking can also occur in the visible light also, but the process is quite slow. I mean, compared to the UV light, the process is much slower. So, in presence of both UV and visible light, it can happen. The other form, which incorporates the water, actually shows different mechanical behavior. This is actually showing kind of puffing behavior, puffing with a large volume expansion. Although you can see this is the crystalline shape, and after UV radiation, you can see this is actually completely, completely disintegrated and swelled up. So this swelling is actually related to the expulsion of water from the crystal lattice, as we have seen it from different studies. But before that, I would like to say that the ACM micrograph, how the surface morphology change before and after. You can see the smooth surface before irradiation, but after 2 minutes of irradiation, 5 minutes of irradiation, and 10 minutes of irradiation, the crystal surface is deteriorating rapidly. And you can see that the distance between the cracks are actually increasing with the increasing time of the irradiation. So that means, it's a kind of rearrangement, photo-triggered rearrangement is happening within the crystal lattice that is actually destroying all the intermolecular interactions, or probably because of that the crystal integrity is decreasing, or crystal integrity is lost. So to prove our hypothesis, we have done the TGA experiment for both the crystals, for the one which has the DMF incorporated and the one which has the water incorporated. In both the cases, we have seen that the that means light actually triggered the expulsion. That means, so that this green one, as you can see, that the heated crystal. So that once you are heated, the crystal solvent expulsion starts at very early for non-irradiated crystals. So we have also seen that that almost 6% of weight loss in the PGTG experiment. And we have also seen that there is a distinct change in IR pattern before and after irradiation, that means before and after the solvent expulsion from the crystal lattice. And these are currently under process, and we'll very soon we'll submit the manuscript for this work. And what we can conclude from this, after analyzing the crystal structure crystal structure analysis, that the photo-triggered arrangement of the molecule leads to the solvent release from the crystal lattice. We recently have also found that one crystal which is actually starts swimming and squeezing when they are, these are the small fiber-shaped crystals, very branched crystal, similar to the anthracene crystals that was reported by Professor Barding a few years ago. And what we can see that when you are irradiated, when this are suspended on the DMF solvent, we can see these are actually squeezing, slowly moving and squeezing. So we are yet to understand the process. So we have just observed this phenomenon, and currently all these works are under process, and soon it will be communicated. And with this, I would like to acknowledge my group members over here. All these are PhD students, and this is master's project student. Only a few, 4 PhD students over here. Financial support from the HRB India and ADC, and Professor Panse Nomok for all-time help with characterization and other supports during the research activities. And thank you all for your kind attention. I'll be happy to take some questions.
Thank you for nice and wonderful talk, Professor Panda. Unfortunately, can you hear me, Professor Panda?
Yes.
Sorry, unfortunately, we have no time for question, but I'm sure Professor Panda will be happy to discuss by email. So thank you for a nice introduction, Professor Panda.
Okay, thank you.
So the next speaker is Dr. Fernandez. So please prepare slides.
Yeah, thank you. All right. I will thank you for being here. I like to thank Panchanomith and the organizing committee for welcoming me and making me talk, give a talk. I have I think it will affect me. We'll see. I have a quiet speech disability. We'll see if I can consistently give you my lecture. So I'm interested in effects and affecting mechanistic effects affecting solid-state reactions. So this is an example of my research. I was working on orthoxycinnamic acid, OTCA, and it's a very old compound that was studied in the famous 1964 Smith paper. And in this paper, you'll have a table, table 1, that has all the derivatives of cinnamic acid that was studied by Gerard Smith and his co-workers. Included in this is the 3 polymorphs of OETCA. I will refer to OTCA as cinnamic acid because it will be simpler for me to speak about. So they didn't do, at the time that they didn't do the solid state crystal structures, but we have 3 polymorphs, and they published the unit cells and the products from each one. So if they had the alpha product, alpha polymorph, you had the inversion product. If they had the beta polymorph, they had a mirror product, and if they had the gamma polymorph, they had the no reaction. So, in this talk, I will present the solid-state reactions of the alpha form and a derivative of the alpha form, a solid-state transformation derivative. So at the time, the structure was not done. It's the alpha form crystallizes in triclinic in the space group P1 bar, and it means that the molecules are centrosymmetrically related. Now, if you look at the molecules, you'll see layers. The molecules, the crystal structure is arranged as layers, and the cinnamic acid is hydrogen bonded to another cinnamic acid, forming a carboxylic acid dimer. These are further arranged to make a layer by CHO interactions. You think CHO interactions are not very significant to make a popular ribbon, but ribbons form 3 out of 4 forms of OTCA. So 3 out of 4 polymorphs have ribbons. So the ribbons in the alpha polymorph are arranged as layers as you can see here. And this will has a consequence on the solid state reaction. So briefly, this is the chemistry that Smith studied. And if we have the molecule, and so I schematically represented the cinnamic acid as this. And if it's centrosymmetric in the crystal, you'll have a reaction leading to a cyclobutane ring. And if it reacts, Smith's criterion tells you that if it reacts, it's probably that your distance between the double bonds is between 3.5 and 4.2 angstroms. So if you do it, if you study the alpha polymorph, if in ordinary light or time, yeah, all right, thank you. If you studied it in sunlight and or strong UV lamp light, the crystal will explode and you'll get a powder. But if you recrystallize it, you'll get the structure of a inverted product. And the powder and the crystal structure, the recrystallized crystal structure, has the same structure. Now, if you reacted using weakly absorbed light, you need to react it for a lot of time. So this one is 80 days to have a full reaction. But the problem is that the result at the end, you'll have a glass material that doesn't diffract so well, and you can't do a crystal structure of it. So now, during this process, we found if you heat an alpha polymorph crystal, you'll have a transition like this. Now the transition, the alpha polymorph will go to a alpha prime polymorph. The alpha prime polymorph is labeled as it leads to a inversion product, but it's another form of cinnamic acid. So what happens? We have the molecule, we have layers in the half polymorph, and when you heat it up at around about 63 degrees, you'll have a transition. And you'll see the crystals expand, but I will talk more about this later in the talk. The crystals, the layers also bend at the same time. And this is associated with the alpha prime. Now, if you look at the alpha prime form, you'll have two reaction centers, two sites of reaction. In the ordinary alpha form, you'll have only one site of reaction. So if you, between A and B, you have a reaction site and another one on the other side of the cell, and it accounts for 2/3 of the reaction, 2/3 of the reaction sites. And the distance between these molecules is 3.7 angstroms. So when you think about Smith's criterion, it will probably react. The other side is between C and C molecules. And when you measure the distance, it's around about 5 angstroms. And this accounts for 1/3 of the reaction sites. Now, so if you want to react alpha prime at room temperature, you need to stabilize it before react it, stabilize it at high temperature before cooling it down and reacting at room temperature. So, first we reacted it at high temperature to 10%, and cooled it down to room temperature, and reacted it at room temperature. So this was the result. You have this is the starting crystal. At 70 degrees, you'll have a product forming in the AB sites, and when you cool it and react it to 100% completion in these sites, you'll have one conformer that it's topochemically derived, and it accounts. So you'll have a 2/3 reaction or 66% reaction in this form at room temperature. But you can also react it at 70 degrees. We'll see if something changes. So at 70 degrees, you have 2 stages. This is the solid state reaction in a single crystal, and stage 2 is the reaction in in a crystal, but it's a powder reaction in a crystal. So, we have to make it easier for me to explain it, we have in the ordinary crystal, you have the reactant crystal. I'm labeled I colored the molecules as black. If you have a topochemical product, the topochemical product will be orange, and if it converts to another conformation, it will be blue. So the DE is the orange product, the FG is the blue product. So when you react it, you'll initially get the DE product, the topochemical product, and with time, and if it's reacting to completion in the AB sites, you'll see that you have 2 conformations in the AB sites. So originally you have the AB, the starting crystal, and you'll have when you start it, you will have the DE product created, and if you look at the graph, this is the product with time, and initially you have only the DE product over here, but after 25%, the DE product will also will be made, but it will also transform into the FG product shown here. And the end of the reaction, you'll see that the 2 products are effectively 1-to-1, more or less. So if you look at the reaction site, you'll see the reactants, you'll see the direct confirmation from the photochemistry. You can see the EFAL is pointing towards you, and it's this one, the product is also pointing towards you. Now, with time, the phenol group in the solid state rotates 180 degrees, and you can see the FOXY group is pointing towards the board. The off-FOXY group, the phenol ring, rotated 180 degrees. And when you look at the carboxylic acids, you'll see that they have retained the conformation from the initial product. Now, when you these are the plots or differences in the unit cell parameters. The dashed lines are the reaction from room temperature, and the solid lines are the from the high temperature reaction. And you can see the consequence of the phase of the rotation, the conformational change. And it's rather dramatic in the B and C axes and the angles. Remember, this is triclinic. So when you saw the graph in the beginning, the DE product is made until 75%, but it also undergoes a conformational change, and you would expect we will have cooperativity in the phase change. So we can look at the closed contacts. I will only look at the hydrogen bonding. So if we, when the product is made, we'll have the C molecule and paired to a photo product, another photo product, and hydrogen bonded to the another C molecule. So this is the string of hydrogen bonded molecules, and the hydrogen bond of interest is between the carboxylics between the DE products, and you can see we have a large vertical displacement. And if you look at it, so this is side on. If you look at it from above, you'll see that the carboxylics are vertically displaced. Okay, and the distance is large. Now, if we look at the FG molecules, the blue molecules, it looks good from the side, but if you look at it from above, you'll see it's horizontally displaced and really short for a hydrogen bond. But if we combine it together, you'll see we have a good looking hydrogen bond, and it's good looking from above. These are the hydrogen bonded to the C molecules are also good for this structure and the other for this string of products, and for the other ones too. So if there's many interactions, I've talked about only 3, And when you, the probable final arrangement for the molecules is the conformation, the F, G, and the D are separated by alternating in the crystal structure in the 3 dimensions. And this conformation, when you compute a lattice energy, this is the most stable compared to any other arrangement. All right. Now, in the C, so at stage 2, you can't follow it by single crystal diffraction. So you need to follow it by powder. So if you have the crystals and you react it, if you've reacted the AB sites and you reacted it further and got a powder pattern, you'll see it's the same type of photo product and crystal as the alpha polymorph yielded. And also, if you have the final crystal for when the AB site was fully reacted, and you reacted more, you'll get a crystal that that has the spots of a stage 1 crystal and has spots, rings for the powder. So, and when you integrate them, this is in green, and you calculate the powder pattern and fit it. These are from the powder pattern, from the related to this structure. Now, what's interesting is that you can see the C molecules depend on rearrangement on the surface. They will react and crystallize as this this form, and the reaction goes into the middle. The other thing that's also interesting is that it's a powder ring. You don't have any preferred orientation. All right. Now, I kept the upping until the final stages. So this is the alpha to alpha prime polymorph, and it hops, and the reason is not only because we have a large change in the unit cell. It's because this is not only, this is one reason. The other reason is that, so if you up it and you cool it down, 1 in 10 crystals will also help up. And when you do it again, when you eat it again, it will not hop. If you heat it very fast, it will hop. But if you heat it normally, it will be like the phase change that you saw before. Now, the reason that it hops very violently is that if you look at the diffraction pattern associated with the layer lines, layers, you'll have these diffuse reflections. I didn't remember to add the layer plane. It's 102, -102 plane, and these are the -102 family of reflections. So this indicates we have disorder in our crystal. The layers are not on average, they arrange, but we have disorder in the layers. So what I didn't tell you is that in the alpha polymorph, you had the distance between the reacting atoms is 4.6 angstroms. But however, it reacts and it's beyond the Smith criterion. The reason is that some of the layers are in Smith criterion, but when it reacts, it will distort the structure, and when you study it, you will see that it's autocatalytic. So when you react it reacts 10% over 5 minutes. The other 5 minutes it will react 5%. The other 10 minutes it will react 10%. The reaction rate is increasing with time, thanks to defect creation during the factor of dimerization. So when you transform the crystal, you are actually ironing out the distortion, and when you eat it again, the distortion is gone, and it will transform very evenly. So if you want to activate it, you can activate it using a short burst of UV light, and it will jump. And not all crystals will jump, but for example, this one, we have 2 crystals that when we heated it up, these were jumping. The other ones were not jumping. So it works your mileage will vary. If you, I can't say another word. But if you do it for a long time, we found it works for particular crystals around about 5 times, but you'll have cracks forming with time. All right. I will leave you with this as a conclusion, but the take-home message is that with crystal engineering, you can do anything with crystals if you have the patience, dedication, and the imagination. So I need to thank my colleagues. These worked on solid-state reactions or similar solid-state reactions. And so we have a fashion model, we have a business executive, and the academics are in the middle. So I must thank Demi, my colleague, and thank you for your attention.
So thank you for a wonderful talk, Professor Fernandez. So we have time for one question.
Thank you first for very interesting work. I am fascinated by the question of the light intensity, because I try to combine between molecular intermediate changes, so steps like this is very fast, and the rate of photon absorption per molecule is probably very slow. So how do you connect between, okay.
So solid state reactions in crystals are confined to a bulk. They can't move a lot. So these type of reactions, if you have the wrong intensity, you'll have reactions on the surface, and they will break apart. If the absorption is really low, you'll have a microwave effect. It will react randomly in the crystals, and that's how we do it. If we want to get the mechanism. These moving crystals that you saw on Monday and the previous lecture, they depend on isomerization and only on the surface. But I can. These are the experts. So that's why it's bent. For me, I'm interested in the solid state reaction overall, and these don't go back. And this is very important for me. It makes my life easier.
Thanks.
Thank you. Thank you.
So thank you for an interesting lecture, Professor Fernandez. And this brings us to the end of this morning session. And all speakers come to stage for photo. Thank you.
She's a hard woman to please, and I thought about letting her know. She's a hard lady to leave, and I thought about letting her go. I gave her laughter, she wanted diamonds. I was romantic, she treated me cruelly. Where wanna start this chain reaction. I feel the building up inside. When suddenly, oh, what's more that I can bear? More that I can bear. When I saw you walking down the road with someone, I couldn't believe it, it was true. Oh, it was true. I find it hard to sleep at night. This jealousy is burning bright. Visions of somebody else torments me to distraction. Oh, I think of him making love to you. It's more, it was more that I can bear. It was more that I can bear. Oh, yeah, girl, walking down the road with someone. I can't believe that it was true. It was true. When I saw you walking down the road with someone, I couldn't believe it was true. It was true. When I saw you walking down the road with someone, I couldn't believe it. This was true. It was true.
Coming out and dance if you get the chance. We're gonna speed on around. All I wanna know is how far you wanna go. Fighting for survival. Underneath the stars where we park the cars, ain't showing signs of stopping. Pretty little girls naked to the curves, ready to lay under cover. If you wanna go, I'm gonna go. I got a fire burning, gonna take my hand. Hope you see a man. Baby, it's gonna be a big one. Baby, it's gonna be a big one. When we see the lights and we the fights, it's gonna be a stunt. I've got something here. If you give me one more pick, I'm gonna color on. I don't wanna say what I have to say. If I kick it up now, if I wanna go,
If you wanna go, I'm going back down south now. Come and take my hand. I'm going back down south now. When we see the lights and we those fires, I'm going back down south now. I'm going back down south now. I'm going back down south now. On a starry winter night in Portugal, where the ocean kissed the southern shore, there a dream I never thought would come to pass came and went like time's been through an hourglass. You made love to me like a fire and rain. Oh, you know your love got to be a hurricane, killing me with kisses. Gonna let you go that easy. You got to say you love me too. I ain't gonna let you go that easy. I'm gonna give it all to you. Portuguese in love. Just say it to me, say it to me, say it to me, babe. Portuguese in love. Just say it to me, say it to me, say it to me, babe. Portuguese love. Harbor nights we made love till the morning star. Then you crooned a song to me on your guitar. Was it so familiar calling soft my name? Sunlight dancing slowly through love's window pane. You made love to me like a sugar and spice. Hush my broken heart, this must be paradise. Killing me with kisses so tenderly. You made love forever, baby. You made love forever. Oh. I ain't gonna let you go that easy. You got to say you love me too. I ain't gonna let you go that easy. I'm gonna give it all to you. Portuguese in love. Just say it to me, say it to me, say it to me, babe. Portuguese in love. Just say it to me, say it to me, say it to me, babe. Portuguese love. Say it to me, say it to me, say it to me, baby. Portuguese love. Say it to me, say it to me, say it to me. She told me that I'm not enough, and she left me with a broken heart. She fooled me twice and it's all my fault. She got too deep, now she left me scored. Now there's so many thoughts going through my brain. Now I'm taking these shots like it's Novocaine. Harder than the liquor I pour. Tell me you don't want me no more, but I can't let go. Everybody told me so. Feeling like I sold my soul. Devil in a form of a whore. Devil in a form of a whore. You said it. No, you said it. You said it. We'll be together. I fall apart. I fall apart. Eyes keep pouring and the drink keep flowing. Try to brush it off, but you keep on going. Covered in scars and I can't help showing. Whipping in the foreign and the tears keep blowing. Eyes keep dropping and the drink keep flowing. Try to brush it off, but you keep on going. All these scars can't help from showing. Whipping in the foreign and the tears keep blowing. Ooh, I fall apart. Down to my core. Ooh, I fall apart. Down to my core. Didn't know it before. Surprised when you caught me off guard. On this unruly I bought. You was not a shorty I thought. You used to call me on my cell phone. Late night when you need my love. Call me on my cell phone. Late night when you need my love. I know when that hotline bling, it can only mean one thing. I know when that hotline bling, it can only mean one thing. Ever since I left the city, you got a reputation for yourself now. Everybody knows and I feel left out. Girl, you got me down, you got me stressed out. 'Cause ever since I left the city, you started wearing less and going out more. Glasses of champagne out on the dance floor, hanging with some girls I never seen before. You used to call me on my cell phone. Late night when you need my love. Call me on my cell phone. Late night when you need my love. I know when that hotline bling, it can only mean one thing. I know when that hotline bling, it can only mean one thing. 'Cause ever since I left the city, you and me, we just don't get along. You make me feel like I did you wrong, going places where you don't belong. Ever since I left the city, you got exactly what you asked for. Running out of pages in your passport, hanging with some girls I've never seen before. You used to call me on my cell phone. Late night when you need my You're so golden. You're so golden. I'm out of my head and I know that you're scared, 'cause hearts get broken. I don't wanna be alone. I don't wanna be alone. When it ends, don't wanna let you know that I don't wanna be alone. But I can feel it take a hold. I can feel you take control of who I am and all I've ever known. Loving you's the antidote. Golden. You're so golden. I don't wanna be alone. You're so golden. You're so golden. You're so golden. And I'm out of my head and I know that you're scared, because hearts get broken. I know that you're scared because I'm so open. You're so golden. I don't wanna be alone. You're so golden. You're so golden. You're so golden. And I'm out of my head and I know that you're scared, because hearts get broken.
Can I stand all the people standing on their own? They'll fall to pieces, so we watch them grow into strange and pretty faces. I don't know, clutching to my lipstick traces, watch them go and make mistake number. It's strange how much it changes, how they wanna know, how cynical are people. That's what you
gonna find out, pretty mama, what turns on your lights. The full moon is calling, the fever is high, and the wicked wind whispers and moans. You got your demons, you got your desires, but I got a few of my own.
Someone to be kind to in between the dark and the light. Oh, you coming right behind you. Swear I'm gonna find you one of these nights.
One of these dreams, one of these lost and lonely dreams. We're gonna find one, one that really screams. I've been searching for the daughter of the devil himself. I've been searching for an angel in white. I've been waiting for a woman who's a little of both. I can feel her, but she's nowhere in sight.
Loneliness will find you in between the wrong and the right. Oh, coming right behind you. Swear I'm gonna find you one of these nights. One of these nights, in between the dark and the light, I'm coming right behind you. Swear I'm gonna find you one of these nights. One of these nights. Oh, oh, oh. One of these nights. One of these nights. Oh, oh, oh. One of these
Tastes like strawberries on a summer evening, and it sounds just like a song. I want more berries and that summer feeling, so wonderful and warm. Breathe me in, breathe me out. I don't know if I could ever go without. I'm just thinking out loud. and it sounds just like a song. I want your belly in a summer feeling. I don't know if I could ever go without watermelon sugar high, 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 watermelon sugar high.
touch the ground with a restless heart, not the chain and bound. The sky is burning, a sea of flame. Talk the words changing. I will be the same. Na 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 na. Na 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 na. Slave to love. No, I can't escape. I'm a slave to love. Na 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 na. Na 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 na. No, I can't escape. I'm a slave to love. The storm is breaking, oh so it seems. We're too young to reason, too grown up to dream. Now spring is turning your face to mine. I can hear you, lover. I can see you smile. Na 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 na. Na 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 na. Slave to love. No, I can't escape. I'm a slave to love.
1 1 1. Okay, works. 1 1 1. 1 1 1. Okay. Okay, hello everyone. Good afternoon. I hope everyone had a good break. As you can see, we're a little bit behind, but we will try to catch up a little bit by unfortunately making our coffee break a little shorter. Our session for today is Crystal Surfaces and Interfaces. My name is Alexei Tivanski. I'm from University of Iowa, and my co-chair.
I'm Akiko Sekine as co-chair from Tokyo Institute of Technology, Japan. Thank you.
Great, thank you. So I will try to do a quick overview with introducing the session and also very briefly introducing each speaker in terms of their research. And so let me begin with an example of aspirin form 1 crystal. Imagine that you synthesized it, so it's shown here. It's a nice looking crystal. And I do characterize a lot of surfaces, and so one of the things that immediately clear to me is that it has surfaces or interfaces. And for example, you can do single crystal X-ray diffraction, you can map out this crystal, and then you can get an idea about particular crystallographic planes, for example, 100, 011. And then with a crystal structure, you of course can look at different crystallographic planes and have some expectations, as shown here for aspirin crystal structure along 010 direction, that depending on which plane you're looking, or which surface you're looking at, you can experience and quantify different, for example, dimensions. So as an example for 001 surface, so this is an image with the AFM, you can determine morphology. So you see those steps, and you can quantify the step size, which can be related in this case to the thickness of a molecule, or you can look at 100 surface and get also step size, which correspond to the thickness of a molecule. So you can have this nice connection. So there are a couple of points I want to make. So number one, again, if you have a crystal, bulk crystal, it has a lot of surfaces, molecular interfaces, if you will. So they have different molecules or different functional groups. So one could argue that different surfaces, they will have different chemical composition, right? And you can have many different kind of surfaces. So the second aspect that is important to bring up, if you think about energies of surfaces, so they are energetically unfavorable. And this is very easy to understand if you think about a bulk crystal. Let's say you cleave or cut it, right? And so what happens is that the molecules at the interface, they're now missing neighboring molecules as a result of either breaking bonds or missing some interaction forces or types of interactions that stabilize those molecules, right? So that is the penalty which makes surfaces energetically unfavorable. But on the other hand, that also makes them more reactive. And so this is one of the reasons why there is a lot of interest in surfaces or interfaces, because they provide really nice opportunities to do different studies related to reactivity and so on. And the fact that you can have different types of surfaces with different composition, different functional groups, that suddenly opens up a lot of opportunities in the context of different properties, for example, mechanical properties and so on. So different morphologies, so I just showed you one example. Here's an example from our own work where we have a nice, what we call macroscopic crystal, and then depending on which side you're looking at, in this case, both top and bottom sides were chemically equivalent, yet they displayed different morphologies. Here we had a three-dimensional look using atomic force microscopy of spiral pyramids, so we can quantify the step size and so on. But if you look at the bottom, it shows a different morphology. And different morphologies, of course, are important for different applications. So another aspect that is also important to recognize, so you can start, or if you have a crystal, a single crystal, those that a lot of you are using for single crystal X-ray diffraction, so this is the one where you have a high degree of order, crystallinity throughout three-dimensional body of your solid, right? And you can also imagine situations that is referred to polycrystalline material. And this is an example where you can have order domains or regions within your solid that contains nano or micro-dimensional highly ordered crystals of different sizes, and they can be randomly oriented, right? And finally, amorphous material is complete lack of order. So the reason I kind of mentioned this is important in the context of, for example, if you have a material, functional material that relies on crystallinity to do a particular function, right? And imagine if you have a surface or interface where some regions are crystalline or polycrystalline and some regions are amorphous. So one would need to have different techniques that would allow you to differentiate these regions and potentially quantify those different properties. And so some of discussions today will highlight those experimental approaches. Another thing very quickly that I want to bring up is this concept of size. And size is not something that we as chemists kind of used to think about, right? And I want to just very quickly do the following exercise in the context of surface to volume ratio. So imagine that you have a cube of each side is A. So you can quantify the surface area, you can quantify the volume, you can get the expression for surface to volume ratio, and then you do the comparison between what I would call a macroscopic cube, let's say with dimension of 1 millimeter, versus that of 100 nanometer, or it can be smaller. So if you do the comparison, you immediately recognize that as a result of decreasing the dimensions from millimeter to 100 of nanometer in size, you have several orders of magnitude increase in surface to volume ratio. You can do similar for other morphologies, of course, and the equations will be slightly different, but the general trend that the surface to volume ratio will be inversely proportional to size will remain valid. And so why it's important? So it's important, as you can see, if you have a size reduction, especially at the nanoscale, or where the dimension is below 100 nanometers, you suddenly have a lot more surfaces exposed, right? And we just discussed that the surfaces can be unique, and they can display properties different from the bulk. And therefore, if you go to those small dimensions, a couple of things you want to recognize. Number one, you have more surfaces. And number two, because, for example, surface to volume ratio depends on the size, one may expect size-dependent properties. So So very briefly in the context of the relationship in size, again, because we as chemists not typically used to think about sizes, I just want to have this slide that I commonly show my students and other students. That this is on the left is an example of a typical human hair. So the diameter is 50 micrometers or so, right? And here on the right is just the list of different dimensions, perhaps related to this work. So if you have, for example, films, they can vary from nanometers to micrometers. Nanocrystals must have at least a one dimension below 100 nanometers. Microcrystals will have micrometer scale. And what I call macrocrystals, millimeter-sized crystals, right? Now, you may ask yourself, why would you be interested in nanocrystals? And there are a couple of arguments that I generally make that I kind of try to highlight here. So number one, while from experimental standpoint, it's much easier to look and observe macroscopic crystals, but for practical applications, most likely you will have to generate those types of solids with very useful, for example, functional properties in some kind of nanodimensions. So form thin films or order terrace or things like that, right? For example, device applications. And in addition, it's highly favorable, right, to have a very large amount of surface area exposed, which you can achieve if you have a nanodimensional materials. So for example, in the context of catalysis, right? But the caveat here is that we just discussed from a very simple surface to volume ratio idea that you may expect size-dependent properties. And what that means is that not always, but sometimes if you do measurements on macroscopic crystals, you do not necessarily can extrapolate those properties at the nanoscale. And again, you can also observe size-dependent properties. So it kind of hints to the idea that you need to have experimental techniques that are able to probe those nanocrystals, for example, directly. So finally, very briefly, this concept of defects, which is very hard to characterize, but I do think that they're very important for various reasons. And here's just a few examples of steps, kinks, and add atoms, and there are many other kinds, okay? So the only thing I want to mention here is that when you have surfaces, but for bulk as well, those defects are present, and depending on the solid, depending on the surface, you can have very number and type of those defects. And this, in turn, of course, can influence a variety of physical-chemical properties. And so one of the things, for example, that we try to address in my group is understanding how size reduction may impact the relative number concentration of those defects, especially in the context of mechanical properties. So something I will discuss later on. So very briefly, I am an AFM, atomic force microscopy person, and so I don't really want to go into a lot of details. I just want to kind of highlight so the AFM, it uses a very sharp tip. So for example, 10 nanometers as an example shown here. And the key aspect of AFM, you can measure forces and distances very accurately. And what I did here is just showed a quick example of the extent of mechanical pressure that can be generated. And so I'll skip the math, but I just want to highlight that the localized mechanical pressure under that very sharp tip can be remarkably high, orders of magnitude higher than atmospheric pressure. So that creates a problem in the context that you can damage your material, but also creates an opportunity where you can study pressure-induced phenomena of different solids, right? And just one example, I think Panchi will appreciate, is an example of unpublished work with Len McGillivray and my research group, where we started with a metastable form 2 core crystal. So as you can see, we have a 10 micrometers or so long rod. And we followed in situ transformation to more stable form 1. And what is happening as a result of repeated AFM imaging, we think that we are facilitating the transformation, which results in generation of those nanocrystals. And somewhere around here, what happens is that the extent of stress and strain buildup is so much that the crystal disintegrates, okay? To the extent that, as you can see, we lost a lot of material. So those nanocrystals, they jump away, okay? I know Panchi likes that, right? And we also quantified the mechanical properties, so we saw that metastable form was more rigid, and another form was lower Young's modulus. So very briefly, there was a lot of discussion, and it's also kind of related to things that I will be talking about today, the mechanical properties. So there are a couple of very quick things that I want to touch. First, elastic response. So this is the idea, using just this tip as an example. So you indent into the material, then you pull back. If the material recovers fully, let's say you're not leaving a hole or anything like this, this would be an example of elastic response. You can nicely follow it with going in and out with atomic force microscopy data. So you see you have a nice overlap. Or if you have viscoelastic response, or if you induce a plastic deformation, so it can leave an indent or a hole, if you will, on the surface. And with force spectroscopy from AFM, you can easily observe this hysteresis, right? You can also do quantification of properties. So I saw quite a few times about Young's modulus, so I just figured I will spend a minute. So in the context of elastic modulus, Young's modulus, so this is something that is related to elastic deformation, and it basically tells you how soft or rigid the material is. And the hardness is related to now the mode when you induce plastic deformation, so those irreversible changes, and the hardness is indicative of the extent of the resistance to those plastic deformations. And a couple of points to highlight in terms of the importance of these mechanical properties. There is more, but it's just, again, just as an example. One, if you, again, think about employing your wonderful material that has very interesting functional properties, if you want to do it for any practical applications in industrial environment, one of the things you need to be aware of is, of course, that there is generally very high mechanical and other types of pressure and forces associated with this. So it's very important to have this knowledge, because otherwise you can end up with material that can undergo some kind of solid-to-solid transformation, or it can lose crystallinity completely, which, if your functional properties are generally related to the fact that you need to have a crystalline material, then you will lose that functionality. And there will be a couple of talks today related to mechanochemistry, and I just want to kind of, while I'm not an expert, but I do think that mechanical properties and knowledge of mechanical properties are important in the context of understanding elastic and plastic deformations, especially if you think about mechanochemistry. What you have two interfaces, right? Solid and solid under very high pressures and local temperatures. And so some of those properties will be important. And finally, and I'll discuss briefly when I will be presenting, so the Young's modulus of both micro and nano dimensions can be measured with AFM nanoindentation, and of course, macro-dimensional solids can generally be measured with a more traditional indentar approach. Okay, so just very briefly, this is the outline. So we have 5 speakers today, and what I want to do is just want to give a very, very quick introduction in terms of the scope of the work. Again, I'm not an expert. Our first speaker, I also apologize if I don't pronounce your name correctly, is Franziska Emmerling from Federal Institute of Materials Research and Testing. And the title is Mechanochemical Formation of Multi-Component Crystal Systems, Mechanisms and Kinetics. And in today's talk, she's going to be investigating formation of different types of solids, so co-crystals, organic compounds, salts, and she's trying to understand the influence of different parameters and reaction sequences towards understanding the mechanisms and how she utilizes in situ approaches, time-resolved in situ approaches. So the second talk will be from Maria Chiara Di Gregorio from Weizmann Institute of Science, Israel. The title is Meta-Organic Crystals, Shaping, Uniformity, and Symmetry Breaking. And as you can see from those wonderful images, so she's going to be discussing her free additive type of synthesis to generate variety of these types of crystals with very, very interesting morphologies, and some even have a hollow structures, so really exciting. So then we'll have a coffee break, which likely will be a little shorter, and then we will resume. Igor Sokolov is going to be presenting the talk titled Detection of Different Phases of Polymer and Organic Materials Using New Modes of Atomic Force Microscopy. And so just very Briefly, so some of the things that I think he'll show is how you can use the AFM in different modes and multiple modes, and characterize different crystallinity and amorphous phases of different surfaces, and also some connections with how you can use this analysis in connection with machine learning. Then I will give my talk, which will be focusing on a few examples using atomic force microscopy, how we compare the change in the mechanical properties and some functional properties as a result of nanoscale reduction. And finally, we will have Shamarka Mohammed. The title of his talk is Mechanochemistry biased towards thermodynamic products of crystallization? Insights from experimental and computational methods. So it's going to be a discussion focusing on combining experimental and theoretical aspects. And then he highlighted a few examples of, for example, looking at extremes of potential energy landscape as opportunities to understand and explore different opportunities in the context of discovery of functional materials. Okay, with that, I would like to welcome our first speaker, Franziska Emmerling. Thank you.
Okay. Is that working? Ah, perfect. Now I had my Shakira moment, so my day is already good. Maybe that's how she feels. Yeah, thanks a lot for having me here. Thanks a lot, Panche, to bringing us to this spot in the world. That is really amazing. I think everyone would agree that we would be rather out, enjoying the sun, than being here, but I try not to ruin your coffee break by being too long. Okay? Really? Fine. Fine. Okay, so yeah, my name is Franziska Emmerling. I'm from the Federal Institute for Materials Research and Testing in Berlin. And I just wanted to quickly show you at least a few pictures where I'm from, because it's not a university, it's something different. We belong to the Federal Ministry for Economics and Climate Change, so that is the new name. And the institute was founded a few years back. Actually, we had our 150 years anniversary last year, and it was a sad one. We had to celebrate inside, but nevertheless, now times are hopefully getting a bit better. So it was founded as the Prussian Royal Mechanical and Technical Institute, and you see this guy here. So we were meant to test stuff after it is broken. So the Hindenburg and some railroads and so on, these things would go to our institute. Nowadays, it looked a bit, let's say, more colorful. We have colleagues from different disciplines. We have microbiologists, physicists, chemists, of course, engineers. Here, for instance, our engineers try to 3D print material in space, so they do zero gravity flights and test these printers that should then work also under zero gravity conditions. And this guy here is a junior professor, he is a biologist, and he is looking for termites and want to understand how they live. We were investigating termites for long years just for wood protection, but he took this topic up. Okay, before I start with the, here, that's another look at where we are located. So that is in Adlershof, it's an area in Berlin, and that what you can see here is one of the largest science and technology parks worldwide, belongs to the 15 largest technology parks. And there are two things important, at least in my map. So that is where the group works. So that is our campus here. And you can see here the round thing. That is synchrotron, that is SPECI 2, where we do many of our experiments. And now I managed to ruin the chart. Here is Humboldt University, where I also teach. Okay, first of all, I want to thank the colleagues that did actually the work. You can see part of my group here. At our last dance outing, Adam talked us in 2019. That was our Christmas party. We hope that this year we'll have a good one again. You can see here colleagues who contributed to the results I will show today, and also the younger scientists that directly contributed to the things I will be explaining. Adam, you have already seen. And this is Spischweit, a very gifted chemist, and Ines, who has been postdoc with us. Hannes did his PhD with me, already finished, and the two others are struggling to finish their PhD. And of course, I would like to thank the funders. Okay, our research interest quickly. There are different facets of our research. I showed them here. You can see we are interested in organic compounds and co-crystals. There is coordination polymers and MOFs, but also nanoparticles, both in solution and manufactured using mechanochemistry. We are interested in crystallization phenomena and, of course, polymorphism. The darker facets I will explain a bit more today, and the rest has to wait for another time. Okay. Adam and James already said a lot about mechanochemistry. Just to remind you and also to show another Agricola picture, that is a super old technique that has been used throughout the centuries, here to crush rocks and also in pharmacy. It was used for years, and we always need this slide here. This is a rather new one, so you can see in the last 25 years, we have an increase in citation when it comes to mechanochemistry. And there's a reason for that, and I will show you the reason in a second. Just to remember what that means. If this increases in a way, that means that different scientists have picked up the idea of mechanochemistry. It's no longer only in the alloy region or for people working with oxides, for instance. Organic mechanochemistry is a strong field now, and also we can see that other fields pick this up. So just to remind you, what started as a lone mechanochemist is now something where we have to talk to others coming from different backgrounds, and if we come together in this diverse crowd, we might be able to generate some new ideas and maybe also generate a better understanding of the things we are looking at. You're looking actually at my son, and he will kill me if he would have known that I showed this picture, but it's just, it was the easiest way to explain to him what mechanochemistry does. Okay, but that may be bottom line, the more mechanochemists we get, the more fun we might have in the future. So why are we interested in mechanochemistry? And I think as well, James already mentioned aspects of this, and also Adam. Here are again the 12 principles of green chemistry, the one we keep showing up until we don't need to show them anymore. So you see the 12 principles that we should follow in order to really produce green results. And I think this is also familiar to those who listened to the session this morning. So this is energy efficiency. It's an oxidation here using potassium permanganate, and you can see that these guys here on top, planetary ball milling and vibrational ball milling, are really making the race, especially if you take into account that you have to cool the stuff you do in a conventional synthesis. But not only energy efficiency is a point, also waste prevention. Here you see a comparison of a reaction done in solution and done via ball milling. And you can see, interestingly, this takes 60 hours, and you have a yield of 34%, whereas in case of mechanochemistry, you can do it in 5.5 hours, and you have a higher yield in this case. And another thing which is coming up now is like they're using mechanochemistry also for recycling. Here you see the example of PET that you can recycle in easy steps to get at the end terephthalic acid and then move from there. So it is a green method. It still needs to be exploited in many other fields. And why do we need these green methods? You all know these global sustainability goals. We keep showing up from time to time. And behind these colorful facets, you know that typically for all, let's say for all these challenges, the solution is typically material-based, and therefore we need new materials to substitute existing ones or to have new materials with better functionalities, and therefore we would need also newer or other synthesis pathways. And if you come up with a material wish list, so green design would be a good thing, the properties should be tunable, but also upscaling should be possible. And as James already showed in his talk this morning, as you know, that is also possible in mechanochemistry. IUPAC was very helpful in 2019, pointing this out. That is a chemistry innovation that will change the world. It was even better in the text below, because it already said what is really positive about mechanochemistry as a method and where the problems are or the challenges are. So we can make processes possible that we cannot do with traditional solution-based methods, and on the other hand, we are still struggling to understand how the progress really works. That is, but on the other hand, that is the reason why we are scientists, and we need something to think about and do, otherwise we get bored. Quickly, the comparison to solution chemistry in that sense that we can see what we need in both fields. These things I have already mentioned to some extent. It gets more interesting here in this area. We usually end up with powders, or we also see amorphization, and sometimes it's difficult to precisely control the synthesis, whereas in solution-based methods, we usually get highly crystalline products, and the products can then be easily used for single crystal analysis, and here, at least, we claim that we have a certain amount of control about the synthesis. Yeah, this is where the fun begins. If you have a powder, then you have to solve the crystal structure from powder diffraction data and use other methods, and that was really the reason why I started the field and why I started with mechanochemistry, because I wanted to learn more about that. So that is not really a problem. This one is a bit trickier, and you see it here in this easy sketch. If you want to succeed with in reproducibility, if we want to make our reactions so that everyone in the world can do them, and if we want to scale up, we need to a certain extent a control over the reaction, and if you want to get control over something, we need to understand what's happening, both the mechanisms and the kinetics behind the reaction, and that needs a lot of effort from different colleagues and also different methods that we use to look at our reactions. Okay, we said we can scale up, and here's another problem. If something works fine in mortar and pestle, then there's a need to transfer this knowledge to the vibratory mills and then planetary mills and so on. There is something to do, and also, as we all know, when we try to follow the recipes of colleagues, we have to keep in mind the different milling conditions. So that is shown here in this easy sketch. We have, of course, to consider the mill we use and the jar material, but also the balls used. we have to consider the filling degree and also the time we use for milling and also the additives we add to our process. Liquid-assisted grinding was already mentioned as one of the methods where you can obtain higher crystallinity in some cases, but also use it to get to a preferential product, which I will show later as an example. So keeping this in mind, there's still a lot to learn. And let's start with examples that we have done in this field. So I will focus in the first part on organic compounds and co-crystals, and we will also look a bit on the polymorphism in these systems. This is a typical reaction to form a co-crystal. We started with carbamazepine here, and we had different dihydroxybenzoic acid. You can see they differ in the position of the second hydroxy group, and we wanted to see whether we can make new co-crystals. You see here the milling conditions. So we used a vibratory mill, 50 hertz, and we milled for 30 minutes under normal atmosphere, and no liquid was added, so it's a neat grinding process. And the outcome were 3 new co-crystals. You see here the Rietveld refinement, so we were able to solve the crystal structures from the powder diffraction data and then could look at the crystal structures a bit in more detail. This is the first example with this 2,4 co-former, and you can see here in the crystal structure the arrangement that the homosyntons are preserved, so the same synton we have in carbamazepine is persistent, and the same is true for the co-former. We have this zigzag sheet here of alternating drug and co-former molecules. And in the second case, you see it changes. We get a new type of ring formed here, so we get new syntons that are formed, and we have, as a result, we have a wave-like layer of this co-crystal. Here for the 2 to 6 compound, we get a heterosynton, so you can see here the co-former in a direct hydrogen bond with the carbamazepine molecule. Okay, fine, we have our new co-crystals, and now we wanted to know how they form. And what we did is we performed different milling experiments, starting the reactions again and again. So you can see all the points here belong to new milling experiments that were stopped at a certain time, and then the powder was measured immediately and subjected to Rietveld refinement. And what we can see is that the reaction is pretty fast, so within 10 minutes we have these 2 guys ready. This one takes a little bit longer. Remember, that is the one that forms the larger rings in the crystal structure. And that is also our rationale to explain what's happening. So the rate of co-crystal formation in our mind seems to be somehow correlated to the packing motif we have in the final product. We investigated that a bit further and looked at the crystal size changing during the processes. And if you look here at the 2 to 4 co-former, you can see that directly after the start of the reaction, we have product formation, and we end up here with a crystallite size of 90 nanometers. So there is no really period at the beginning. It directly starts to form this new compound. In this middle case, so the slowest reaction, we see that first we have a comminution, and then the crystal is formed, also reaching around 90 nanometers in crystal size in the end. And again, with this 2 to 6 DHPA core former, we see that directly after the start of the reaction, we have the formation of the product, leading in the end to slightly larger crystallines. Okay, that is ex situ data, but we also follow our reactions in situ. And tomorrow, Adam will give a more detailed talk on this. I just wanted to show you what we use so that you can find your way to the data I show in the following. So this is our mill we usually use. That is a Fridge P23 mill, so a tiny vessel, looks like a little egg. And you have the steel balls inside. We made some changes to the vessel geometry, so it's now like more like a cylinder. And then this is put in the mill, and that should work. And then you see, like all the movies, not so dangerous as in James's case. You see it wobbles around, and we have a reaction forming. You saw the synchrotron at the beginning, so we take this little mill, put it in the synchrotron, and that is how it looks like, a little bit more crowded. You can see here is the normal mill. We have different analytical methods, so that's our Raman spectrometer. Here it's the CCD camera, and the beam is coming from this side. And the data we get then for these measurements, I will illustrate here in a quick reaction. That's theobromine oxalic acid. That's kind of a PET reaction we always use. This is a 2-to-1 co-crystal in the end. You can see it up here. We use these milling conditions, 30 Hertz for 20 minutes. And here in the middle, you can see the X-ray diffraction data. And we can, more or less assign 3 areas. We have an induction period where we only see the adducts. We have a very short reaction period. And then here we see only the products forming. In our combined approach, we can also look at Raman data at the same time. And that is quite convenient because we can then see whether we measure the same thing at the same time. For instance, here we can follow different bands. So this band at 855, stemming from the theobromine, vanishes during the reaction. And we can also see a shift here in this area. These are the CC and the CN stretching vibrations of the imidazole ring in our, where can you see it here? In our theobromine, so that changes during the reaction. And you can see that at the exact same time we have this transformation to the... Okay, working? Okay, sorry. So let's move on to another system that is theophylline benzamide. You see I'm working towards the caffeine you get in the coffee break, though these are all relatives to caffeine, and you know the bad solubility, and therefore we went for co-crystals here with benzamide. We have 2 forms present. This one was a pain to solve. You see that's a rather unusual space group, but nevertheless we managed, and you see here the diffraction data for both of them. And we were interested whether we can influence the polymorphic form that is formed in the end by changing solvents. And we did a solvent screening, and here you see the neat grinding, the in situ data for neat grinding. You see the 3 stages I showed you before. So we have the reactants, we have a reaction period that is a bit longer than in the first example, and then we have our form 1 crystallizing in this experiment. If we change to liquid-assisted grinding and use ethanol or acetonitrile here in this case, so we see something different. We see more stages. We have in between the formation of this form 1 and afterwards form 2 crystallizes. And the same here, it's a bit shortened, but in principle, we see the same mechanism here. So we looked a bit closer what happens. So that is a sketch what we just looked at. We have the direct reaction if we use neat grinding or non-polar solvents, and we have a 2-step reaction in the case when we use apolar solvents. We did also additional slurry and seeding experiments to know what we are actually looking at. And this is more or less the result. So this is the kinetically favored product. It's formed in between before the thermodynamic stable one is formed in this pathway, and in underneath grinding and conditions we observe the formation of the kinetically favored form. This is something we and colleagues quite often observe. Also in our next example, same trick. We have a neat grinding and using of non-polar solvents. We get in this case form 2, and in use of polar solvents we get form 1. That is pyrazinamide pimelic acid, so we leave the coffeine relatives. And here in this case we observe these two polymorphs. We solve the crystal structures. You see the diffraction data here and the crystal structures down here. There's nothing special about them. The connection and the hydrogen bonds are quite similar. Also, if you look here at the thermograms, you can see there is an endothermic peak in both cases, nearly at the same temperature, 86 degrees C. So we know a bit about the stability, and we can also, let's say, suggest that the lattice stability is quite similar, and that's also confirmed by DFT calculation. And you see here around 200 degrees, it starts to decompose. So it's not so interesting, so it's something that we see a lot. It got more interesting when my PhD student measured the same sample after a certain amount of time, and then we saw, oh, this is not stable. Here, after 20 days, you see that this form 2 decomposes, and we form form 1. And we did some investigations, so that is our normal reaction, the normal reaction conditions we used, and then we changed those a bit. You see here data for milling at 120 minutes at 30 Hertz, or 120 minutes in a PMMR jar, and that's also the results are depicted here. This is the thing we have been looking at the beginning, and you see here if we decrease the impact, either by using a smaller ball or by reducing the frequency we use under these milling conditions, form 2 is even less stable. An interesting result is up here in our PMMR jars, milled for 120 minutes at 50 Hertz. The compound is quite stable for some time. So it was not really clear what we are looking at. So, and there we thought, okay, maybe we have an issue with seeds that are present in the jar, and that's why we have this transformation. And here you see again our in situ data for the different milling conditions, neat grinding, and here with toluene or with acetonitrile. And you see, or you cannot see any other phases in between, so it goes directly to one or the other compounds. So we have no intermediate formation of another polymorph, and therefore we believe that the difference in longevity, so that in the PMMR jars form 1 is, let's say, form 2 is so stable, has to do with some effects or templating influence of the jar material. So that's a still unsolved problem, but a phenomenon I would like to bring to mind when you think about when you measure your X-ray diffraction data, and also for how long your compounds stay on the shelf. Here another example, this is a N-chlorination reaction of a molecule called hydantoin. These are antibacterial compounds that are, for instance, in textiles. And it was known that it can be formed during mechanical milling. This is calcium hypochlorite used as chlorination agent. And this is, when you think about monitoring reaction, is a nice reaction because you can distinguish easily the reactants from the product. In this case, we were interested in the influence of the ball size on the final product. And you can see on the right side the data for 2 millimeter balls and 4 millimeter balls. Here are the X-ray diffraction data. These are X-ray diffraction data taken at different times, just to see also quality of the data and the assignment. Here in case of the 2 millimeter ball, we have an induction period of 9 minutes, whereas in the case for the 4 millimeter ball, the reaction is quite fast. This 2 millimeter ball reaction never went to completion in these 60 minutes, whereas here we have a full turnover in the reaction. The Raman data is consistent with the things we have seen in the X-ray diffraction experiments. And here we have plotted the kinetic curves for the different ball sizes. You can see what you would also expect. The higher the impact is, here with the 8mm balls, the faster the reaction is. We also see the influence on this induction period here. It takes quite a while for the 2mm ball to get things going. And you see here how the reaction changes from very fast to slower and not ending, let's say, in terms of this 2mm ball. We had then help from our colleagues from theory. This is a kinetic model that was fitted to our data. You can see here the curves fit rather nicely. So this kinetic model consists of a statistical factor and a chemical factor, taking into account that the reaction can really only happen at surfaces that have seen a pronounced, let's say, impact. And here the colleagues then put these curves together, taking into account a scaling factor to eliminate differences in time. And then you can see that overall these curves fit nicely among each other. And here in the next picture up here, you can see the mass fraction changes plotted over the ball volume times the time, so the product of volume, ball volume and time, and you can see that the middle sizes fit nicely together. The other here, the 2mm balls and the 8mm balls are a bit different. What is also clear here in this case, that the rate of transformation seems to be guided by the amount of powder that actually sees critical loading conditions. And here you can see it varies linearly with the volume of the ball. Okay, for the rest, I will show you our work on metal organic materials. So we were very interested in a class of materials that's called metal phosphates. They are coordination polymers or metal organic frameworks, and they come with more or less the same properties and application range as normal MOFs or coordination polymers would do. There's one special feature, and that is the super stable carbon phosphorus bond that makes the compounds chemically and also thermal more stable. Here you can see that we have a rather flexible coordinate, or we have the opportunity to have a flexible coordination environment, because these guys can be differently protonated, giving rise to different binding opportunities, and they are highly insoluble in many solvents, which is nice for some application and annoying if you want to grow crystals. And the system have been notoriously problematic when it comes to growing crystals, and though we went for mechanochemistry, and you see here the copper phenylphosphonate example looks rather crystalline. We couldn't grow larger crystals, but we still could solve the crystal structure from powder diffraction data. So you see the solution here, when you see the problem also. So the phenyl rings are rotating in the structure, and not only that, we needed help here from Ute with electron diffraction to sort the problem out, because you see here the stripes in the diffraction pattern. We not only have these rings rotating, but there's also stacking disorder, so we had to finally solve the structure in a larger cell to take account for that. Nevertheless, on the bright side, using mechanochemistry, we can easily access different geometries and different dimensionalities of these metal phosphonates just by changing the stoichiometry. So if you use 1:1 metal salt to linker, then we get these layered compounds. In a 1:4 ratio, we get these isolated clusters that are also not so easy to obtain in solution. And then you can play around. This is just to illustrate if once you have the reaction conditions, you can even change the linkers here, different degrees of fluorination, and still you get easily your your final product, just exchanging the linkers here in the system. Here are the diffraction data. These layered structures always look the same. You have the layer distance up front. You see that increases here from the neutral molecule to the perfluorinated one. And yeah, in this case, we did some measurements to check whether the material would discriminate water absorption, and of course it does. So the moment it's heavily fluorinated, these are water and ethanol absorption experiments, you see that there's nearly no water uptake. Okay, water uptake was not wanted in this field, but is wanted in the next example. These are metal phosphonates, which we want to use as proton conductors. You see, we changed a bit our philosophy. That's not only one linker, so we also added an auxiliary ligand here, bipyridines, or let's say at least something that resembles a bipyridine. And again, the reactions were done mechanochemically for different salt precursors, cobalt, iron, and here copper. In case of iron, we have to go back to this chloride, which brings some annoying problems, but nevertheless, we were able to get new structures. They are proudly enabled now, BOM 1, 2, and 3. And you can see here the simulated patterns and then results for 1 gram and 10 milligram reactions. If you look at the crystal structures, everything worked nicely. We have our auxiliary ligands and we have the phosphonate ligands here, and we also have a coordinating mortar molecule, which is something that is interesting when it comes to proton conduction. Looking more closely on these structures, you can see phosphonate ligands do what they do best. Here it connects bidentately to the copper ions, and here you have a monodentate connection, and we have these zigzag sheets here in BC, in the BC layer, and these are stacked to the 3D network that we have in the end. And a closer look here, along the B-axis, we have the channels with the mortar molecules inside the structure and connections to the coordinating water of the cobalt atom and also the phosphonate hydroxyl group. Here for the other compound, 1 and 2 are the same, are isostructural. The cobalt and iron compound are the same. Copper compound is a bit different. You see here the first coordination sphere is a more or less a chain, and then we have here a network formed by hydrogen bonds, and again we have our promising channels that might be helpful for then proton conduction. Just a quick step backwards, how we do these syntheses. I showed you we put everything together, though that would be this approach. 2 linkers, 1 salt precursor, and then build up the MOF. But we have seen that it's also possible to do it sequentially, so to either start with a bipyridine or with a phosphonate linker, and then add the second one in the next step. It was unclear which reaction would be faster, so we did some in situ investigations, and again, that's the one-pot reaction. You can see it's done in more or less 1.5 minutes, or maybe 2 minutes, so pretty fast. If you do it one after another, you see it takes a bit more time to form here the cobalt bipyridine complex, and also even longer time to form the phosphonate. But then if you put the bipyridine linker to this phosphonate, that's a pretty fast reaction again. So actually the system really wants to form the MOF in the end. So quickly looking at the water uptake in this context. So you see here in black, that's BOM 1, so the cobalt MOF. We see, okay, it starts to, the water uptake starts early, and that is also a sufficiently high amount. Same is true here for the red curve. Even though they are isostructural, the behavior is a bit different. So obviously, the metal atom plays a role here. When we switch to iron, the curve looks a bit different. And then we have here in the BOM MOF3, which has a bit of a strange behavior, and that has to do with the fact that there is a change in the structure. Okay, nevertheless, We performed impedance measurements to check whether we have a proton-conducting material here. You see here the typical curves with a semicircle in the end, and here this steep slope in the lower frequency region. We see a behavior we would also expect. So we have an increasing conductivity with increasing humidity. And if we keep humidity constant and increase the temperature, then we also have an increase in conductivity. Here you can see the values, though it's still not competing with Nafion. So that is still much better, but it's a possible, we are possibly on the way to have an exchange for that. For the proton conducting mechanism, you always have to make sure whether you have this Scrotus hopping mechanism or the vehicle mechanism where you have charged carriers carrying the protons around, and here the low values derived from the Arrhenius plot, they point towards a proton hopping mechanism. So with that, I'm done. So just the final comments. You know, you might have knew already, so that is a clean and efficient method to synthesize new materials. So mechanochemistry can be used to access new, and in our case also metastable compounds. There's still a lot of work to do to understand what's really happening during the reaction. And if we understand that, that is key to control, of course, the reactions. We might need to develop further in situ methods or use the existing one existing one in a different way, and also refine the way we treat our samples. But for the last two things, I think Adam's talk will help a bit. With that, I thank you for your patience, and I'm looking forward to your questions and want to point you in between to this crystallographic school in Berlin. Thank you.
Thank you for the wonderful talk. Is there any question or comments?
Marta Dudek, Polish Academy of Sciences. Thank you for beautiful talk. I have encountered opinions that mechanochemistry is like a preferred route to, say, metastable polymorphic co-crystals. So if you want to like obtain a metastable form instead of thermodynamically stable, you should like do mechanochemistry first. So what's your take on that?
Yeah, if you compare it to solution chemistry, in most cases, the thermodynamic stable one will win, yeah? Even though you might be forming it in between, you just don't catch it. You have seen in the examples I have shown that in some cases, especially when we can deal a bit with a liquid-assisted grinding additive, we can change that, so we can access the metastable phase. And in many cases, it's also stable but it depends on how long you would want it to be stable. Yeah? Let's say, as I have shown in the one example with the pimelic acid, it also changes after time. But nevertheless, it's true that you, under mechanochemical conditions, you can obtain also the metastable phases.
Okay, thank you.
Thank you, Francesca, for a wonderful talk. So I've got another kind of theoretical based on everything that you've seen. So there's two ways to go about doing these crystal forms in a mechanochemical system. You could take two big molecules and break them all the way down, and then they can start building back up again. Or you could take two systems, start building it down to a bit, they start interacting, and then you start building that down. You could look at the intermediates. What do you think is going on in these systems?
I think it depends on the system. If you remember the Bill Jones work, where he put together on a glass just like two coformers and bring them together, and then they form a eutecticum, and then that's the driving force. Yeah. So in let's say at least in our setup and with the time resolution we have, I have not so often encountered amorphization as I would have expected, suggested that it happened at the beginning. So I was thinking that everything would go through amorphization. But there is not one mechanism. I'm pretty sure there are different things at work.
If I take advantage and ask a quick question. So on your last couple of slides when you were discussing the humidity-dependent studies, so I was just kind of curious if you looked at the kinetics. So for example, how long for your solid it requires to get into the equilibrium with the surrounding water vapor? Because I suspect especially for low-rate humidity that may take some time, right? Thank you.
Thank you for the question. We haven't done that, but that is actually very interesting. Yeah, that's something to keep in mind. Thank you. Yeah. Yeah. Thank you.
So, thank you very much again, Professor Emmerling. So, next speaker is Professor Maria Chiara Di Gregorio from Weizmann Institute of Science, Israel.
It's possible to have. Good afternoon. So you can hear me? Good afternoon. First of all, I would like to thank Panche for this great opportunity and for organizing this wonderful conference, really. I'm very happy and honored to be here and to share with you my research. In this talk, we will speak about the possibility to modulate size and even more morphology of crystals, generating a morphology that has a curved line, chiral feature, and very, very complex habit. Let's start with a brief introduction. Understanding what is the relationship between the crystallization parameter, the crystallization process, and the final product of our crystal is a great challenge of chemistry. Mastering these aspects means being able to design crystal with targeted function. The interest is transversal and involve all the research field that deals with crystal. For example, drugs, nanocrystal for nanotechnologies, and so on. Often, in order to learn how to crystallize, we look at nature. Nature has extraordinary capability of crystallization. For example, scientists were amazed for years by the very complex morphology of snowflakes. Another intriguing class of material are crystals that comes from biomineralization process. A few days ago, we attended a beautiful lecture from Asaf Gal. So this crystal often show features that are paradoxical. For example, they exhibit curved lines. So usually this is not conventional for crystal that has straight facets. Another interesting aspect is chirality. Chirality at morphological level that appear without having chiral building block. And another interesting feature is that often these crystals have, from a morphological point of view, a multi-domain appearance, but they are perfect single crystal. My question now is, are we able to translate this feature in synthetic crystal? I will try to give my contribution in this field. In particular, I will show you 3 works. In the first part, we will speak about the possibility to generate crystal with a curved line, and we will do it through a very easy approach. In the second part, we will always keep very high the complexity of the morphology, and we will introduce chirality at morphological level. In the third part, I will try to explain why these features appear in this class of material, comparing the morphology with the crystal packing. We will use, it's not switching, okay. We will use as tools for our investigation a specific class of crystalline material, metal organic framework. This choice can sound weird. Why? Metal organic framework, or MOF, as for sure you know, are crystals obtained by the self-assembly of organic molecules and metal ions through coordination bond. The self-assembly leads to the formation of an ordered framework that is often porous. To summarize a large literature, we can say that till now, most of the effort in the field has been focused on the crystal structure design, to get crystal structures that are more and more porous and use them for application like gas storage catalysis. But what about control over size and morphology of this crystal? This aspect is much less investigated. Usually MOF that are grown without additives, surfactant, capping agent, they look like this. They are not homogeneous in size and in shape. In contrast to this general trend, we developed a very easy approach that allow us to have a homogeneous MOF. And what we do is a very easy solvothermal reaction. We use just the basic building blocks, so we don't use any template, no additives, no surfactant. What we do is to prepare the two-stock solution of the ligand and the metal salts, to mix them in a pressure tube, to seal the pressure tube, put it in the oven, wait several days, and after that, we observe the formation of a precipitate. This precipitate is actually our MOF. So what are the building blocks that we use? As a concern the molecular the organic part, we synthesize this class of ligand, here reported, and they are tetrapodal molecule. Each arm terminates with a pyridine unit that is responsible for the coordination with the metal. We notice that we can affect the self-assembly process by changing the molecular structure in specific position. In the core, till now we introduce a carbon core or an adamantane core, and also we varied the bond order in the position here highlighted in blue. As a concern, the metal salts, in this talk I will show you mainly nickel and copper-based salt, and what I want to emphasize is that in the self-assembly process is very important, both the typology of the cation and the counterion. By changing one by one this parameter related to the basic building block, we managed to generate a wide array of morphology, ranging from simple polyhedral structure to more complex polyhedral structure, but that still can be described according to the conventional rules of crystallography, till to reach to very, very weird and complex morphology. I told you that we can also have a sort of control over the sides monodispersity. Here I reported the case of a MOF that we obtained with this ligand, carbon core double bond, and nickel bromide. They are nanomorph with an hexagonal morphology. The material is crystalline, as you can see, and please notice how much homogeneous is the size of this crystal and how much quantitative is the reaction. What we put in the pressure tube, it reacts without formation of subproduct. Now, besides the parameters that are related to the basic building block, we also observe that we can affect the self-assembly process by performing a very trivial solvent pretreatment. What does it mean? In a conventional synthesis, what we do is to solubilize the ligand in a mixture of DMF and chloroform, and the metal salt in DMF. Here, this is the case of the ligand with adamantane core and double bond, and as a metal salt, we have nickel bromide. What we do is to mix these two building blocks in a pressure tube, to put it in the oven for 2 days, and after that, this is what we obtain. Nice prismatic mauve with an hexagonal base. Now, what happens if I use exactly the same typology of building blocks, exactly the same solvent, everything the same amount, everything the same procedure, but before dissolving the ligand in the DMF and chloroform solution, I sonicate just the solution and I carry on as I did before. This slightly change in the preparation leads us to this completely different structure. They are elongated structure. Each structure looks formed by 6 subunits, protunding subunits that are rounded, that arrange around the central axis of the structure. And if we focus on the termini, this structure looks hollow. What happens when we go to sonicate the solvent? When we go to sonicate the solvent, we generate a radical. The radical comes from the decomposition of the DMF. We detected the presence of this radical through electron paramagnetic resonance measurement. And I want to emphasize that we got this signal without any spin trap. This is a very stable radical, lifetime around 15 minutes, so it's a time that is perfectly comparable with the time that I need to prepare the sample. And also we notice that when we go to introduce the metal salt, the lifetime of this radical increases even more. So what this tells us? That when we go to sonicate the solvent, we change the composition because we generate other species, and then we have a radical that interacts with one of the building blocks. And this is enough to change the crystallization path. How these crystallization paths change? We decided so that in order to get the final structure, we need 2 days of solvothermal reaction. What we decided to do is to stop the solvothermal reaction at shorter time and analyze what we have in the sample. We did it both for the sample with sonicated solvent and for the sample with not sonicated solvent. Let's start with the sample with not sonicated solvent. So after half an hour, this is what we have in the sample. So we have a flat structure with a parallelogram profile. These structures are dominant also after 1 hour and a half and 3 hours. They are very dominant in the sample. We can start to see very few cylindrical structure, and if we focus on the termini of this cylindrical structure, we can see that they are closed. After 1 day of solvothermal reaction, the situation drastically changed. Still, we can see few remaining flat and parallelogram structure, but most of them are redissolved, and the sample is strongly dominated by prism with an hexagonal base, and after 1 day they are not so homogeneous inside, but after 2 days of solvothermal reaction, they get a good homogeneity. Now, bringing this in our mind, let's go to see what happened in the sample with sonicated solvent. After half an hour, again, we have similar structure as we saw before. But this structure redissolved much faster, and after 1 hour and a half, already we have this cylindrical structure. This is the sample after 1 hour and a half, 3 hours, 1 day, and 2 days. In the top part, you can see a zoom out of the sample. In the second line, you can see a zoom in on representative structure. And on the third line, you can see details on the termini. So what we observe is that during the solvothermal synthesis, this cylindrical structure grow in length, but even more in diameter. We start with something that is around 10 micron, and we ended with something that is almost 15 micron. If we focus our attention here, we can notice that at the beginning, the external surface is flat, but with the time, a fine texture starts to appear till to develop very well-defined protruding unit. If we focus our attention on the termini, we notice that after 1 hour and a half, the termini is closed, or at least we can see just a small concavity. But with the time, a cavity appears, and is larger and larger as we increase the reaction time. We wanted to know more about the appearance of this cavity. So what we did is to collect microcomputed tomography data on this initial structure. So as you can see at the SEM, they look close structure, compact structure, but when we go to analyze the transversal section of this crystal, we notice that we have empty area. You can see the black background, so this means that there is much less material. So this crystal is not so compact as appear at the SEM. As it concerned the sample after 3 hours, we decided to cut it by focused ion beam. So we mechanically cut the crystal. We did 4 consecutive cuts, moving from the termini towards the center. And this is the images at each cut. And as you can see, we notice that the cavity appears close to the termini, but as we approach the center, it closes. So the core is more dense. Similar things we saw in the sample after 1 hour. This time we cut the crystal in this direction, and this is the crystal after the cut. And we can see a similar thing that we observed before. So a core that is full, and a cavity that is larger at the termini and becomes narrower as we approach the center. After 2 days, the crystal is completely hollow. Again, we saw it by cutting the crystal at 4 different positions by focused ion beam. And even more, we can see it with a microcomputed tomography reconstruction. Here you can see the full volume reconstruction. You can clearly see that we have a continuous cavity. You can clearly see the 6 protruding unit. And now you will see all the section. And again, we notice that the cavity is larger towards the termini. We collected the other SEM images, and we could notice further details. If we focus our attention in the inner part of the cavity, we can see these fine textures that is indication of material redissolution. And also we notice that this protruding unit grow by a further addition of material, layer by layer. So in the light of this data, we hypothesized the following mechanism. So basically, in the solvent, in both samples, we see similar structures. So initial parallelogram structure, that probably they are the one kinetically favorable, and the elongated cylindrical structure that probably are the thermodynamically favorable. The drastic variation is in the kinetics. So this initial structure redissolves much faster when we have the formation of this radical, and this crystal appear much faster when we have the presence of the radical. And we know that if a crystal grows too fast, it can develop defect. And indeed, in this initial cylindrical structure, we see empty area in the center. This probably triggers the redissolution process that we observe by SEM and induce the formation of this cavity. Parallelly, we observe a further path, that is the redeposition of material on the surface to form this protruding unit. Till now, I just spoke about morphology, but what about crystal structure? This approach just touches the morphology. It doesn't touch the crystal structure. The crystal structure of all the crystal that we saw, the not sonicated one, the sonicated one, final structure, or after 1 hour and a half, is exactly the same crystal structure. I will not go into the details now on this crystal structure because I will explain it later. We further proved the isocrystallinity of this crystal by TM diffraction. So we collected TM diffraction on the hollow MOF, and we compare it, the diffraction, with the single X-ray data of the not sonicated and full prism. And we can see that the matching is perfect. We also went to analyze the bulk sample. We collected the PXRD, and as you can see, we have exactly the same peak that we could fit, and we have very, very similar unit cell parameter. So this approach is just an approach that touches the morphology, is a shaping approach, but the crystal structure is exactly the same. At this point, you can ask me, so this approach works just for this system? No, we further investigated this synthesis with the other ligand, with the other MOF. So we use the same ligand, but this time we use copper bromide. If we do a simple synthesis without sonication of the solvent, this is what we obtain. So it's not nice, not homogeneous, not so crystalline also. But if we go to perform the sonication of the solvent, we have this nice shaped crystal with 12 facets, and as you can see, is quite homogeneous, and the material is crystalline. So I showed you here that we can affect the morphology of crystal by just using the basic building blocks, changing pivotal parameter, and we can observe formation of morphology very complex that present, for example, this curved line. Let's move now to the second work. Here we will speak about chirality. For this system, we will use these building blocks that are completely achiral. So a ligand with adamantane core, triple bond, and as a metal salt copper nitrate. What we do is our conventional solvothermal synthesis, 2 days of reaction, and after that, I just take out the pressure tube for the oven, and I wait for 2 days at room temperature without doing anything. After this trivial synthesis, this is what we obtain. Again, very complex morphology. Each structure looks formed by 2 subunits, and each subunit has exactly the appearance of a flower with a central stigma and many petals. The number of petals goes from 13 to 20 petals. This morphology is chiral. Why? So the 2 subunits are not symmetric, but they are twisted. We could see this by microcomputed tomography. In the top part, we have the full volume reconstruction of the object, and in the bottom part, we highlighted the region with the highest contrast. Now, if you focus your attention on the center, here, this point, you can see the twist, both in the top part and bottom part. In the same sample, we observed crystals that are twisted in the clockwise and anti-clockwise manner. So this is the other morphological enantiomer. And both of these crystals are in the same sample. Now, how this crystal form? This crystal form mostly in the second part of the synthesis, when we leave the sample to age at room temperature. What does it mean? So when I stop the solvothermal reaction, this is the structure that we have in our sample. So they are very simple, globular structure. This is the top view, this is the side view. After 11 hours at room temperature, we can clearly see an hexagonal profile from the top, and we start to see the two subunits. And after 2 days, the flower is very well formed. At this stage, we can clearly see, this time by SEM, the twist. And again, in the same sample, we can observe clockwise and anti-clockwise twist between the two subunits. Now, how is possible to switch from this geometrical polyhedral structure to this very complex, almost artistic morphology? So we notice that starting from the hexagonal base, further layers grow on top, and they grow in a chiral way, making chiral spiral loop. And this is what induced the formation of the petal area. And we see this growth at different stage. And again, we see both petals that grow in a clockwise and anti-clockwise way in the same sample. This is the morphological evolution. What about crystal structure? Here, the big surprise. So, looking at this crystal in which you can clearly see subdomain from a morphological point of view, you would say this is a polycrystalline material. No way that this is a single crystal. This is a perfect single crystal. We took the full crystal, and also we split it in the two subunits, and we analyzed them one by one. We put this crystal under the X-ray beam that we have in the laboratory, 1 micron diameter beam, so we are sure that all the crystal is immersed in the X-ray beam. And we can see a classical diffraction from single crystal, well-defined single spot, and also reported here 3 projection of the dual sphere. As you can see, it is a single pattern that we could index with a single domain without any indication of twinning phenomena, multiplicity. So this fact, to have a crystal that from a morphological point of view appear multicrystalline, that has multiple subdomain, but that from a crystallographic point of view is a perfect single crystal, is a phenomena that occurs in nature, is even rare in nature, in crystal that derive from biomineralization process. We managed to reproduce this phenomena in our moth through a very easy approach. We went then to solve the crystal structure. This is the crystal structure. The crystal structure is ordered by coordinative interaction. This is the coordination node. So we have the copper, the metal in the center, that coordinate 4 pyridine units. These 4 pyridine units belongs to 4 different molecules. In the axial position, we have oxygen that belongs to water. The material is porous, as you can see. We have 2 kinds of channels. This is the view down the z-axis. We have a continuous channel with an hexagonal symmetry and a triangular channel with trigonal symmetry. Space group, another big surprise. The space group is P622. This space group is a very rare space group. Before our study, there were just 7 examples in the Cambridge database out of many, many crystal structures. This kind of space group is achiral, but it's one of those achiral space groups that tell us that we have some chiral packing inside the crystal structure. Let's see if it's true. So let's go to analyze the region around the hexagonal channel. This is the top view, this is the side view. And you can see that the channel is formed by 2 sets of helix that are interconnected. Similar things we can see if we go to analyze the region around the triangular channel. Again, the triangular channel are formed by a motif that is chiral, that is spiral. So in this work, I showed you that we have a crystal that presents chirality at 2 levels, at crystallographic structure level and morphological level. And it is known that and the basic building blocks are achiral. It is known that a chiral building block can give chiral crystal structure, but it's not trivial at all that chirality appears at morphological level. Another important point is that we have a sort of counterintuitive paradoxical phenomena. We have a crystal with a multi-domain appearance from a morphological point of view, but is a single crystal. Let's move now to the third and last part. In this last part, I will try to justify, explain why this kind of strange phenomena, also paradoxical, occurs in this class of material. And I will do it using this kind of crystal as a tool for our analysis. This crystal forms by the self-assembly of this ligand with copper sulfate or copper nitrate. By changing the counter ion, we strongly affect the sides. With the copper sulfate, we get a structure that has a diameter around 200 micron. If we use copper nitrate, the diameter is much lower, around 30 micron. But overall, the morphology is exactly the same. It's a morphology of a 6-tip stars. And again, in this crystal, we have a multi-domain appearance from a morphological point of view. We have a central hexagon that is surrounded by 6 pentagons. Another interesting feature is that we have reentrant angle. I want to emphasize that this reentrant angle facets are not random. So we can clearly see a constant degree, 169, in both cases, and the angle between the adjacent tips is always 60 degrees. So due to this regularity of the facet disposition, we can describe with this morphology with a point group. Point group is 6 MMM. So we have a 6-fold axis that is perpendicular to their star shape, and then we have 3 perpendicular mirror plane. Now, we have these 3 features: multi-domain morphology, concave angles, point group. These 3 features are in contrast among themselves. Why? Multi-domain morphology and concave angle usually suggest polycrystallinity and twinning phenomena. On the other hand, point group is the classical tools that we use to describe morphology of single crystal. How these 3 features can coexist in this system? But we have a further contradiction. Once we have a point group, according to the conventional rules of crystallography, we have expected form. And this form is not the one among the expected for the point group 6MMM. But I will say even more, this form is not expected for any point group, because all the form has a not concave angle, but convex angle. So how we can solve this puzzling system? First of all, let's see the crystal structure, the crystallinity. It's a single crystal, it's a polycrystalline material, it's a twin material. We collected single crystal X-ray for both samples, for them off with copper sulfate and copper nitrate. And again, we have the typical diffraction of single crystal. Our single crystal X-ray expert, Dr. Linda Shimon, told me, Chiara, let's check that if there is some hidden twinning phenomena like the merahedral twinning. She did a special test to check also this aspect. Nothing. These crystals are single crystal. We went to solve the crystal structure, and again we observed the crystal structure that I showed you before, an hexagonal unit cell, 2 channels with a helicoidal motif of the wall of the channel. The space group, again, is P622. And this space group very well relates with the point group that we observed, P6MMM. So at least for this aspect, we are okay. But now, how to justify the form for the point group 6 mm? These are the expected form. Why we have that concave angle? Why we have that shape that usually appears for twinned crystal? So what we did, in this case, we were lucky. Unlike the previous example that I showed you, this crystal is, the copper sulfate-based crystal is very big. It's 200 micron. So we can put under the camera of the microscope and we can clearly see it. And another advantage is that this crystal has no curved feature. So we have straight facets that we can index it. So what we did is to take a crystal, to mount in a loop, to put it in the X-ray machine, to collect the diffraction, to solve the crystal structure, and we oriented the unit cell compared to the morphology. The z-axis, that is the axis where we have the channel, is perpendicular to the star profile, and the A and B axis pass through two tips of the star. At this point, we went to index the lateral facets. For sake of clarity, I labeled each facet with a number and with a color. And here you can read the plane corresponding to each lateral facets. Once we have the lateral facets, we went to retrieve these facets on the crystal structure to understand what is the composition here at the facets. Now let's see these facets, this HKL index. Unless two Ks, facets number 1 and 7, that is in line with the facets of the unit cell, let's say it's the facets that we would expect if we have an hexagonal prism with an hexagonal base. For all the other facets, we have HKL index related to planes that are inside the unit cell. This is the unit cell. That are inside the unit cell. This number, again, we did this analysis for several crystals. These numbers are not random numbers. It is recurrent in the analysis of also other crystals that we analyzed. Now what we see, that all this plane belongs to the wall of the hexagonal channel. What we can learn from this data? So we have a unit cell that has a 37% of porosity, 37% of empty space. So we have a low molecular density, and we have an inhomogeneous distribution of this molecular density, because the channels are in specific position that is inside the unit cell, but also at the edges of the unit cell. In other words, what we see is that the edges of the mathematical unit cell is not the edges of the molecular unit cell. This what suggests us that the front growth of the facets can be different within a single facet, but also within a portion of the facets. Due to the presence of the channel, the attachment of a further molecule will be more favorable where we have a high density of molecule, and will be less favorable where we have the channels. This fact can induce the formation of this reentrant angle. But again, this reentrant angle perfectly follows the symmetry, because the molecular packing has an intrinsic symmetry. So in this way, we can explain why at a morphological level we have this convex angle, but that perfectly follow the link of symmetry from the molecular packing level to the morphological level. With this, I would like to conclude my talk. I hope that I convince you that unexpectedly moths are a very good class of material to shape. We can generate very complex morphology, by just using the basic building blocks, no additives, no surfactant, nothing. Even more, we can generate morphology that has a curve feature. We can observe paradoxical crystallographical phenomena that are paradoxical not just for MOF, but for, in general, for the interrange of organic molecule. And somehow we think that these phenomena at morphological level are strongly linked to the open-packed crystal structure of the MOF. So this pushes us to further investigate this class of material, but it's also possible that this occurs in other class of porous material. With this, I would like to conclude. I want to emphasize that this is not just a thanks slide. This is a piece of my life. I left Weizmann Institute 2 months ago. Currently, I'm an assistant professor in Italy, in Rome La Sapienza. But I was in Weizmann Institute in the group of Mirko van der Boom and Mika Lav for 7 years. And this was my daily family. And I would really like to thank Milko, Mikal, all the members of the group, all the staff scientists of the Department of Chemical Research Support for their support and guidance. I would like also to mention the huge expertise and work of Dr. Linda Shimon, that is responsible of the X-ray, single X-ray analysis. Dr. Lothar Uben is responsible for TM data diffraction, and Vlad Brunfeld that assists me with the microcomputed tomography analysis. These people help me to shape not just my crystal, but also myself as a scientist and as a human being. Last but not last, I would like to thank you all for your kind attention.
Thank you for the beautiful talk. Now it is open for questions and comments. So please.
Interesting work, Chiara. So my question is, in your first part, in tuning this morphology, so in that, is it just the procedure having a radical that is important, or it is also the structure of the radical? Suppose, assume that you created a radical using dimethyl acetamide instead of dimethyl formamide.
Yes, for sure,
How
for sure.
it will
This kind of synthesis is very sensitive to each small parameter. If we change solvent, probably we drastically change even the crystal structure. Here, the reason behind the use of DMF and chloroform is that the chloroform helps the solubilization of the ligand, and the DMF, during the solvothermal synthesis, generate a basic environment that help the pyridine to be available for the coordination. So, but for sure, if we change solvent, things can drastically change.
So, great talk, fascinating crystals. But I also have a question about DMF. It's used almost always in MOF synthesis, and so do you think that this radical generation is a lot more common phenomenon and influence on crystal structures than people appreciate?
I also thought a lot about it, because also MOF usually often is growth through sonication process, mechanochemistry. And I think that this fact can be strongly overlooked, so that there could be a chemical effect of the sonication and not just a mechanical effect, as it is reported. And I started to think about this DMF radical. Looking at the literature, it's not something unknown. It's a very old work. So I really think that can be an effect that is in other systems just is overlooked.
Thank you.
Thank you very much for this question.
Thank you very much. Very interesting talk. I'd like to know, you measured for your petal crystals. They seem single crystals from X-ray diffraction, right? So, but you have these domains. You have inter-domains regions that might be fuzzy from a single crystal perspective, or on the other hand, very interesting for some application. They look like defective part of the crystal or something like that, so they might be useful for catalysis, for example. I don't know, something like that.
I completely agree with you. We tried a lot to analyze what happened at these edges. For example, I was thinking about screw dislocation. That is a common now, well-assessed phenomena for generation of chirality at morphological level. We had a big problem of this crystal, that they are too big to put under the TM and to see what happened in this region in which we have the switch from a domain to another domain. On the other hand, microcomputed tomography has not enough resolution to see such a details. I was also astonished that we could, in general, get microcomputed tomography that we had a good contrast. So for this kind of analysis on the surface, on the defect, in order to say something reliable, we really need TM. We tried in many ways, cutting by FIB, cutting by microtome, but we were strongly damaging the structure. So I cannot say anything about the details, but you are completely right that this feature can be used to trigger catalytic process.
Great talk indeed. For the first part, there were in the beginning those plates. Can you say what is a code that tells them to stop growing and start assembling? Is it just a density thing, or there is something that really stops the growth of the
domain?
The isolated the plates that you get in the beginning, in the first part.
The first part, the hollow structure?
So before that, you start in the initial, like in the first hour or so, you get plates, and then they start to assemble and merge, right?
No, they dissolve. They redissolve, and a cylindrical structure start to grow.
It's not just the merging of.
We think, okay, that kind of platelets were too small to have the crystal structure. So we cannot say we don't have single crystal X-ray. But for example, looking at the Raman profile, the profile is different. So this tells us that the crystal structure of that parallelogram structure are different from the prism that evolved later. And what we observe is that this small structure redissolve and something else form. So they are probably kinetically variable structure. That
so you don't think that they first merge and then change the structure, the inner structure?
In this case, I would say no. But in other MOF that I'm working with, I have this sort of feeling. But it's just a feeling. I don't have data. But in this case, I really think is a redissolution and recrystallization process.
Okay, thanks.
Thank you.
All right, I think we're kind of in a coffee break time. So just before we thank Maria one more time, just quick announcement. So we'll cut the time by 10 minutes. So the plan would be to resume at 15 or 3:55. And with that, thank you, Maria.
Say a special place to go.
this time giving goodbye, goodbye. Oh, I'm a man of many wishes. I hold my premonition misses, but what I really feel, my eyes won't let me hide. 'Cause
want to jam it with you. We're jamming, and I hope you like jamming too. Ain't no rules, ain't no law, we can do it anyhow. Cause I will see you through. Cause every day we pay the price with a little sacrifice. Jamming till the jam is through. We're jamming. To think that jamming was the thing of the past. We're jamming. And I hope this jam is gonna last. No bull can stop us now. We neither beg, no, we won't bow. Neither can be but no sword. We all defend the right. Judge our children must unite. Your life is worth much more than gold. We're jamming, we're jamming in the name of the Lord. We're jamming, we're jamming where the strife from your holy Mount Zion, holy Mount Zion, just seated in Mount Zion, arrows of creation, jamming, what you want. I wanna jam it with you. We're jamming. I hope you're jamming too. It jumps above my pride. Truth I cannot hide. To keep you satisfied. True love that now exists is the love I can't resist. Jump by my side. Jamming and jamming and jamming. Jamming and jamming and jamming. Hope you like jamming too. So jamming, I wanna jam with you.
Between the eyes of love, I call your name. Behind those guarded walls, I used to go. Upon a summer wind, there's a certain melody takes me back to the place that I know. On the beach, down on the beach, the secrets of the summer I will keep. The sun of time will blow a mystery. No one but you and I underneath that moonlit sky. Take me back to the place that I know. On the beach. Forever in my dreams, my heart will be hanging on to these sweet memories. A day of strange desire
night that burn like fire. Take me back to the place that I know. On the beach. Down on the beach. Down on the beach. Yeah, yeah, yeah. On the beach.
More and more, you're kissing like a half-open door. I can't get in. You stopped me just before I began, and it hurts to be in love when you never get enough. Oh, it hurts to be in love. This endless search keeps my body right on the verge. We touch and then I wanna do it over again, and it hurts to be in love when you only want me half as much. Oh, it hurts to be in love. I'm always worried you think I'm pushing too hard. Oh baby, it hurts.
excuse me. Yes. I hope everyone come back from a coffee break. So next speaker is Professor Igor Sokolov from Tufts School of Engineering, USA. Please.
Okay, thank you. And thank you, organizers, for this opportunity to expose what we are doing to your community and expose your community to me. Because I think definitely there is a big overlap, and hopefully there is future collaboration. Actually, so first, like literally maybe like a few words about what is we are doing, because it's not really for organic crystals is my main focus. My main interest is the physics of cancer and aging, and we develop new methods of imaging and data analysis pretty much, and AFM of soft materials is one of them. So also we develop new materials, and actually that include organic crystals, and thinking about listening talks and thinking about it, actually I see more and more that we actually have in common. We actually even try to grow for organic crystals out of cellulose acetate, but we fail to find anything interesting with those systems, but anyhow. So today I will focus on AFM of soft materials. But before actually listening to previous talks, I actually have to say that we actually have rather a similar kind of interest in formation of crystals. And this is, I wouldn't call this organic crystals. This is a mix. It's called mesoporous materials. It's when you have template using some amphiphilic molecules, which are then rigidified using some salt gel precursor. And the mechanism is actually very peculiar, because if you look at the type of shapes we are getting, this is like very similar, even like more complex than the previous speaker showed, including helices, which show definitely some chirality. And I have to say that we actually understand clearly all these mechanisms these days. And they are quite different from the previous talk. But it's kind of interesting. So it's all porous. So if you look, we can make films out of it, because this is like solid silica coated with these films, which are, again, nanoporous. Porosity is well-tuned with using different size of templating molecules. And the mechanism, this is actually simply a fun. It's an electron microscope picture, and the different colors are simply different morphology, internal morphology of, I wouldn't call this even crystalline, because long-range order is at the range of 3 nanometers. I mean, building units is, I don't even think how to call it. It's essentially nematic phase of liquid crystal. And the mechanism is actually, I was surprised that people call a mechanism that I thought was classical, but in your community it seems it's called non-classical. It's when you first have nanoparticles created, like primordial building blocks, which are fused together and create crystals. That's what we always observe like that. But in the case, of course, I mean, if you have a very low concentration, or if there is some biological active material, then you definitely should observe different as well. But in our case, we always do the synthesis using supersaturated solution to start. But anyway, so that's simply kind of a note. If you have any interest in it, or because we have like quite a lot of use of this material. And so I would be really glad to chat with you about it as well. But now about AFM. So the outline is very brief, literally, because a lot of people use atomic force microscopy. And then about 2 literally very recent modes. One is called ringing mode, and another is FT, which stands for Fourier transform, like the same, like FTIR. And nano-DMA. DMA stands for dynamical mechanical analysis. So what is AFM? And AFM is essentially a device which is very easy to understand how it looks like. It's something in which you have a needle, a very sharp needle touching the surface, and very kind of crude way of explaining it, as soon as needle deflects by the action of various forces, laser, typically a system which is reflected from the top of this cantilever, can be detected by a computer. And as a result, you can see some collection of these deflections or some other signals on a computer, and it's usually coded in the color, like brighter means higher. But this actually description is extremely misleading, because atomic force microscopy is not really microscopy. If you think about microscopy, there are zillions of other microscopies way, way better. Atomic force microscope allows you to really record and visualize maps of physical properties and maybe chemical properties of the surface. And from that point of view, it is really unique. So probably the easiest way to understand force microscopy is think about it as a finger of a very, very small scale. And you can do with this microscopy exactly what you can do with your finger. Like a blind person touching the surface and feel how it looks like. Or you can put some magnetic stuff and literally feel magnetic field. You can put some glue on your finger and feel magnetic stuff, chemical stuff on the surface. You can scratch the surface, looking at the wearing of the surface. You can push and feel the elastic properties, or you can make it conductive and try to electrocute yourself. And so all that implemented at various different siblings of force microscopy already. So also this microscopy allows you to see from the optical scale, and this is indeed organic crystal which was synthesized in space to simply decrease number of defects. So we can see this is like 12 microns by 12 microns, which is perfectly optical visible. You can go to suboptical resolution and see molecular resolution. What you need to do essentially just zoom in the microscopy. So that was classical force microscopy. Now ringing mode. This is a relatively new mode which allows you simultaneously to visualize, record at least 8 different channels. Of course, if I only start telling you about the channels, it will be all the time consumed. So I'll give you just highlight a few. And first, I show you simulation. Simulation of what is this microscopy is doing. So in this mode, essentially here you have motion of cantilever up and down. And when the probe goes up, it's not specifically pull off so-called neck height. And we can measure size of that neck in this mode. This red stuff is molecules which can actually simply fling on the surface, and we can measure the size of those molecules very precisely. Not directly, but I'll show you how. And that's actually how it's done while rastering across the surface. So each touch, you can record this information and create a map. Oscillation, vertical oscillation is pretty high, can be, what is implemented these days is up to 2 kilohertz. So this is pretty fast compared to some other vertical oscillating modes, like so-called force volume modes. So that's why I think this is interesting, because this is visualization mode. And I'll simply give you one feeling why this mode is very advantageous compared to other. This is like so-called restored adhesion. And here, I think you barely see it, but let's see if I can really increase it in the size. So what happens after disconnection of the probe from the surface? Let's see if I can really use laser pointer here. No, that's essentially what happens is zing, and this is why it's called ringing mode. Probe disconnects, and then cantilever goes up and down, ringing in its natural resonance frequency. And it turned out that this ringing is a perfect example of a damped harmonic oscillator. So the physics of this motion is perfectly known. So we can simply try to use the entire curve to restore these like amplitude of the cantilever towards the time it was disconnected. Why we need to do that? Because disconnection, it's a very tiny, very minute time, when it's happening. If you want really to do it extremely accurately, you need extremely high digitalization card, which is impractical these days. So what we can do instead, we can simply use a lot of these points and average them using this simple formula. As a result, signal to noise enormously improved. And I'll give you just an example, simultaneously recorded this restored adhesion and standard adhesion, which was before. So I just give you like a bigger picture of, I don't know if you really see it, but you can see like much more like finer details in this mode compared to the other. Increase of resolution depends on, of course, rigidity, and I'll show you specific examples, numerical, how much better resolution you can get. And again, we are speaking not about images of the surface. These are maps of physical properties. So you can actually see, for example, aging of low-density polyethylene. These are kind of how they see after creation. And then after, well, in this case, several years. You can probably, I cannot really do it like simultaneously, but you can see lamella, which is formed, which is definitely a different phase. You can even see some kind of interesting spots, which look like it's crystalline. Why do you think so? Because adhesion is very low. Adhesion is low, it's when you have usual deformation is small, or area of contact small, because adhesion is proportional to the area of contact before disconnection. And if it's smaller, so it means it's harder to deform. So that's what like happening, for example, for this low-density polyethylene. So we also can see what happens to the surface, actually height of the surface, at different points of physical processes. For example, this is a mix of low-density polyethylene, these round spots, on the background of polystyrene. And cross-sections here are shown of what's traditionally called height, literally what is classically shown as an image of atomic force microscopy. Number two is so-called zero force. Because when classically you image something, you push the surface, you deform it. So what you actually see is indeed deformed surface. When you have zero force, like that's technically you don't really have much of deformation. Indeed, if you have adhesion, so you still have some. Three, it is the height of the neck. So how a surface look like when you, at the moment of disconnection, when you pull off this neck. And you can see that it's actually quite different for low-density polyethylene. It's like pretty substantial, and it's in nanometers. So that's another beauty. So it is absolute values. You don't need to do any special additional calibration. You can see these numbers literally directly measured. And number four, it is the height of the molecules. You may think that this is pretty noisy. It looks like a noise. No, it's actually simply extremely high resolution. And if you look at, well, here it's just not that visible, but if you look, it's actually not random. There are some areas which you can see these dangling bonds, which we are actually pulling off. And these are like pretty repeatable. So that's why like we hope to use these modes, for example, for something which is quite important for something, for example, like medicine. In medicine, you cannot tolerate errors, or at least like irreproducibility. So, but anyway, so and interesting if you compare again for low-density polyethylene, you can see the whole this range of possible interesting knowledge. And polystyrene is like durable material, solid, like nothing. So that's another interesting comparison. That's simply like example of multiple channels similar, because you can, as I said, like you can get 8 additional channels, additional to actually what already can be recorded, including height, adhesion, and rigidity. And this is interesting, again, if you look at the neck height, you can see that actually neck height is non-zero even for polystyrene. It's actually around here, around like 15 nanometers. while dangling bonds actually pulled like pretty noticeably. Neck height is almost zero. It's like the bottom one, 0 for polystyrene. But we still pull off some molecules, while for polystyrene it's quite higher. And again, you can see even like within for this 1 submicron resolution, different phases. Regretfully, we don't really have comparable, like for example, Raman with that much of a resolution to say which phase is this. But I'll show you examples where we really can. But now, if you think about 8 additional channels, for human eye, or even for human brain, it's actually too much. Even like looking at 2 channels together. This is a surface of red blood cell infected with malaria strain, a malaria parasite. This is how a regular topography of standard AFM look like. Well, you just, okay, some bumpy. But this is a combination of neck height and molecular size. So you can see that these bumps, they have very different membrane, and there is no molecules of glycocalyx, for example, coating these bumps. So it's definitely different phases in some sense if you think about biological membrane as something like that. Like it's not really crystal, but at the same time it's like 2-dimensional array of very well-ordered molecules. So this is another example of topography of a cell. This is a melanoma cancer cell, and you see that distribution of molecules on the surface highly non-trivial. So the other model is disconnection energy loss. And this is something different because in typically force microscopy, it's already calculated as a difference between approach and retraction curve because of various time-dependent effects like viscoelastic losses. You can calculate some losses. But in our case, we calculate only after disconnection, after this probe starts flying away from the surface. And during that very short period of time, probe loses energy, and we calculated this energy. It's much lower, but resolution is much higher. And by some reason, it's much less of artifacts. For example, this is multi-layered material. It's actually human flakes, skin flakes. And you can see that disconnection energy losses actually show you a very nice layered structure, while the classical dissipation channel gives you, well, quite a lot of artifacts. Again, we are not up to improving the existing AFM, we're just suggesting something new. And this seems to be like more realistic. And of course, like phase, because when you do oscillations, you always can say, okay, there is some phase shift because of losses. And we can calculate this phase shift. And this is an example, again, this almost like calibration standard polystyrene, low density polyethylene. And you can see clearly this differentiation between these 2 polymers. Of course, it's a little bit trivial, but if you look at small dots on polystyrene, it's a question like, is it polystyrene or it's low-density polyethylene? And looking at the phase, you can say it's a polystyrene because it's exactly the same phase. So speed, that's maybe a little bit technical, but compared to regular by the way, this family of modes in general called sub-resonance tapping. And probably one of the best known mode is peak force tapping. And compared to that mode, ringing mode is about 20 times faster. And this is a lamella of a mix of 2 polymers mixed together. It's a polystyrene mixed with polylactocapron. And you can clearly see lamella. And each you scan with 1/4 hertz up to 5 hertz. And you can clearly see that structure still. But in classical mode, you see it's pretty much like washed out. And as I said, there is a very simple explanation why this mode has a much higher resolution. This is the same mode, the same simultaneously taken images, classical mode and ringing mode, with this adhesion. And because the signal is measured in ringing mode at the moment of disconnection, while in regular height images, its area of contact is much higher. And resolution first-order approximation, resolution in force microscopy is the area of contact. So if you compare literally through the analysis, you can see that on pretty rigid material, half a gigapascal polyurethane, we have 5 times better resolution. 5 times maybe not a lot, but if you remember, last Nobel Prize for super resolution was for 4 times increase in resolution. Although, of course, like competing with optical microscopy would be ridiculous. A force microscopy is actually a very interesting technique because it can be extremely gentle. It can really scan with forces as small as 50 piconewtons, which is the force which in regular conditions needs to break 1 hydrogen bond. So that's as small as possible. It can be. It can actually create multiple pressure of multiple metric tons per square centimeter. And this is example of, you can measure not only very soft materials, but relatively hard. This is composite material. It's shales with organic bitumen mixed with inorganic various crystals. And you can see that a force microscope in this sub-resonance tapping can actually measure something around 20 to 30 gigapascals. It's a little bit tricky to find such a high modulus. You have to be careful, but it is possible. So all that information can be recorded with force microscopy. And it's again like much higher resolution compared to, for example, force volume mode. It's simply because it's much faster. Much faster than you can do. You can make, for example, imaging of degradation of polymers in, well, in this case, in water. So a low-density polyethylene, when you have a thin film, is actually pretty, I wouldn't say dissolvable in water, but it's unstable. And you can see that it's kind of an interesting structure of degradation. So it's literally start to, well, essentially dissolve, but it's almost like erosion. So to give you a feeling how small you can go, these are molecular coatings on cellulose acetate nanoparticles, which each has about like 50 to 70 nanometer size. And you can go inside of these particles, make a zoom, and see not only the distribution of the adhesion, you can see neck height. Neck height, it means you literally look at beneath this molecular coating on the surface of cellulose acetate, and you can see distribution of the neck height. If you have any crystallinity, you would see that immediately. And disconnection distance is height of the molecules that you have on the coating. That's, by the way, gives a huge boost, well, at least I hope, for nanomedicine, for drug delivery. Because right now, it is a really pretty much dead area because targeted drug delivery is dead because as soon as you introduce it to the blood, particles aggregated and cleans by the pretty much like all these cleansing organs in our organism. And our hypothesis is that the particles typically have some defects in the coating, molecular protective coating. And this technique allows you to see these defects. And we already have examples, defects, no defects, and biodistribution is hugely different. For another part is FT nano-DMA. This is where we actually try to see more phase segregation in, well, in polymers, you can in principle always create some crystalline subphase. And is this phase is more rigid or less rigid? It's actually, there is no, usually it is softer when you decrease crystallinity. But it's known example, for example, in copper, so-called like, I think it's called rigidification or something like that, stiffening. If you try to break copper wire, for example, you'll feel that it gets more rigid. When you try to bend it, you create more and more defects. So that's why, like, this technique, I think, definitely should be able to distinguish between different phases. We don't have a good sample, and that's where, if you have one, so we will be glad to actually look at it. So, but how viscoelastic or time-dependent properties measured in general? So it's a little bit of like mechanical engineering. So there are multiple like creep, stress relaxation measurements, creep compliance, but storage and loss modulus measurements are probably the most application friendly because they are almost model independent and experimentally friendly. In this technique, you literally develop some contact and then you oscillate with some different frequencies and see what is the response of this indenter to these frequencies. And that's where we decided to develop FT nano DMA, and it works as follows. We essentially develop initial contact, but then, in contrast with the existing DMA, we send all frequencies at once. This is already a technique existing in electrospectroscopy, in infrared spectroscopy. So the beauty of this is not only because you can do simple acceleration, just measuring these frequencies on time. It also, because during the contact of soft material, pretty much all organic, you have some is the stress relaxation of creep, which is area of contact is time dependent. So, and as a result, you cannot really do good measurements. Technically, I would say there is no good theory to even recover. And even then, it's like if you increase area of contact each time, you lose resolution. So it's much better to do it very fast. So we kind of optimize this technique. For example, if you measure 10 frequencies, so it's sufficient for almost like all materials we observe to simply avoid that substantial change of area of contact. We do it very quick measurements. As a result, we don't need to wait until all this area stabilization. And this is a classical for all nano-indentation technique. As a result, we can really do acceleration very substantial. This time we're speaking about hundreds of times, not really just 4, 3 times. And this is just, by the way, it's a picture of pumpkin seed, living cells, and each of the pixel here is 21 different values. So technically, we would have like 21 different pictures. Storage modulus, which is equivalent to Young's modulus, or kind of how rigid material it is, and the loss modulus as a function of different frequencies. Loss modulus is like what is responsible for loss of energy. And this is just, again, like some beauty of this technique. It gives quantitative results. Again, it's not just kind of some relative. If it's quantitative, you can use it for something, which later I will tell you, 21 channels here, 8 channels before. So it's, again, like human cannot really comprehend it easily, so you need to use something like machine learning. And it's actually extremely powerful, turned out. So it's much higher spatial resolution. Again, we are speaking about like more than 100 times increase in spatial resolution because we are not waiting for area relaxation. And time relaxation is also very fast. Again, like more than 100 times, we can do it much faster. For example, to take a picture of that pumpkin seed, if you use a regular nano-indentation technique, it would require 22 days. Which is, if you try, anybody tried indentation, it's just simply like because of thermal drift, it's impossible. And that picture was obtained within 1.5 hours, which is like definitely doable. So that's simply maybe like example of, again, polymers with some features, human skin, in which you can see features around 50 nanometers. So it gives you direct kind of evidence of resolution. Theoretical resolution here is 10 nanometers. And again, it's only because we need to work in linear regime. Because it's very easy to make super sharp probe, but it creates you a nonlinear stress strain. And technically you can measure something, but it's not, well, not repeatable. Time resolution. This is a little bit like I skip in the explanation. This is like clouds. So don't worry. It's simply because each time we measure something different, and it simply gives you a feeling that we can measure, for example, change of these properties, mechanical properties, with steps of here well, here specifically like 2 seconds, but we can go to 0.7 seconds. And this is specifically for polyurethane. And this is example of low-density polyethylene in which there are 3 different phases. We can see these phases using, for example, Raman confocal imaging, polarized imaging, and we see that there is this kind of pinkish, these are crystalline, they are the hardest one, then semi-crystalline or anisotropic phases and amorphous phases. So, and something like that we see in this mode. For example, and as I said, we can do different frequencies. For example, we can even look at the static modulus. But if you look at a static modulus, yes, you can clearly see crystalline phase, amorphous phase. But if you try to do the same at 255 hertz, so you can see that actually it's almost like, so it should be here, yeah. It stays here the same, but some other parts actually behave very differently. So it tells you that at first glance you can say, okay, yes, rigid, more crystallinity, but it's way more difficult, more complicated than that. And here again, what I want to say that this technology gives you way more information than just kind of a linear analysis. Yeah, more crystallinity, more rigidity or something like that. So how it can be interpreted, how much information it can be translated into the, for example, understanding mechanisms or defects. Defects surely, it's not like usually very localized. Mechanically, defects should be seen quite surrounding. And when you do deformation, remember that we need to develop initial deformation. But we can do it in different heights, different forces. So we can speak about, in principle, tomography if you do that at different forces, like at different levels. So that's why I think it's definitely interesting to look at formation and behavior of different phases. We can change temperature, for example, here, or add multiple, we need only transparent medium. This is just a picture of cell. Of course, cell is not crystal, but it just gives you a feeling. That is an optical picture of the cell. And this is mechanical picture. If you literally want to compare, there is some resemblance, of course, but there is so much of more information in the mechanical part, which we have no clue what it is. Right now, we try to torture some biologists, but they pretty much like, you need to translate rigidity into something biological terms. Then they can answer your question. But at this point, like we know how to address it, but it's a very laborious thing. You can disturb like potential some organelles using known biological methods, but it's maybe like taking forever. So in summary, like we have like literally 2 ring mode and FT nanodime, which is right now it is ring mode is already commercialized by Bruker, or at least it's available through Bruker. FT nanodime it's already commercialized by a smaller company, and just only like a few more words about how you can handle that much of information. And technically, we are thinking about multidimensional spectroscopy. Multidimensional is not just a nice word. It's usually spectroscopy is like a linear. You have, for example, X-ray versus angle, or for like an Raman versus wavelengths. Here you have one piece of information, but from different dimensions, like rigidity, adhesion, like some molecular sizes. And if you try to combine it, it's pretty hard because human brain doesn't work that way. So that's why we need something like machine learning. So we would call this also following biological approach in which they use, for example, different genes do different things. Activation of genes and study of that called genomics. Here, because we are speaking about surface, we call this approach outeromics, like outer surface. Well, it's not really super nice word, but we didn't really figure out anything better. So, and if you think how we can really do characterize images, for example, you can use surface parameters which are used in engineering, like roughness, fractal properties, and so on. It's like, in total, like 37 different parameters. So if you have in ringy mode, as I said, 8 channels, but it added to already existent channels, so altogether it's 14. So, and even if we really get rid of a lot of parameters and say only like important one, 20, 30 parameters, we still have like 30, almost like 400 parameters. With FT nano DMA, we have like so many parameters, so it's already exceeded a number of genes typically analyzed. So that's why we go for these similar approaches, and this is just an example of how you can combine different channels to distinguish between different cell phenotypes. Again, like we're looking at physical properties of surfaces, and in this case, instead of like saying, okay, like we want spectroscopy of polymers or crystals, we want to look which cell is, for example, cancerous or less cancerous. In this case, it's like both cancerous, but one is more aggressive. And when we combine all channels, we actually have accuracy of 94% using single cell. Single cell DNA gives you 80%. So this is a really scary result. Because of course, like any professional genomist should kill me. Because it's just like, it's too good to be true. But definitely it's only one indication and we need more manifestation. But it gives you a feeling that how more accurate this spectroscopy can be. And one of, right now, really crying necessity, if, for example, we have some well-defined crystal with multiple phases, and we can train this system and then try to recognize, as using regular spectroscopy, machine learning here is simply like it's a way to handle this amount of information. But technically, it's spectroscopy. And we can really say, can we recognize each particular phase? The resolution here can be down to 10 nanometers. Well, actually, ringy mode gives you even like 1 nanometer. I'm not sure if ringy mode is sufficient or not. This, for example, is only ringy mode channels. So just give you a feeling of what can be done in the future. So that's like, it's another. So in conclusion, is simply, these modes can give you like 8 additional channels, 21 channels in FT nano DMA. It can provide quantitative results. And it's a must for incorporation of machine learning algorithms. So, and in principle, we can speak about this multidimensional spectroscopy for identification of crystalline phases, defects, or maybe even, again, it can be done on time, so-called longitudinal study. For example, aging or degradation, or even polymerization. And as a result, you can, in principle, approximate to the future. So, of course, this all done just by multiple people. Well, medical stuff is done definitely with medical collaborator. But Renato Agoliera, who is in Intel right now, Maxim, who is right now, he actually stuck in Russia with all these events. And, but he was my postdoc for a very long time and a very talented graduate student. Actually, there was one guy who simply high school student. It's unbelievable. At one point, I simply forgot he is not a graduate student. I asked him to calculate something, and he actually learned everything by himself using Wikipedia. It's very dangerous, but actually, he did it correctly. No, it was pretty much unique. Okay, so that's pretty much it. And again, like if you have any interest or any questions or collaborations, we would be really glad to look at your samples and think about future spectroscopy for development of these organic crystals. Thank you.
Thank you for your beautiful talk. Are there any questions?
Hello. Yeah. Very nice. You showed us maybe AI, but also human learning, right? With this school student. No, my question is about the resolution. You claim to have like fast enough not to get the relaxation around the data point. But I really have a question about it. I'm not sure that this assumption is correct.
Oh, we check it, of course. During the measurements, we check how much area of contact changes. And
it's not, I don't talk about the area of contact. You may have a specific point on your tip, but once you really take you pull out, the surrounding must, react. I doubt that you can.
No, of course, if you functionalize the probe, yeah, that would be the case. But in our case, a probe is not functionalized. And in principle, you're right, if molecules, every time, because of the Brownian motion, molecules can touch the probe differently, so you have distribution. So it's, of course, you're speaking about averaging of multiple touches, which, by the way, is interesting information by itself.
Yeah, I guess so, yeah.
Mm-hmm. Mm-hmm.
Thank you. Yes, it works.
Thank
you for the beautiful talk. I have a question. This ringing mode, is it can be incorporated in any Bruker system? What are the requirements?
It can be pretty much as an add-on to any existing microscope. As a proof of the concept, we developed it originally for multi-mode by Digital Instruments, which was 20 years old. And it worked even better because that microscope is actually very good.
Of course, that was the best one, right?
Yes.
I have another question. Actually, I was a bit confused. At the beginning of your talk, you say your understanding of non-classical nucleation is different than the community. What did you mean by that?
Oh, because here I thought that classical, it means when you have not really nucleation, but growth of crystals by depositing atom by atom or molecule by molecule. But what we observe, it's from supersaturation solution, we have always, I thought it's actually classical, that you have these primordial particles created. So it's a result of this Marangoni effect and Oswald wrapping. So you minimize, I think it's called also in chemistry, chemical potential, which is a combination of enthalpy and when you simply look at it, and there is a tiny minimum for the size, which depends on the material. For example, for metals, it's like around single nanometers. For organic crystals, would be like 10, 20 nanometers. And those guys fuse together and dynamically then just keep growing. That's what, I thought it's classical, but here look like it's called classical.
I think the distinction, at least from my perspective, is like, well, not my perspective, but what is from heterogeneous growth, right? It's that when you have an ordered nuclei, when your nuclei is already like particle by particle attaching and it's already ordered in the crystalline shape, then that will be like the classical version. And when you have an amorphous nuclei forming first and then transforming into the ordered one, then that will be non-classical.
I see. Yeah, but from that point of view, still we observe non-classical because it's aligning later.
Yes, that's the aligning later.
I see, thank you. Mm-hmm. Mm-hmm.
So I'm sure you have more questions, but we have not so much. We don't have so much time. So please discuss with him later. Thank you again.
Thank you.
So next speaker is Professor Alexei Tivanski from University of Iowa, USA.
I got it, I think. I just tried something I shouldn't have. Okay. All right. Okay, if you thought that you had enough AFM, so I do have a little bit more AFM, but my AFM is much more simple. So what Igor was referring to, it's my students doing it for hours and hours, so more simplified version. But anyway, first I just want to one more time thank Panche and everyone else in his group for organizing this symposium. It's wonderful. A lot of, as Len mentioned as well, nicely organized social events, and it's a beautiful country, so thank you again. All right, so with that, very briefly, in my group, we do a variety of different things and things that are completely unrelated to this field, so do a lot of work in environmental atmospheric chemistry. But from the perspective of this field, a lot of effort in my group is focusing on a variety of different materials, where primarily using atomic force microscopy, we study mechanical and electrical properties of different solids. If I would say the central question of trying to understand the effect of size and morphology on those properties. And so what I hope I will be able to illustrate to you today, using a couple of select examples, how size reduction to the nanoscale and also in a couple of cases difference in morphology do affect both mechanical properties in particular and also functional properties. And one of the things that I want to highlight one more time, I think I mentioned it at the introduction, that it's very important because of the expectation of size effects to be able to study in nanocrystals, ideally individual nanocrystals directly, because sometimes extrapolation from macroscopic solids towards nanoscale can be problematic. And so in that regard, one of the techniques that we are using a lot is atomic force microscopy. I'm not going to spend time explaining it. Igor did a fantastic job. The only thing I just want to mention is that we do quite a bit of work where we measure electrical properties of organic solids and nanocrystals using so-called conducting probe AFM or conductive probe AFM, although I'm not going to talk about this today. And also we have a possibility of a variety of environmental controls. So we can do it under liquids, solvents, gases, or in air. And we can also control relative humidity, so we can study uptake or hydration of crystals, for example, and we can do it as a function of varying temperature. Okay, so this is a busy slide. You don't really need to look at the equations. So I just want to mostly ask you to look at this central. This is an example of so-called a force plot, where you look at the force approaching, touching the surface, indenting into the material. And this is only approach part is shown. And this is so-called AFM non-indentation approach, that slow approach that Igor mentioned previously. But the bottom line is that you can use a variety of different theories. And the advantage of using this approach is that you can really fully understand the range of indentations where you have elastic versus plastic deformations and so on. So I'm not going to talk about the hardness today, but this is also something that you can quantify with non-indentation approach. And so commonly we use so-called JKR elastic contact model. So again, all the equations are there. Bottom line, we can directly measure all of the properties that are relevant to this model. And really the key thing that I want to mention also is that we can determine properties, mechanical properties of solids with a very small and controllable extent of indentation. So as shown in this example, we can indent 10 nanometers, and we can quantify, for example, Young's modulus of polymer fuel as an example, right? And the reason it's important because if you look at how traditionally mechanical properties are often measured, they rely on so-called indenter, and it's a wonderful technique. The only issue is that you need at least a couple of 100 nanometers of indentation, right? And so you can immediately recognize the issue if you want to apply that for nano-dimensional materials that have dimensions below the required indentation, okay? And so in that regard, atomic force microscopy non-indentation is really suitable for this kind of work. Okay, with that, I want to very quickly give you 3 examples. I hope I will be able to do it on time. So first one is collaboration with Len McGillivray and Mark Arnold from University of Iowa. And this is the work where we looked at a series of co-crystals, which is shown here, using the work that Len mentioned this morning, this template modulated approach, where you can generate nicely hydrogen-bonded discrete assemblies. And so in this case, what we wanted to do, we wanted to do 2 things. First, we wanted to explore how substituting resorcinol either unsubstituting or using dichloro, dibromo, diioda, influences the mechanical properties. That was number one. I think at the beginning of the conference, there was a question about the halogens and connection to polarizability. I thought it was really excellent because this is an example where we do establish that direct connection. And also explore the size effects, okay? And so what we did, we synthesized big macroscopic crystals and nano-dimensional crystals. We got the crystal structures, so luckily 3 out of 4 were isostructural, so allowed us to compare it, so specifically 1 or unsubstituted, and then bromo and ioda were isostructural, while chloro was not. And so then we carried out our mechanical characterization, and what is shown here on the right are the histograms, left for macro-dimensional crystals, where we generally look at the top and bottom sides because they're nice and flat, so it's very convenient with the AFM. And as you can see, they're somewhat similar, although there are some differences between them. And then we did similar for nanocrystals, okay? And so first, just I want you to look at the comparison. It's kind of listed in this table. And what you will immediately see is that with exception of one co-crystal, the other 3 co-crystals at the nanoscale become more rigid. And we think that the reason is related to the relative number of defects, where a general idea is that if you have a large number of defects, that increases disorder, and that corresponds to softer material. However, what I will also show with other couple of examples, this is not always the case. And so remember, I had this question during the overview, what happens if you have a size reduction, whether it decreases or increases number of defects, and it seems like there is no clear answer, so there are many factors in play, okay? And so this is in terms of size effect, and another thing that we also noticed is that as we introduce chloro, bromo, or ioda substitute groups, we obtain progressively softer material. And this is something that we can relate to polarizability, and we did it in 2 ways. First, we just simply plotted the inverse Young's modulus as a function of atomic polarizability. So we just looked up at the values for this for atoms, and as you can see, we have a reasonably good correlation. I'm not saying that this is implying that this is indeed 1 over Young's modulus is directly proportional to atomic polarizability, but it does seem to work. In addition, what we did, and this is work done by Mark Arnold research group, so they measured polarizability of co-crystals over terahertz frequencies, and they determined the polarizability, which we, similarly to the plot on the left, plotted as 1 over inverse Young's modulus, where one more time, for both macro and nano-dimensional solids, we do appear to have this correlation, okay? So it's kind of, in summary for this part, you can use polarizability as a kind of idea that if you introduce more polarizable molecules, you may have some expectation that you may end up with softer materials. Okay. So the second part is the work that we've done in collaboration with Chris Bardeen from UC Riverside, where we specifically looked at the mechanical properties and photomechanical fatigue of macro and nano-dimensional diaryl-ethane molecular crystals. And this is a really interesting molecule, so it undergoes reversible transformation between so-called open ring, which is transparent, and the closed ring isomer, which is nice and colorful. And so Chris's group, they developed this approach of generating nanowires using the template method. So they have a very well-defined diameter, 200 nanometers, and tens of micrometers in length. And they showed how it can undergo this nice reversible bending motions. Okay? Not only that, the studies on the macro-dimensional crystals show that you can do this isomerization back and forth with repeated UV and VIS exposures many, many times, hundreds of times. And then Chris Bardeen group, they did an additional experiment where they actually used this template with those nanowires in. They exposed part of it, And they show that now if you look at the side of this template, that these nanowires, they can expand, and that generates mechanical force. And so you can envision using this type of approach to generate mechanical work, for example. But one of the things that they discovered is they repeated these UV exposure cycles a certain number of times, then it stopped working. And so this is what is referred to the photomechanical fatigue. And this is where we came in. We tried to really see if we can determine what was the origin of this fatigue. And so in this work, what we did, we used AFM, and we put either macrocrystals or nanowires onto the surface. We exposed from the side, and then we looked at the changes in morphology and then mechanical properties. And again, the beauty of this system is that you know very well, because it changes color, so you know if it's in one form or another. So very briefly, as a result of visible and UV exposure, we saw no changes in the morphology, so they stay the same. And there was no change in the mechanical property after one UV-Vis exposure, so we quantified the mechanical property, and this is the value, 4.5 gigapascal. And then we did the same for individual crystalline nanowire, which is shown here. So it's kind of similar. There is no change in morphology as a result of one exposure. So we quantified the mechanical property. And then if you compare the two, you can immediately see the effect of size reduction. So the reduction of going from macro-dimensional crystal to nano-dimensional nanowire results in 3 times reduction in mechanical property. And this presumably, again, while we don't have a direct proof, we are attributing that in part to increasing number of defects in the nanowire. And then we carried out this repeated, just to see the extent of this photomechanical fatigue, we carried out repeated exposures of visible light and UV and visible light. And so for the macro, after 50 cycles, this is the mechanical properties just for selected few cycles, there's basically no change, consistent with the previous studies. And when we did it for the nanowire, what we discovered after approximately 12 cycles, there is a significant reduction in the Young's modulus. And so what that indicated to us is that we can actually use the mechanical characterization as a means to probe this photomechanical fatigue. Okay? So Young's modulus can be used as a means to follow that. So then if you compare in terms of the histogram, so this is the histogram of Young's modulus before the fatigue was developed, and then this is after. So as you can see, there is a significant reduction. And then if you looked at the force differences, so blue is before the fatigue, and this is the force plot going in and out after the fatigue. So you can clearly see that there's this hysteresis developing, which is related to the viscoelastic nature of the material. And what we thought is going on is this fatigue is a result of loss of crystallinity. So we're forming ultimately an amorphous material, which also is consistent with the idea that nanowires have a higher initial number density of defects, right? And presumably by going back and forth, number of defects accumulates to such extent that leads to a loss of crystallinity. And so then we did a PXRD where we had unexposed nanowires, and then after 10 cycles, as you can see, there is a significant reduction in the PXRD peak, so it's kind of supports the idea of loss of crystallinity. And finally, what we did, we also did a very similar experiment, but now we created amorphous film, and then we did a multiple back and forth exposures. So nice thing about this material that it doesn't, in terms of change in color, it works equally well if it's crystalline or not. And what is shown here in, I think, green triangulars is basically showing after UV and visible exposures, there is no change as expected in terms of the mechanical property. But what was very useful for us is, as you can see, blue nanowires response after the photofatigue, that it starts to overlap. So it was our kind of final, from mechanical standpoint, confirmation that the origin of photomechanical fatigue in these materials is indeed due to the loss of crystallinity. Okay, and finally, very briefly, just another example. So this is in the forbidden area of meta-organic frameworks. I just want to highlight very quickly. So we did an experiment, and this is in collaboration with Len McGivelry, looking at a topical meta-organic framework, so-called ZIF8. Don't want to spend too much time. Just except to say that we also looked at the difference between the macroscopic and nanodimensional solids. And this particular ZIF8 is very interesting because it undergoes so-called breathing transition if you have a sufficient gas pressure. And there were previous reports that gas absorption properties were size dependent. And so we were kind of curious to see if we can explain that in the context of mechanical properties. And so this is what we did. So we generated a micron dimensional ZIF8, and we did the nanodimensionals, and then we did the AFM nano indentation approach, and this is the results. So consistent with our expectation, we see a reduction in the mechanical property, Young's modulus specifically, as a result of nanoscale reduction. And so I hope, just kind of summing it all together, I just gave you a few selected examples, but we certainly see many more of this, that if you decrease the sizes, especially at the nanoscale, then the properties of your material change in the context of, for example, mechanical properties. And so with that, I just want to acknowledge students whose work I showed. So 3 of them already graduated, Telini, Suman, and Teranjiva, and some of the work done with Al, and also collaborations with Len, Mark, and Chris. Thanks NSF and University of Iowa for funding, and thank you very much. I'll be happy to take your questions.
Thank you very much for your beautiful talk. Are there any questions or comments?
Alexei, nice presentation. Thank you. One quick question regarding you showed this 1/E Young's modulus versus the polarizability of the halogen atoms. I see the crossover there. So if we say that for the you compare the macro indentation value versus the nano indentation value, right? So if the nano in size is normally give you larger E, so lower 1/E, but then for the one to the left, it is opposite trend. Do you have any explanation of that? Yeah, this one. The one below
like this
one.
one?
No, the one below one on the x-axis. The one with least polarizability.
Oh, this one?
Yeah, yeah. Rest of it seems to make sense because the nano measurement should be higher than the E value, but that one is opposite.
Yeah, I mean, I don't know. Yeah, I don't really have a good explanation. So, I mean, we were surprised that it works really well. And again, we picked it up from metals, that there is this actually relationship. And I think it just kind of shows that while you can use atomic or actually measured polarizability as a way to kind of have some expectation, but there are so many other factors in play that limits this application.
Okay, maybe the difference is not significant.
Yeah. Well, it's inverse, and so
Yeah.
yeah. So here, yeah, this is maybe, but we can discuss in more details.
Yeah.
later.
Okay.
Yeah.
Thank you.
Thank you very much for the talk. My question was also on this slide. How do you measure the polarizability experimentally?
I think, yeah, it's so they measure terahertz spectra, and then they calculate it, and then they use processing. So it's kind of convoluted. I will be happy to discuss afterwards. But
Okay,
they don't measure it directly, but they do some modeling. They get the electric constant, and then they ultimately pull out the polarizability. So, but it's from absorption spectra at terahertz frequencies, and then with some assumptions they can determine that.
And this you can apply in, like, do you have any constraint of the samples to apply this technique to measure the polarizability?
I would say it's not well-established approach to quantify polarizability.
Yeah, that's why I'm very interested. I'm looking for ways to.
But we did publish this And it does appear to be working reasonably well. So this is the work that is done by Mark Arnold and his students. But yeah, we could kind of discuss it more. It's not a direct measurement, so you have to process the spectra. So, and they're generally really complicated. Yeah.
And other questions? So, okay, so we think we move on next. Thank you very much. Next speaker is Professor Sharmarke Mohammed from Khalifa University of Science and Technology, UAE. Sorry. Please.
Okay, so thank you, Alexei, and thank you all for making this a wonderful program. Thank you, of course, to Panche and his team from New York University, Abu Dhabi, for helping out with all the organization. When I tell people that I'm from Abu Dhabi in this particular audience, I've been getting a lot of congratulations. And then I remind them that I'm actually not from NYU Abu Dhabi. There is more than one university in the city. More on that later. In typical academic fashion, I'm going to revise my initial submission. So this is the revised version of my talk title. So I was thinking how best to put this across, and maybe it didn't work out the best way when I did the initial submission. But really what I want to focus on today is we've all seen examples where people are using ball milling to synthesize new molecules by making new bonds and breaking bonds. But we don't really talk about unstable mixtures, and we don't talk about composites. So hopefully I'll convince you by the end of this presentation that we really need to start looking at them if we're going to be interested in extracting things from the environment and also optimizing properties. Talking a little bit about Abu Dhabi, so this is Abu Dhabi, this is the map of the UAE. So Abu Dhabi is actually both a city and an emirate. It accounts for about 87% of the country's landmass. You could say that we are the slightly richer but unknown cousin of Dubai. My university, Khalifa University, is a relatively young institution. We have a very diverse community that I would just like to emphasize. I think a lot has been said about equity and diversity, and I'd like to congratulate Panche for really doing a good job on that in this particular conference. We have about 28% of our students being international students, coming from about 53 countries. We do relatively well compared to most universities when you think about male to female ratios, both in the student population and in the staff, and that's something that we're very proud of. If you believe in QS rankings, we're in the top 200. So this is my attempt to make my dean happy in promoting our institution. Hopefully he'll be happy, and my team can report back on that. In terms of Abu Dhabi and what it looks like, so this is our campus here. Abu Dhabi actually consists of about 200 islands. So if there is any rise in sea temperatures, we're really screwed. And if we were doing ICOS in Abu Dhabi right now, I think it's fair to say that it would be slightly different temperature. Somebody has actually done the experiment. You could make your own breakfast in the pavement. So if we were ever to invite you guys, you don't need to book a hotel with a kitchen. Just bring your frying pan, and you'll be all right. So my talk today, I just want to kind of just introduce a little bit about the different products that we may be able to get from ball milling. So I think we're all familiar with, complete chemical transformations. I think James Mack did a fantastic job on that. I think, you know, these smiley faces and these sad faces kind of represent where we are as a community in the organic solid state in doing well with these kind of changes. So I think this gets a slightly sort of like neutral face. We do well, but as was mentioned before, we don't really understand what's going on inside the milling jar. Where we do really well, and I think Franziska did a great job in kind of highlighting all these different kind of co-crystals, is supramolecular chemistry using ball milling, right? So I think we have a good understanding of how to make new architectures that way. But we really don't know much about eutectic composites and things that are weakly bound in separate crystallites, not inside one crystal, right? And as we'll see in this talk, these represent a good opportunity in environmental chemistry because actually we see that the solubility changes quite significantly if you can get these composite materials. And that means, of course, separation processes can be made more easier. So before I talk about that, I'd just like to just talk a little about some CN coupling work that we did. So this would be at the very more stable end of the energy landscape. So we got into this because we were interested in optoelectronics. And if you think about the current state of CN coupling chemistry, you know, you're using some sort of metal catalyst to carry out the coupling reaction. Palladium seems to be the most common. So this is the typical cycle. It works relatively well. We think we understand the mechanism. In the solid state, things are a little bit more complicated. There was a report quite recently by Hajime Ito's group where they showed that actually you can get CN-coupled products using simple ball milling, and the yields are pretty disappointing. So you get about 30%. The important thing to notice here is that they followed this up with a later work where they showed that you can actually improve these yields significantly by using some sort of external heat gun source, right? So temperature there, again, going back to what we were talking about in the previous lectures, seems to be very important in driving these reactions. So we looked at this and thought, okay, so obviously this presents like a complicated setup. It's pretty dangerous. If you have students in the lab, can we actually do the mechanochemical CN coupling without using an external heat source and do better than 30%, right? So that was basically the aim in this project. So, why would we want to do that in the first place? So for those of you who are in the PV world, you recognize this molecule. This is probably the most commonly used whole transport material in perovskite solar cells, and this is basically made from solution CN coupling, right? The problem is if you look at the conditions, you've got some sort of process that takes 12 hours, you've got 110 degrees temperature you need, and then after all of that, you have less than 50% yield, right? Not to mention the cost, which I'll talk about in the following slide. So there's a lot of problems with this benchmark material in the perovskite world. Photoconversion efficiency is pretty good, but if you're going through all this to make it and you're spending all this money, it isn't really commercially viable. So the question was, can we make a better material using mechanochemical CN coupling? And then, in comes Dr. Bauseheb Dokhale, who did this work. So he's organic chemist, currently in Wyoming University. And when he started working on this project, we had this idea of using, pyrene. We know that pyrene is a very good optoelectronic material. Most polycyclic aromatic systems tend to be. And then we wanted basically to couple this with another material which could act as essentially an electron donor, right? So phenothiazine seems to be a good candidate for that. And then we looked at the typical reagents that you need to use as reported in the literature for doing this CN coupling reaction under ball milling. No additives, no external heating, and we get a sad face, okay? Very typical in chemistry in general, I think, as the students will attest to. So obviously, if you can't get this to work with one CN coupling site, you have no chance with 4, right? And that's, perhaps not surprising results. So we did the same thing with tetrasubstituted pyrene, and again, you don't have any luck with that. So we thought about this. We looked back at Hajime Ito's work, and we thought about the aggregation state of the palladium catalyst. He did some nice SEM work to show that this actually has an effect in the coupling reaction. We did our own SEM work, which is not here, which showed that this is actually a factor. So then we thought, what additives can we use to break up this aggregated palladium and activate it to do the mechanochemical reaction? So that's the route that we took. Okay. And we screened a bunch of different additives, and we found our candidate. I'm just going to give it a name X for now. This material actually worked out to be pretty good in activating the palladium catalyst. During that process, we do see that the reaction does work. The yield is about 50%, but remember, we were getting about 30% with Ito's work without any external heat source, and we have slightly better here. Also remember, that was one-side CN coupling, so this is actually a lot more difficult reaction to do. So if you think of it from many, many different points of view, this seems to be a very good outcome, right? Going back to what I was saying about cost, look at this, right? So the benchmark spirometad material, $400 US per gram. So obviously that's not going to scale if you're going to put that in a perovskite solar cell. Our material, we did the cost analysis, very low here. This is some other sort of benchmark materials which are also on the market, although they're not as commonly used. The other thing I'd like to point out here is solvent use. So you see here that many of the materials that people are using currently in the perovskite world, made from solution chemistry, are really bad for the environment. So even when you compare with spirometad, we do much better in our material. So we then said, okay, this is very nice, but can we actually see any photoconversion efficiency? Can we put this in a solar cell and see what we get? And that's exactly what we did. And again, comparing with spirometad, this is the JV curve. You can see here the short circuit current slightly worse for our material in red. But if you're talking about 3% or so difference in the JV curve performance, you also need to talk about the input, not just the output. So the input matters, and if the cost is this much, 3% is not huge price to pay. In terms of the photoconversion efficiency, we looked at both the encapsulated solar cell and the naked solar cell. So again, we've got about 2 to 3% difference where we do slightly worse than spirometad here in black. But then if you use the naked cell, which I would argue is actually a better test of performance, because it gives you direct indication of stability, you see that after 4 weeks, we actually do a lot better. So the solar cells with the spirometad actually are not stable, so they break down and the efficiency deteriorates much quicker. Okay, so hopefully that gives you some flavor of the kind of technologically valuable work you can do at relatively low cost using mechanochemistry. So we looked at the sort of stable end of the potential energy landscape there and what we can do with mechanochemistry. If I talk a little bit now about the extreme, the opposite extreme, which is where you have these very unstable composite mixtures, this was actually geared more towards environmental mechanic applications rather than optoelectronics. So Zainab Saeed, who could not be here unfortunately due to visa issues, did this work for her master's in my lab. She's now a PhD candidate. And what she showed was that you can actually use the same chemicals to make weakly stable, weakly sort of bound mixtures. So we have the pyrene, and then we have the phenothiazine. So remember before we showed that you can couple these things to form stable compounds. Now this is an example of where you can use the same molecules to make unstable mixtures, right? So we'll talk about sort of the properties we get with that. But what do we mean by a composite or an unstable mixture? Well, I think this community understands very well what a periodic co-crystal is, right? So you have 2 or more chemical fragments in one crystal that repeats in all directions, looks the same. Graham Day has done some good work on these kind of systems and showed that they are generally driven to form on energetic grounds, right? So they're more stable than the precursors. So a eutectic composite is where you don't have a single periodic crystal, but where the different crystallites are actually weakly interacting through surface interactions, right? So there isn't actually a single crystal here. There are multiple crystals, And it's just the surface interactions that are leading to the difference in the thermal profile and properties that you see. So we looked at this and we tried to see if we can apply this for remediation work, just to show, the kind of like the status of eutectics versus co-crystals. This curve shows the amount of Scopus documents dealing with eutectics versus co-crystals. You can see that there's a lot more work going on eutectics, so they're technologically much more valuable at the moment because people study them a lot more than co-crystals. But of course, that's the opposite in our community. So if I say a little bit about the properties of these materials, so again, remember we're trying to see if we can use these unstable composite mixtures to do remediation. Two of these compounds are actually polycyclic aromatic hydrocarbons with no functional groups. One of them is bisphenol A, which is a known pollutant, and then the other one you can classify as an additive. So of these four, three of them are recognized environmental pollutants, right? What are the improvements that you get in the solid state properties? Well, I think this was mentioned in a previous talk early in the week. Anytime you can modify the melting point or the thermal behavior of a compound, you're also changing the solubility because those two things go together. And this is particularly important for polycyclic aromatic hydrocarbons because, of course, their low solubility is the very reason why you can't get them out of the soil, right? It's difficult to dissolve them in something, even in organic solvents. So you can see here that, for anthracene, which has a very high melting point of about 222 degrees C, when you form the eutectic composite, you see a marked 50 degrees centigrade drop in the melting point. And this goes nicely, also correlates with the improvement in the solubility that you see for this composite. So almost a 5-fold improvement there for the anthracene composite. The mixtures are actually relatively stable even under slurrying. So this is very good for separation processes. The only thing I would highlight for our community, if anyone's interested in going in this direction of looking at eutectic composites, X-ray diffraction is not going to help you because you cannot see any difference in the powder patterns of composites through powder XRD compared to the precursors in the same way you would in co-crystals. I'm not going to dwell too much on this. This is just some microscopy work and the phase diagrams. The one thing I do want to highlight is that you see distinct morphological differences between the compounds, even after milling. So if you wanted to, you could actually use that as an identification. But of course, you would probably use SCM with EDX to do that if they have different functional groups. So I just want to say a little bit about the computational work that we did, which hopefully can be followed up by more systems and see if this trend holds. So generally, to get eutectic composites from ball milling, you need to use an anti-crystal engineering design strategy. So we're all familiar with the idea that paired synthons lead to good hydrogen bonds lead to co-crystals. So for eutectics, it's the opposite. So what you want is molecules that have non-complementary interactions, because then you will not likely see that they will form a crystal, but instead they will remain as separate crystallites and just have these weak surface interactions. So we used the well-known model in the polymer community called Flora-Huggins, which essentially models the mixing energy as a function of temperature using stochastic methods to look at the way that the molecules bind. So the key thing I just want to emphasize here is if you look at the chi distribution, which represents the mixing energy as a function of temperature, these three curves for the eutectics, you can see they will have very weak mixing energies. So that suggests that they're not good candidates for co-crystals. By contrast, the control sample that we used which is also anthracene containing, but this time it's a co-crystal, you can see that the distribution is very different. So you have a negative distribution throughout the energy profile, and this would indicate that actually the two compounds are strongly bound, so probably not a good candidate for a composite material. DFT energies also show the same thing, so that was very good. But again, I think the caveat here is this is a very small sample size, so I'm not claiming that this will work for every system, but it is a positive indication that modeling can help in discovering these kind of systems. So the last thing I just want to say, I think we've got a few minutes before the bus comes, is environmental mechanoremediation. So what do we mean by that? Well, if you look at the literature, people who work on soil chemistry, unfortunately, they tend to be engineers, not chemists. What they do is just take buckets of surfactants, they take some polluted soil, stick it in there, stir it, and then separate the surfactant from the soil, right? And the reason they do that is because we know that the surfactant essentially can form mycels. These mycels will basically form cavities around the pah, and this will hopefully allow it to be extracted from the soil. Problem with that, there are multiple problems, but the main problem is that the stuff you're using as surfactants tend to be probably worse than the thing you're separating, and you're also using quite a lot of stuff here, like a lot of surfactant in your solution here. Some work has been done on RMP, which is reactive milling of pollutants, where people try to oxidize directly the pollutant in the soil rather than separating it. So we've done some work on that as well, which I'll talk about. But the one that we focused on is actually where you don't do any reaction, but actually just use an additive to, again, weakly interact with the pollutant and hopefully then separate it using some sort of solvent-based method, right? So going back to what Francisco was mentioning before, 12 principles of green chemistry, this will probably closely align with thinking about your design for degradation from the beginning. So this work was done by Iman Abujami, who was completed her master's in my group recently. And what she was interested in is to try to see if we can use mechanochemistry to actually have good surface coverage between the pollutants that we find in the soil and the metal catalyst. So the metal catalyst is essentially changing the chemical profile or the functionality of the molecule, and then through that, the properties of the pollutant. So the idea is if we have good surface coverage between the pollutant and the catalyst, then that will support better transformation of the pollutant and hopefully easier separation, right? So again, we know from various works that if you just look at magnetite on its own and you do ball milling, you see these very clear blue aggregates in the SEM, and this corresponds to basically the catalyst, which is a pore form of the catalyst for doing oxidation. So you really want to disaggregate the material. If you use the pyridine with the magnetite and you do the ball milling, you can see also here that the situation is still bad. You still have islands of aggregates. That's not a good outcome to be, because it means that there isn't good surface contact between the pollutant and your oxidizing catalyst. So what can we do? Well, we play the same games. We go into the lab. We see what the engineers have done. And we try to use some sort of good additive to support contact between the pollutant and the catalyst. Many of the surfactants that people have used in the literature are unsuitable for ball milling because they tend to be liquids and they tend to be very viscous and hygroscopic. Some of them are suitable, SDS, SDBS, but we found candidate Y, which was actually much better than all of them and much cleaner in allowing good coverage of the pollutant on the surface of the catalyst. So this is just some of the chemical structures of these things. So just the last few slides here. So when you include the mysterious additive Y into our process and have the pollutant milled with the magnetite, you see a very different SEM EDX, right? So instead of having these separate islands of blue and red, Instead, what we see here is very small individual particles where you have good surface coverage between the organic substrate and the metal catalyst. And that's the sort of thing we're looking for. We've done some follow-up work on this where we actually showed that it does make a difference in the extraction. We're working on that, so I'm not presenting it here. But what I would like to end with is what happens in the kinetics of degradation of the pollutant with magnetite without the additive. So you see here, this is just a summary of the amount of the pollutant that we lose as a function of time. This is just the GCFID. So you can see that the process is relatively sluggish, right? So less than 20% degradation after 30 minutes. It goes up relatively slowly. So this is obviously not optimized. What we're now doing to follow this up with is, can we improve these kinetics by using this additive that we discovered to improve the degradation yield at lower time. So this is still very much ongoing work. So I hope that I've convinced you that unstable mixtures have a role in supporting environmental remediation, and that we shouldn't always just be looking for the most stable product from our mechanochemistry experiment. Surface activation is very important if you're using any metal catalyst in your reaction. So you really need to think about the aggregation state of the metal before you use it in ball milling, because that will obviously have an effect. And I'd like to just end by thanking our sponsors, which are listed here. My team, some of which could not make it. Abir and Praveen are here, so if you haven't had a chance to interact with them or see their posters, please do speak with them. And again, thank you for listening.
Thank you for your wonderful talk. Are there any questions or comments?
So
just before your question, sorry, just a quick announcement. So the bus departure time is changed now to 6, okay? So you don't have to run away right now. We have 30 minutes or so.
But you can keep
no
the
pressure.
questions short.
But yeah, probably we'll just have 1 or 2 more questions.
So
And
I can
then,
ask
yeah,
her now?
everyone will have a break.
You
Yeah,
want
go
me to
ahead.
ask her? Okay. So you were mentioning about crystal engineering and anti-crystal engineering strategies.
Yeah.
Crystal engineering itself, there are so many concepts which are proven to be not too following the trend. So how do you think that your anti-crystal engineering strategy will help you out in your
Sorry, repeat
work?
that last bit. How do I think the anti-crystal engineering strategy will?
Crystal engineering itself, there are so many exceptions are there.
Sure.
So how do you think your anti-crystal engineering will help you in this work?
Sure. Yeah, so I never really like rules because I think, as someone said earlier, rules are there to be broken, laws are not, right? So I think the exceptions you mentioned are definitely suggesting that there isn't like a single thing that leads to a co-crystal. And similarly, I would say there isn't a single thing that will lead to a eutectic composite. However, if you look at the work that was done by, I think it was Ashwini Nangia who did a really good ChemCom review article on eutectics. Generally, when he surveyed all the examples that were out there, and this is organic eutectics, mostly pharmaceuticals, you do find that shape mismatch and synthon mismatch seems to be common to most of them. We have had in this paper, if you read the SI of this paper, which is given here, we've listed a bunch of different polycyclic aromatic hydrocarbons that form eutectics with other compounds, and generally that also seems to hold true. So I think the trend seems to be that synthon mismatch and shape mismatch, these two things are important.
I'm not
To
sure.
answer your question.
I'm not sure my voice is going to hold, but I'm going to try. I think we have to be more careful using the term mechanochemistry, because I think grinding is actually a combination of thermo and surface chemistry. When we don't talk about autoplate chemistry or Bunsen burner chemistry, but the surface aspect is important. And all other ways of using energy in chemistry, we dump our energy directly into the electronic modes. So I think when we talk about mechanical chemistry, we should be talking about moving up the repulsive part of the potential.
Thank you for that, Craig. So I agree.
Hi. This is just a simple question. In your last bit, the soil stuff, you said you didn't want to use liquid additives because those are not good for mechanochemistry. Why not?
Yeah, they're actually, it's more to do with I know that people use liquid additives quite commonly in mechanochemistry. It's more to do with the viscosity of these things than the fact that they're liquids. So you want something that, will not, you want something that will be easy to disperse and not form one little clump inside your jar somewhere. And that seemed to be what the students observed.
Fair enough. It just seemed to me that a liquid would be easier to get out of there at the end of the day, which
Yes.
I guess you also want to do.
Yeah, I think in all of these processes we're using anyway a liquid at the end to dissolve our material and quantify it using GCFID. So the liquid is involved. It's not completely solvent-free. But as I say, I think in these cases you don't want something that's very hygroscopic or viscous because for practical reasons.
Thank you very much. Okay, thanks again.
And I also want to thank everyone in this session. Thank you for wonderful talks. And thank you for listening. Thank you.
For all speakers of this session, please come to this stage quickly because of photographs.
I think Abir has a camera in my group, unless somebody has a more professional.